Exploring each planet's core, we learn its secrets one by one, from Mercury's hot surface to Pluto's frozen depths. Mercury, the innermost planet, is the first stop on our journey as we brave the planet's cratered landscapes and the immense heat that defines it. Next, we'll take out in the direction of Venus, which is obscured by dense clouds that expose the raging fires beneath. Earth, our home planet, is seen as more than simply a static object. Each living thing on it has a unique life narrative that is intricately linked to the Earth as a whole. The red sky warrior Mars tells us stories of ice, water, and the never-ending quest to find extraterrestrial life. As we move out of the asteroid belt, we come across gas giants like Saturn, ringed by its beautiful rings, and Jupiter with its enormous red spot and plethora of moons. Because of their skewed orbits and strong winds, the icy giants Uranus and Neptune confound us. Pluto, a dwarf planet that was formerly the solar system's 9th planet, is the next stop on our voyage beyond Neptune. Right here, on the cusp of our cosmic doorstep, we discuss the many definitions of planets and rejoice in the variety and complexity of the solar system's planetary neighbors, and intricacy of the solar system's neighboring planets. The innermost planet in our solar system, Mercury, is a mysterious and extreme place. At 88 Earth days per orbit, it completes its whirlwind journey across space, passing closer to the Sun than any other planet. Although Mercury is not the sunniest planet, that honor goes to Venus, it does undergo the solar system's most dramatic temperature swings. As we travel through space to investigate Mercury, we learn about its distinctive features, including as its cratered surface that records events from the early days of our solar system, and its odd rotation and orbit, which provide a world with both perpetual light and perpetual darkness. Come with us as we explore the mysteries of Mercury, a dwarf planet that reveals a lot about how our solar system came to be and what happens to celestial worlds near their stars. The physical features of Mercury are both extreme and intriguing. Mercury is the tiniest planet in our solar system, with a diameter of around 4,880 km, just a hair bigger than the moon of Earth. Mercury has a density almost as high as Earth's, suggesting it has a big iron-rich core, which gives it a lot of power for such a little planet. The fact that Mercury's core accounts for over 60% of the planet's mass indicates that it may have experienced a violent past, maybe losing its outer layers to solar winds or a devastating impact, since this is the highest percentage of any planet in our solar system. Heavy craters and a moon-like appearance on Mercury's surface attest to the planet's long and eventful past as a target for asteroids and comets in the early solar system. A huge impact crater with a diameter of more than 1,550 kilometers, the Caloris Basin is one of the most prominent of these craters and provides evidence of the violent events that molded Mercury's formative years. Atoms of oxygen, sodium, hydrogen, helium, and potassium are blasted off Mercury's surface by solar radiation and make up its thin atmosphere, also called the exosphere. Extreme temperature changes on Earth are caused by its thin atmosphere, which is unable to store heat. Because Mercury does not have a substantial atmosphere to absorb the sun's heat, surface temperatures can reach 430–800 degrees C, hot enough to melt lead, during the day, and 180–90 degrees C, cold enough to melt lead, at night. The unusual spin of Mercury is another interesting physical feature. It takes just 88 days to complete one orbit around the Sun, but its axis rotation is extremely sluggish, requiring around 59 Earth days to finish a single spin. The remarkable effect of this is that at some locations on Mercury's surface, one can witness the Sun rise, quickly set, and then rise again in the span of a single Mercurian day. Because Mercury completes 3 revolutions for every 2 orbits around the Sun, this is an effect of the planet's 2-spin orbit resonance. From its thick metallic core to its sun-scorched surface and the stunning temperature variations that define its days and nights, Mercury is a planet of contrasts and extremes, as can be seen when one explores its physical properties. Mercury provides a glimpse into the processes that have molded our solar system and challenges our notions of how planets form and evolve. Mercury's orbit and rotation showcase a remarkable dynamical system within our solar system. It unveils a celestial ballet that surpasses the simpler motions of its planetary neighbors. Mercury is the closest planet to our star, with an orbit that is highly eccentric and the most elliptical of all the planets. At its closest approach, perihelion, Mercury's orbit ranges from 46 million kilometers, or 29 million miles, to 70 million kilometers, or 43 million miles, at its furthest point, aphelion. As a clear illustration of Kepler's laws of planetary motion, Mercury's speed changes significantly at perihelion and aphelion due to its elliptical orbit around the Sun. Equally peculiar is the way the planet spins. One rotation of Mercury takes around 58, 6 Earth days due to the planet's sluggish spinning on its axis. What results from this languid spin and its 88-day orbit around the Sun is intriguing. The 3-2-spin orbit resonance is observed on Mercury. What this means is that it completes 3 full rotations on its axis for every 2 Sun orbits. Consequently, Mercury's day is twice as long than its year, at 176 Earth days, measured from dawn to sunrise. It is believed that Mercury's spin was altered over millions of years to reach this unique condition via tidal interactions with the Sun, which is responsible for this resonance. Additionally, with an axial tilt of approximately 0.034 degrees, Mercury's rotational axis is almost perpendicular to the orbital plane. Since Mercury has the solar system's smallest axial tilt, it does not share the seasonal experiences of Earth or Mars. While the absence of a strong atmosphere causes Mercury's temperatures to fluctuate greatly between the day and night, the planet's relatively constant temperatures are mostly attributable to the fact that the Sun's position in the sky remains essentially constant throughout Mercury's orbit. Day and night on Mercury are affected by the planet's orbit and rotation, which also affects surface conditions and the environment that spacecraft encounter. Mercury is an intriguing object for studying the dynamics of planetary bodies and their interactions with their parent stars due to its exceptionally eccentric orbit and its distinctive spin-orbit resonance. Discoveries regarding the innermost planet in our solar system, Mercury, and the rich history and environment it possesses have been made possible via extensive investigation and observation. Mercury is less frequently visited than other planets because of the technological difficulties caused by its closeness to the Sun. Nevertheless, the efforts made have greatly enhanced our comprehension of this mysterious realm. In 1973, NASA launched Mariner 10, the first spacecraft to visit Mercury. In 1974 and 1975, Mariner 10 mapped approximately 45% of Mercury's surface during 3 flybys made possible by Venus's gravitational pull. Surprisingly, considering Mercury's diminutive size, this expedition revealed the planet's magnetic field, extensively cratered surface, and absence of a large atmosphere. Decades later, in 2011, the first spacecraft to circle Mercury was NASA's Messenger, which was launched in 2004. With its groundbreaking discoveries of water ice in permanently shadowed craters near Mercury's poles and confirmation of the planet's exceptionally high metal content, Messenger transformed our understanding of Mercury over the course of 4 years. In addition to studying Mercury's geology and drawing precise maps of the surface, the mission also probed the planet's thin exosphere and magnetosphere. Geological processes and volcanic eruptions have molded Mercury's surface throughout its history, according to Messenger's findings, which point to a more active past than was previously believed. With the 2018 launch of the Bepi-Colombo mission, the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, have teamed up to investigate Mercury. The European Space Agency's Mercury Planetary Orbiter and Japan Aerospace Exploration Agency's Mercury Magnetospheric Orbiter are the 2 spacecraft that make up this daring endeavor. Following up on Messenger's findings, Bepi-Colombo will conduct more in-depth investigations of Mercury's magnetosphere, internal structure, and magnetic field. The spacecraft aims to reach Mercury's orbit in 2025 after completing a sequence of intricate flybys of the planets Venus, Earth, and Mercury. It will use gravity aids to get closer to Mercury. Our understanding of Mercury has also been enhanced by observations conducted from the ground. Optical and infrared telescopes have examined the surface composition and monitored the exosphere, while radar-equipped telescopes have been employed to identify ice in the shadowed craters of the planet. Telescopes have tracked the exosphere and examined the surface composition. By shedding light on Mercury's surroundings and solar system position, these observations supplement space missions. Mercury research pushes the limits of what we know and can do with our current technologies. With every trip and observation, we learn more about the inner solar system and the characteristics of the tiniest planet, which helps us understand the processes that control it. It would be impossible to exaggerate Mercury's importance to our solar system knowledge. Mercury offers a one-of-a-kind opportunity to research solar system dynamics, planetary formation, and evolution, because it is the nearest planet to the Sun. The geological features, unusual orbit, and harsh environment of this body provide light on the processes that formed the early solar system and have an impact on the planets. The relative size of Mercury's huge iron core and other planets' innards can teach us a lot about how planets are formed and how they differentiate. For models of planetary creation and development, which provide analogies to Earth and other terrestrial planets, understanding Mercury's core is vital. Other planets in our solar system. Investigating the core-generated magnetic field of Mercury provides insight into the dynamo mechanisms that produce magnetic fields on other planets. The surface of Mercury serves as a record of the solar system's early years, preserved by its massive cratering. Celestial collisions in the inner solar system are studied by scientists through the study of these craters and the geological processes that have changed Mercury's surface over billions of years. Mercury experiences the solar system's most intense radiation and most dramatic temperature swings due to its closeness to the Sun and absence of a substantial atmosphere. Investigating the effects of these conditions on Mercury's surface and exosphere can teach us a lot about the durability of materials and the possibility of life in similarly harsh cosmic settings. Because of its extremely eccentric orbit and distinctive 3-2-spin orbit resonance, Mercury provides a natural laboratory for studying astronomical mechanics, with a focus on the role of tidal forces and orbital resonances. The research of exoplanets and the systems in which they orbit faraway stars stands to benefit greatly from these findings. Research into general relativity relies heavily on Mercury. Precession in its orbit is anticipated by general relativity and cannot be fully explained by Newtonian mechanics. Mercury observations are thus an important litmus test for our theories of gravity. The study of Mercury's habitability to water ice in permanently shadowed craters near its poles broadens our knowledge of the unexpected places where water and possibly life could exist, even though Mercury is inherently hostile to life. This complicates and enlightens our quest to find extraterrestrial life. To sum up, Mercury is more than just the tiniest planet in our solar system. It has immense significance. Investigating it has far-reaching consequences for many branches of science, including astronomy, planetary science, celestial dynamics, and the study of basic physical laws. Mercury is an important target for future space missions and ground-based investigations aimed at solving the mysteries of our solar system and beyond. Mercury, with its scorching days, freezing nights, and rapid orbit around the Sun, is a shining example of the celestial wilderness that our solar system is. Despite its little size, this mysterious planet has made enormous strides in advancing our knowledge of planetary science, stellar dynamics, and the early solar neighborhood. Mercury keeps surprising us with new discoveries, like the ones made by Mariner 10, Messenger, and Bepi Colombo, which question our preconceptions and increase our understanding. Mercury is a constant reminder of how much more there is to learn about our solar system and the ever-changing nature of its governing processes. The complex dance of forces that form our universe is revealed with each expedition to this rocky dwarf planet, which uncovers another layer of mystery. Mercury is important not only because of its orbit, but also because it provides insight into astrophysical principles and serves as a benchmark for studying other terrestrial planets and systems of planets outside our solar system. Mercury is still an important place to go on space missions because it could tell us more about how planets develop, how celestial things react under harsh environments, and whether or not there is life out there somewhere in the universe. Continued research into Mercury highlights the indefatigable human will to learn more about the universe and its inner workings. Mercury plays an important role in the solar system's intricate web, connecting the dots between creation, evolution, and the age-old mystery of our cosmic origins. The planet Venus, located in the solar system just behind the Sun. Venus, sometimes hailed as Earth's twin, is an intriguing astronomical object since it resembles our home planet in many ways, including size, mass, and rocky composition. Despite these shared characteristics, Venus is completely different due to its thick and poisonous atmosphere, which obscures the planet's surface. Venus, in sharp contrast to Earth's habitable conditions, is the hottest planet in our solar system due to its runaway greenhouse effect, which is caused by its envelopment of sulfuric acid and clouds of carbon dioxide. Venus, named after the Roman goddess of love and beauty, is anything from a placid and calm planet. As we embark on this visual adventure, we will delve into the mysteries of her searing heat, retrograde rotation, and volcanic scenery, giving light on why. Come and discover Venus with us. It teaches us about planetary ecosystems at their most extremes, and by delving into its history, gives us hope for the future of our planet and all the others out there. A mysterious and unpleasant climate resides on Venus, the mysterious sister of Earth. Envision the Earth embraced tightly by a thick blanket made mostly of carbon dioxide. There is another layer of dense air. Sulfuric acid clouds accompany it, creating an image of a planet where extremi is a bit of an understatement. The Venusian atmosphere is a classic example of the greenhouse effect taken to an extreme. What we know about the greenhouse effect on Earth is magnified to an extent that beyond comprehension here. With its dense atmosphere of carbon dioxide, Venus is the sunniest planet in our solar system. The terrible heat of this planet reaches levels that might melt lead and ruin any hopes of human visitation, reaching roughly 470 degrees T, or 878 degrees Fahrenheit. Conditions on Earth are drastically different from those in the frigid vacuum of space beyond, because this extreme heat is not limited to the surface, but spreads throughout the entire atmosphere. Being on Venus is like being about 1 kilometer under the water on Earth. The surface pressure is 92 times higher than Earth's. The surface conditions are really terrible due to the combination of the high temperatures and the pressure. Venus's clouds are crucial to the planet's weather system. Sulfuric acid, not water vapor, makes up these clouds, unlike the ones we see on Earth. Their high solar reflectivity makes Venus one of the most luminous celestial bodies in the night sky. But this reflecting characteristic also helps with the greenhouse effect, so the surface stays hot all the time. The atmosphere of Venus provides a rare opportunity to investigate extreme climatic systems, despite the planet's notoriously harsh circumstances. Researchers are very interested in Venus's super-rotating atmosphere, which is characterized by winds that round the planet at a rate significantly greater than the planet's own rotation. Observing the surface directly is difficult, but not impossible, due to this phenomenon and the heavy cloud cover. New insights into Venus's complicated weather patterns, like as its dense cloud cover and the presence of dark streaks called unknown absorbers, which trap a lot of solar radiation, have been revealed by recent missions and telescopic views. All of these things, plus the lightning that scientists have found in Venus's atmosphere, point to a planet that is constantly evolving and begs us to learn more about it. Venusian atmospheric research is about more than just academia. The story serves as a warning about the greenhouse effect gone wrong, and sheds light on the climatic problems that we are currently facing on Earth. Our sister planet Venus is engulfed in a broiling veil, while Earth's atmosphere is welcoming and lively. By learning about Venus, we may be able to protect Earth for future generations. Venus serves as a constant reminder of the intricate web of life on Earth and the deep secrets that exist inside our solar system as we delve further into its extraterrestrial environment and gaze through its corrosive clouds. Venus, whose thick atmosphere keeps it hidden from view, has a surface that exposes a geologic past that scientists find fascinating, as well as a story of volcanic activity and intense pressures. Venus is a planet of extremes, with a surface influenced by forces that are both familiar and foreign to our earthly acquaintances, hidden beneath its heavy clouds. Venus has more volcanoes per square mile than any other planet in our solar system, with its surface characterized by expansive plains and mountain ranges. Volcanoes like this, which resemble shield volcanoes on Hawaii, show that Venus has been experiencing volcanic activity for a very long time. Venus, on the other hand, has a distinct kind of volcanic activity and mountain development because it doesn't have tectonic plate action like Earth. Standing at a height of around 7 miles above Venus's surface, the Maxwell Montes are one of the planet's most prominent features. There is evidence from this mountain range and other highland regions that the planet's geologic past is complicated, including volcanic eruptions and its own kind of tectonics. Volcanic flows blanket Venus's plains, suggesting that the surface was originally reshaped by lava flows. These plains are young from a geological perspective, according to radar imaging, which means that Venus is currently undergoing geological activity. Venus may have had water in the past, but the stony planet doesn't provide any signs of liquid water today. Scientists have speculated that Venus may have formerly had oceans, possibly making it more Earth-like in its early history, according to certain geological features that suggest erosion and other water-related processes. There are craters on Venus, although not nearly as many as one might think. The lack of craters on Venus suggests that the planet's surface was resurfaced by volcanoes not long ago, giving the impression that Venus is a youthful planet. Some of the well-preserved craters had intricate radar-bright halos that may have contained debris released during impact. As we can see from Venus's geology, there are some similarities and some significant differences between Venus and Earth. Its unusual surface features, volcanic activity, and lack of water provide light on how planets formed and evolved, as well as what conditions other rocky planets in our galaxy may have experienced. The more we learn about Venus's history, present, and future from its surface and geology, the more mysteries surrounding our sister planet will surely unravel. Venus, our neighbor to the solar system, has some of the solar system's most intriguing orbital and rotational dynamics. Venus has its own special role in the cosmic ballet, and when we study its orbit around the Sun, we find out what makes it different from other planets. When Venus completes one full orbit around the Sun every 224.7 Earth days, the average distance it travels is 108 million kilometers or 67 million miles. 224.7 days on Earth. Venus is embraced by the inner solar system's warm embrace due to its comparatively short orbital period, which brings it closer to the Sun than Earth. But Venus's infamous heat is due to more than just its closeness to the Sun. On the contrary, the planet's thick atmosphere is crucial in absorbing solar energy, which causes surface temperatures to reach an excruciating 465 degrees Celsius. However, the orbit of Venus isn't the only thing that piques the interest of astronomers and space fans. Just as fascinating is the planet's axis rotation, mainly since it differs from the standard seen in the majority of planets. Retrograde rotation describes the way Venus spins on its axis in opposition to its orbit around the Sun. Thus, contrary to our earthly experience, the Sun would seem to rise in the west and set in the east on Venus. Venus's astoundingly sluggish rotation is only one more oddity about this planet. A Venusian year is longer than a single day on the planet, since one Venusian rotation takes approximately 243 Earth days. The already harsh climate is made even more so by the planet's slow rotation, which causes huge temperature swings from day to night. In addition, compared to Earth's 23.5-degree tilt, Venus's axis tilt is almost insignificant, at less than 3 degrees. Because of its very little tilt, Venus does not go through the seasons like Earth. For a long time, astronomers didn't know how to explain the planet's origin or evolutionary history due to its slow retrograde rotation and minor axial tilt. In order to understand Venus's temperature and geological processes and to plan future missions, it is essential to understand the planet's orbit and spin. We can learn more about the formation and behavior of planets in our solar system and beyond by keeping these basic characteristics of Venus in mind as we continue our explorations of this mysterious globe. Recent discoveries made by Venus have puzzled and intrigued scientists who are still trying to make sense of the planet. Astronomers found traces of phosphine gas in Venus's atmosphere, a chemical usually created by biological processes on Earth. This was one of the most intriguing discoveries. Because of this discovery, people all around the world started talking about the prospect of microbes in Venus's cloud decks, where conditions are milder. Although further research has cast doubt on and provided support for these conclusions, the ongoing discussion highlights how little is known about Venus and the opportunities it presents for astrobiological discoveries. As far as geology is concerned, Venus is still a mystery. Venus may not be a lifeless planet, but rather one that is alive with volcanic eruptions and tectonic upheavals, according to high-resolution maps and radar images from previous missions. Offering insights into planetary geology and the life cycle of terrestrial planets, these studies point to a planet that is active and may be altering its surface more regularly than previously assumed. In the future, scientists throughout the world are gearing up for a tidal surge of Venus-related exploration. Topography, spectroscopy, INSAR, Venus emissivity, radioscience, and NASA's Veritas. In the next 10 years, 2 spacecraft, the mission and the European Space Agency's Envision mission, will launch with state-of-the-art sensors that will allow scientists to create more precise maps of the planet's surface, examine its geological makeup, and probe its atmosphere. Questions such as whether Venus originally had oceans and how it became the hostile planet it is today are central to these missions, which seek to understand Venus's history and present. The Shukrayan-1 mission, to be launched by India's space agency ISRO, would investigate Venus's atmosphere in great detail, with an eye toward elucidating its chemical makeup, dynamics, and interactions with solar wind and radiation. A rising awareness of Venus's significance in comprehending both the diversity of planets in our solar system and the features of possibly habitable worlds orbiting other stars has prompted a revival in Venus exploration, which is reflected in these projects. We are on the verge of these thrilling activities, and Venus serves as a reminder of the limitless discovery potential of our neighboring planets. Venus will continue to baffle astronomers for the foreseeable future, but their findings could shed light on the universe's greatest mysteries, including how life began in the years to come. Our search for Venus's mysteries has only just begun, yet the results may change the course of history as we know it. As we near the end of our Venusian adventure, it becomes abundantly evident that this mysterious world is more than meets the eye. The ever-changing and varied nature of the solar system's planets is vividly illustrated by Venus, with its harsh climate and enigmatic terrain. It casts doubt on our knowledge of planetary science, global warming, and the possibility of extraterrestrial life. Venus research goes beyond the classroom. The mystery of Earth's history, present, and future can be solved with its help. Understanding the evolution of terrestrial planets and the impact of greenhouse gases on atmospheric conditions can be greatly enhanced by examining the parallels and contrasts between these two worlds. Some of the most important questions concerning the future of our planet's temperature and environment may be answered by learning about Venus. Our insatiable appetite for knowledge and our innate curiosity are exemplified by the continued interest in and plans for trips to Venus. We get closer to solving long-lived mysteries with each mission. Is the cosmos empty of intelligent life? What makes Earth special when it comes to supporting life? We are motivated to continue our scientific investigations on Venus because of the remote possibility of finding evidence of life there, whether ancient or modern. Looking forward, let's keep our support and enthusiasm for the worldwide missions to Venus high as we plan for the future. The secrets of Venus are more than simply interesting facts. They unite us in our common desire to learn more about the universe. Discovering Venus will test our knowledge of life as we know it, our ability to work together as a global community, and the limits of technology. Therefore, let us perpetually gaze upward, brimming with awe and intrigue. Like the rest of space, Venus is still having its tale told. Further exploration of our sister planet may lead us to astonishing revelations. Your company on this Venusian adventure is much appreciated. May your insatiable hunger for knowledge always guide you, and may your wonder at the cosmos never wane. Stay curious in the universe and all its mysteries until we meet again, and don't stop exploring. Embark on an enchanting voyage to Earth, our haven amidst the boundless expanse of space. Earth, the third planet from the Sun and the sole known location in the cosmos where life occurs, is nicknamed the Blue Planet because of its plentiful water and verdant appearance from a distance. Earth is home to an extraordinary variety of life because to its ideal combination of atmospheric conditions, distance from the Sun, and protective magnetic fields. On this journey, we will delve into the complex mechanisms that allow life to exist on Earth, as well as its dynamic atmosphere and temperature. The diversity of life on Earth is mirrored by the vastness of its landscapes, which range from the bottom of the ocean to the peak of the tallest mountain. We will learn about the forces that have molded the Earth's oceans and continents over the course of billions of years as we travel through its geological history. Come and be a part of our worldwide celebration of nature, exploration of its environmental problems, and revelation of the interdependence of all forms of life. Whether you have a deep concern for the environment or are just interested in learning more about our home planet, this Earth exploration will undoubtedly enlighten and motivate you, all while emphasizing the significance of protecting our ecosystem for the sake of future generations. Let us set sail on this exploration of the cosmos, marveling at the wonders of our home planet Earth. Earth is the home of all species on Earth, and by learning about its history, present, and possible futures, we can respect its sensitivity and strength. The thin veil of gases that envelops our home planet Earth and serves as a barrier between its surface and the immense universe beyond is known as the atmosphere. The atmosphere of Earth is a finely tuned equilibrium of elements that has supported life for billions of years, in contrast to the hostile environments of Venus, our neighbor. Argon, carbon dioxide, and other gases make up trace amounts in the Earth's atmosphere, which is mainly composed of nitrogen, about 78% by volume, and oxygen, 21% by volume. Our way of life depends on this composition. Nitrogen is essential for DNA construction and the air we breathe, while oxygen is necessary for the respiration of innumerable creatures. As a result of the greenhouse effect, a natural phenomenon that absorbs heat from the sun, Earth's atmosphere is able to control the planet's temperature. The absorption and emission of infrared radiation by greenhouse gases such as water vapor, carbon dioxide, and methane keeps the Earth at a habitable temperature. The procedure is well balanced. A world without greenhouse effect would be a frozen wasteland. If there was too much, it would become into a Venus-style scorching shack. The atmosphere is more than a static barrier. It is an interactive system that both causes and responds to changes in Earth's climate and weather. Each stratum of the atmosphere has its own unique properties and processes. In Earth's intricate atmospheric ballet, different layers serve different purposes. The troposphere is where weather occurs, while the stratosphere is where the ozone layer, which shields life from dangerous UV radiation, is located. Higher layers, such as the mesosphere, thermosphere, and exosphere, all contribute. The atmosphere of Earth is characterized by clouds that are generated by water vapor. By diverting solar radiation into space and retaining heat in the atmosphere, they are essential components of the world's water and climate systems. The climate of Earth is controlled by this intricate system of heating and cooling. The combustion of fossil fuels and deforestation has increased the concentration of greenhouse gases in the atmosphere, which is beginning to shift the balance in favor of humans. Warming and changing climates brought about by this amplified greenhouse effect are serious threats to all forms of life on Earth. The striking similarities to Venus's strong greenhouse effect serve as a sobering reminder of the gravity of preserving the equilibrium that allows our planet to support life. Additionally, the atmosphere acts as a barrier to prevent dangerous radiation from the sun and meteoroids from reaching Earth. An extra layer of protection for Earth's biosphere, the magnetosphere, is formed when the atmosphere interacts with the planet's magnetic field to redirect solar wind and cosmic rays. The atmosphere of Earth has been better understood as a result of extensive observation, research, and exploration. The delicate equilibrium required for life depends on vigilant stewardship of this ever-changing system. The importance of protecting Earth's atmosphere for the sake of future generations is underscored when we gaze upwards at the stars and investigate worlds such as Venus. More than just air makes up Earth's atmosphere. There is no life on Earth without it, as it is an intricate system that regulates our weather and climate and shields us from the cosmic radiation. By delving deeper into this tenuous envelope, our understanding of the cosmos and our role in it is expanding, and we are learning not just how to protect our own planet, but also about the atmospheres of faraway worlds. Our home planet, Earth, has a rich and varied geological history spanning more than 5 billion years. Earth is unique among the planets in our solar system in that its surface is dynamic and ever-changing due to natural processes. Life has flourished on this planet, with geological processes both shaping and being shaped by it. From the icy tundra of Antarctica to the hot sands of Africa, every inch of Earth's surface is a tapestry of extremes. The water on Earth makes up around 71% of its surface area, mostly in the form of rivers, lakes, oceans, and seas. Our planet's water abundance is a defining characteristic and essential for the survival of all known forms of life. Continents and islands spanning a broad range of geological types make up the other 29% of Earth's surface. Terrains such as the Himalayas and other towering mountain ranges, the world's breadbaskets of plains and plateaus, and the deep valleys and canyons carved out by rivers and glaciers over millennia are all part of this category. Fundamental to Earth science is the idea of plate tectonics, which describes the movement of the lithosphere, the outer layer of the planet that is composed of numerous smaller and larger plates. Many of the natural phenomena that we see, such as earthquakes, volcanic eruptions, and the development of mountain ranges, are the result of the movements and collisions of these tectonic plates on top of the semi-fluid asthenosphere. As a striking example of the Earth's dynamic geology, volcanoes may be seen in many places, the most active of which being the Pacific Ocean's Ring of Fire. Even though they can cause a lot of damage, volcanic eruptions are essential for making our planet habitable by changing the surface and atmosphere. The surface of the Earth is continually being shaped by erosion and sedimentation, which are propelled by water, wind, and ice. Sedimentary layers are formed when rocks and minerals are broken down and moved to new places. These sediments have the potential to undergo compression and cementation to produce sedimentary rock or metamorphic rock when heated and compacted. An essential topic in geology, the rock cycle shows how rocks change shape over long periods of time. With its ability to erode mountains, shape coastlines, and carve canyons, water is a potent change agent on Earth's surface. Earth is the only planet in our solar system that contains liquid water, which has shaped the surface and provided the ideal environment for life to develop and flourish. The ever-changing processes that make up Earth's surface and geology are on full display here. Each feature contributes to our knowledge of the planet's geological history and can shed light on its potential future. Understanding the planet's inner workings and the fine balance that allows life to flourish is both enhanced and deepened by our ongoing exploration and study of Earth's geology. Planet Earth has a balanced orbit and rotation, two features essential to the maintenance of life on Earth. By exploring these facets, we are able to learn more about the mechanisms that make Earth the most habitable planet in our solar system. The Earth's orbit around the Sun is almost perfectly circular, with just a small elliptical twist that keeps Earth's distance from the Sun relatively constant all year round. A year on Earth is defined by the 365, 25-day period it takes for this orbit to finish. A leap year is added every 4 years to account for this quarter-day surplus and ensure that the calendar is in sync with Earth's orbital location. To account for the angular misalignment between Earth's axis and its orbit, we include a leap year into our calendar every 4 years. The shift in seasons is caused by the angular tilt of the Earth's axis, which is around 23.5 degrees relative to the plane of its orbit. The axial tilt of the Earth is responsible for the changing seasons because it causes various regions of the planet to receive different quantities of sunlight at different times of the year as the Earth revolves around the Sun. Day duration is defined by the rate at which the Earth spins on its axis, which is around once every 24 hours. The day-night cycle is caused by the Earth's rotation because the Sun shines on various portions of the surface at different times. The direction in which Earth rotates is known as prograde, and it coincides with the direction in which the planet moves around the Sun from west to east. That is the reason behind the apparent sunrise and sunset times of the sun in our sky. One manner in which Earth's rotational speed impacts the world is by creating the Coriolis effect, which in turn affects planetary weather and ocean currents. An important factor in the development of weather systems, this effect causes the direction of moving air and water to change in the northern and southern hemispheres, turning them to the right and left, respectively. For life on Earth to persist, the delicate equilibrium of the planet's orbit and spin must be maintained. These basic features lead to the day-night cycle, somewhat consistent weather, and predictable seasons. They assist maintain the world's different ecosystems by regulating the environment. As a standard against which to measure other planets in our solar system and beyond, knowledge of Earth's orbit and spin sheds light on the circumstances required for life. The unique planet Earth's orbit and rotational dynamics are a constant reminder, as we travel through space, of the fine balance that allows life to flourish here. Earth, the home of all life, is a never-ending well of information on its geology, climate, and the complex processes that sustain it. Modern scientific and technological progress has yielded groundbreaking findings that expand our knowledge of our planet and its role in the cosmos. The careful study of climate change and its effects on the ecosystems and weather patterns of our planet has been one of the most important findings. The growing frequency of severe weather events, melting ice caps, and rising global temperatures have all been illuminated by satellite data in a way that has never been seen before. If we want to find ways to slow down global warming or at least adapt to its effects, these findings are essential. Much progress has been achieved in the field of geology in comprehending the inner workings of the Earth and the processes of plate tectonics. We now have a better grasp of how Earth's geothermal activity supports deep-sea life, thanks to the novel structures discovered under the ocean bottom via seismic monitoring and deep-sea research. These features include underwater volcanoes and hydrothermal vents that were previously unknown. Microplastics have been found in the most inaccessible places on Earth, from the ocean floor to mountaintops, demonstrating how far-reaching the effects of human civilization are. Because of this, people all over the world are talking about the importance of sustainability and the pressing need to alter our resource use and production habits. With many projects and expeditions planned for the future, our knowledge of Earth is about to reach unprecedented levels of sophistication. Missions like the Biomass satellite, which are part of the Earth Explorer series and are operated by the European Space Agency, collect vital data for climate and biodiversity research by mapping and monitoring the planet's forests in 3 dimensions. In order to better manage water resources and preserve the environment, NASA's SWAT mission will provide unparalleled data on the distribution and movement of water on Earth's surface. Ocean temperature, salinity, and current data is also continuously being provided by programs like Argo, which has sent thousands of floating sensors throughout the seas of the globe. Climate change, marine biodiversity, and ocean circulation patterns can't be understood without this data. New possibilities in environmental monitoring, disaster response, and resource management are emerging as a result of the integration of Earth observation technology with artificial intelligence and big data analytics. Natural catastrophe predictions, land use, and vegetation cover changes, and planet health monitoring are all made easier with these technologies that enable real-time analysis of environmental data. The natural world is complicated and interdependent, and as humankind continues to learn more about our home planet, new mysteries emerge. These findings not only add to our understanding, but they also highlight how critical it is to protect our special place in the universe. Earth observation and exploration will continue to advance, which bodes well for the future of our planet and its inhabitants. New discoveries will shed light on pressing environmental issues and motivate people to take action. Our last stop on our cosmic tour of Earth brings home just how special and precarious our home planet is in relation to the others in our solar system. The dynamic processes, varied temperatures, and rich biodiversity of Earth attest to the wonders and intricacies of the cosmos. Not only has this study of our planet shown us the diversity of landscapes and ecosystems, but it has also brought to light the intricate balance that allows life to exist. Exploring Earth entails more than just gaining an awareness of its present condition. exploring the past and looking forward to the future. It's a trip through time. It makes us reflect on how we might help keep the world habitable for future generations by maintaining this delicate equilibrium. The more we discover about our planet, from the seas to the atmosphere, the more we can do to keep it habitable for future generations. Earth exploration is a never-ending journey. We learn more about Earth's complex history, processes, and the life it sustains with every new discovery, whether it's in the deepest ocean depths or on top of the tallest mountains. In addition to deepening our knowledge, these initiatives strengthen our resolve to protect Earth. Please maintain an attitude of wonder, value the environment around you, and think about how you can help ensure its survival. The limitless endurance and beauty of Earth serves as a continual reminder of how everything is interdependent on everything else. In our never-ending quest for knowledge, let us not lose sight of the need of being responsible and cautious, so that Earth may continue to support life as we know it. We appreciate you coming along on this journey across the planet with us. We are excited to continue sharing more about Earth's beauties and how we can all help ensure its future, since the adventure of discovery is far from done. The fourth planet from the Sun, Mars, is commonly called the Red Planet because of its remarkable rust-colored surface. We hope you enjoy this fascinating tour to Mars. Countless expeditions, tales, and even the prospect of future colonization have been inspired by this celestial body, which has fascinated and intrigued astronomers, scientists, and dreamers alike. Endless quests, tales, and even the prospect of more colonization. Mars is more than simply a planet in our solar system. It holds the secrets to extraterrestrial life, the past and future of our solar system, and the goals of human space travel. The quest for water and evidence of ancient life, as well as the wonders of the Martian terrain with its towering volcanoes and enormous canyons, are only the beginning of what this remarkable planet has in store for us as we begin our investigation. Mars hides a myriad of mysteries just waiting to be solved. Come explore the atmosphere, geology, and exploration of Mars with us as we uncover the secrets behind this planet's unparalleled fascination. In sharp contrast to Earth's thick atmosphere, Mars's thin atmosphere envelops the red planet. The atmosphere of Mars is mostly carbon dioxide, which makes up over 95% of the atmosphere. Other minor components include nitrogen, argon, oxygen, and water vapor. Martian weather is heavily influenced by its composition. The planet is a frigid desert with a thin atmosphere that causes intense heat and cold, and a surface pressure that is less than 1% of Earth's at sea level. Mars's climate is defined by its very variable and often severe temperature swings. Temperatures around the equator may reach a pleasant 68 degrees Celsius during the summer, making it easy to draw parallels to a chilly day on Earth. On the other hand, since there isn't a dense atmosphere to trap heat, it doesn't take long for temperatures to drop to -125 degrees at the poles on winter nights. Dust storms are another Martian occurrence. They may range from tiny dust tornadoes called dust devils to events that encircle the planet and hide its surface for weeks or months at a time. Planetary features, like as its many massive volcanoes and impact basins, shape the wind patterns that propel these storms. Mars has several parallels with Earth despite its severe and unpredictable environment. Mars has 4 distinct seasons: spring, summer, fall, and winter, because its axial tilt is comparable to that of Earth and the other planets. On the other hand, every Martian season is almost twice as long as its Earth equivalent because of Mars' longer orbit around the Sun, which causes a Martian year to span around 687 Earth days. The study of Mars's temperature and atmosphere is important for more than simply academic reasons. It will play a pivotal role in humankind's future exploration and perhaps colonization of the red planet. To guarantee the safety and success of human activities on Mars, it is necessary to have knowledge of the Martian weather patterns, temperature extremes, and atmospheric composition in order to build shelters and suits for astronauts and to organize missions. In conclusion, the Martian environment is fascinating and demanding. The red planet's volatile temperature and tenuous atmosphere make it a perfect laboratory for studying planetary processes. As scientists learn more about it, we also learn more about how our solar system and Earth function. Martian landscapes are both strange and familiar to those living on Earth. Mars' varied landscapes, including its expansive deserts, majestic volcanoes, and deep gorges, reveal the planet's turbulent past. Martian geology is led by Olympus Mons, the solar system's greatest volcano. In comparison to Mount Everest, this enormous shield volcano stands 22 kilometers above the surrounding plains and has a diameter of almost 600 kilometers. Olympus Mons stands as a reminder of the extensive volcanic activity that molded much of the Martian landscape in the past. Stretching across the Martian equator for more than 4,000 kilometers and penetrating up to 7 kilometers into the planet's crust, the Valle Marineris Canyon system lies next to the volcanic zones. Even from orbit, this enormous gap shows how Mars's complicated tectonic processes have shaped the planet and provides information about its geological history. There are a variety of impact craters on Mars, from tiny, recently formed pits to huge, long-gone basins. The craters on Mars are a record of the bombardments that the planet has undergone over the course of billions of years, which tells us a lot about Mars's and the solar system's early past. The ancient deltas and river basins that dot Mars's surface provide some of the most striking evidence of the red planet's turbulent history. Mars may have once been home to oceans, lakes, and rivers. Today, these dried riverbeds and deltas serve as stark reminders of that past, painting a picture of a planet that may have once supported life. These features indicate that water flowed abundantly across Mars. Martian soil is rich in iron oxide, which gives the planet its distinctive red tint when we see it more closely. Much of the surface is covered in this rust-colored dust, which, when swirled in the tenuous atmosphere, may cause dust storms that can engulf the whole planet. Mars's geology tells the tale of a planet that has changed dramatically over the course of billions of years via a patchwork of characteristics. Mars has a varied and fascinating scenery that never fails to amaze and motivate with its majestic volcanoes, deep valleys, ancient riverbeds, and vast plains. We are continually reminded as we explore this extraterrestrial landscape of the natural processes that shape planets, including Earth, and of the secrets that lie under the surface. The Martian surface's affinity for water has long been a mystery. Mars used to have liquid water on its surface, contrary to the dry landscape we see now. Alluding to a period when water flowed freely over Mars's surface, this discovery is based on a system of ancient river valleys and delta formations carved into the planet's crust. For the time being, ice is the most common form of water on Mars. Water ice and dry ice, or frozen carbon dioxide, make up the polar ice caps, which can be seen even from Earth with a decent telescope. As the Martian seasons change, these caps expand and contract, providing a dynamic window into Mars's climatic cycles. Intriguing evidence of water ice under the Martian surface has been found in other locations as well by recent missions. Large amounts of ice concealed just below the surface at mid to high latitudes may be hiding there, according to radar data and lander observations. Future human explorers may find this ice to be an invaluable resource, as it may contain elements that humans need for survival, such as water, oxygen, and fuel. Additionally, the discovery of water ice gives promise to the quest for Martian life in the past. Life as we know it has the ability to flourish in environments where water is present. Martian habitability and the possibility of microbial life during warmer and wetter periods are both cast into doubt by the finding of water ice. In conclusion, Martian water is an important resource for future Mars research and possible colony efforts, as well as a record of the planet's temperature. We may expect the tale of water to play a crucial part in understanding our neighbor to the west as we continue our exploration of Mars. The red planet, Mars, travels in an elliptical orbit around the Sun, a course that takes about 687 Earth days, or a Martian year. The 4 seasons on Mars, spring, summer, fall, and winter, last roughly twice as long as they do on Earth due to the planet's elongated year, giving the Martian climate and terrain a distinct rhythm. A Martian day, or sol, lasts little more than 24 hours, more precisely 24 hours, 49 minutes, and 35 seconds, because the Martian axis rotation roughly matches Earth's, because it provides a familiar characteristic in the otherwise unfamiliar circumstances encountered by trips to Mars. The similarity in day length has fascinated scientists and space fans alike. However, Mars's axial tilt of around 25-19 degrees is what causes the planet to have seasons similar to Earth's. The seasons are not uniform in duration, however, since Mars has an irregular orbit. As a consequence of being closer to the Sun during the southern summer, summers on Mars are warmer but shorter in the southern hemisphere compared to the northern hemisphere. Adding another degree of complication to the Martian environment, winters in the south are colder and longer. From the size of the water and carbon dioxide ice polar caps to the frequency and severity of dust storms that may cover the whole planet, these seasonal fluctuations affect many parts of Mars' ecosystem. Future expeditions, particularly those that want to explore and even colonize Mars, must comprehend these patterns since they govern the possibilities for water extraction and the difficulties presented by Martian weather. Mars' complex orbit, spin, and seasons provide important clues about the planet's history, present, and future. These details illuminate the planet's climatic dynamics and its ability to sustain life, whether that be microbes in the past or humans in the future. From ancient astronomers beholding its reddish-orange light in the night sky to modern-day spacecraft scouring its surface, the quest to comprehend Mars has enthralled mankind for ages. Important steps have been taken in the investigation of Mars, and with each one, we are getting closer to understanding the red planet. Starting with telescopic views, we mapped the surface of Mars and were able to discover features like the polar ice caps early on in our exploration efforts. We owe a great deal to these findings, which piqued our interest in Mars and led to many inquiries on the red planet's climate and habitability. The Mariner missions, which launched the modern age of exploration in the 1960s, gave the first up-close views of Mars, exposing a planet with mountains, valleys, and craters. To learn more about Mars's surface, atmosphere, and habitability, a fleet of orbiters, landers, and rovers were sent out after these missions. Landing on Mars for the first time in the 1970s, the Viking missions studied the Martian atmosphere and soil and looked for evidence of life. Despite the lack of conclusive evidence of life, these missions greatly enhanced our understanding of Mars and encouraged more exploration. Over the last 20 years, many rovers have explored Mars, including Spirit, Opportunity, Curiosity, and Perseverance. To better understand the planet's temperature, geology, and the possibility of ancient life, these rovers have been outfitted with cutting-edge scientific tools. Their research has uncovered organic compounds, evidence of water movements in the past, and evidence of complex chemical environments that may have harbored microbes. Data on Marsquakes, gathered by the InSight lander as part of its mission to explore the interior of the planet, has shed light on the structure of Mars. Orbiters, like as the Mars Reconnaissance Orbiter, are still busy creating detailed maps of the surface of the planet, which will help with future mission landing site selection and weather monitoring. Mars exploration is more than simply a quest for information. It's a worldwide effort that brings nations and scientists together to learn more about our universe. Mars's past life and future exploration possibilities are being more illuminated with each expedition as new layers of secrets are peeled back. The National Aeronautics and Space Administration, NASA, the European Space Agency, ESA, and other international partners are planning missions to Mars with the goals of returning samples to Earth, exploring the moons Deimos and Phobos, and sending humans to walk on the surface of Mars in the future. Mars exploration is a powerful symbol of the insatiable human need to know more about the universe. Phobos and Deimos, two minor moons of Mars, each have their own fascinating history as they orbit the Sun. Both moons circle their respective planets, but the bigger and more cratered Phobos travels the farthest from Mars to any other moon in the solar system. As it continues to spiral inward, astronomers fear it may eventually either collide with Mars or split apart, creating a ring around the red planet. The smaller and further away Deimos circles Mars with far less drama than its larger and closer twin, Deimos, which shares its cratered surface and uneven form. It seems like a large coating of regolith or dust that has weathered in space is covering its surface given how smooth it is. Legend has it that Mars's gravitational pull snatched these moons eons ago from the neighboring asteroid belt. In contrast to the more spherical moons in our solar system, their composition, extensively cratered surfaces, and irregular forms lend credence to this notion. Scientists are very interested in Phobos and Deimos, despite the little research of these moons. Astronomical missions to these moons may provide light on the asteroid belt, moon formation, and the early solar system. Phobos, in particular, is thought of as a possible base for future Martian human expeditions, providing a one-of-a-kind vantage point from which to observe the red planet and plot out surface excursions. Phobos and Deimos are becoming more and more important as we continue to research Mars and the solar system as a whole. These moons are extraterrestrial friends in more ways than one. The secrets of the universe can be revealed with their help. Looking forward to the future of space travel, Mars is a guiding light for humanity's next great leap. Mars is more than a potential stop for space probes in the future. It ushers in an era of expanded human influence beyond our home planet and into the vastness of space. Over the next several years, a group of space agencies and commercial organizations from across the world will lead a fleet of missions to Mars. By studying the Martian atmosphere, soil, temperature, and the possibility of previous life, these missions hope to better decipher the planet's secrets. Robotic missions are one of them, and they will keep laying the framework for human exploration, the grandest undertaking of them all. The idea of establishing a human settlement on Mars has gone from science fiction to a realistic objective. The plans for human habitation are being drawn up by scientists and visionaries who are thinking about the problems of long-duration spaceflight, how to live sustainably in difficult settings, and how to use the resources of Mars for building materials, air, and water. Not content with just landing people on Mars, programs such as SpaceX's Starship and NASA's Artemis want to create a sustained presence on the red planet. The trip to Mars, however, presents a number of ethical and technological hurdles. Discussions revolve on questions such as how to administer interplanetary colonies, the mental and physical impacts of residing on another planet, and how to safeguard any possible life on Mars. As we gear up for the next phase of space travel, humanity must think about what it means to leave our mark on the solar system. Despite these difficulties, Mars still has great potential. It might lead to new discoveries in many fields, such as the possibility of life in harsh circumstances and the use of Martian geology to learn about Earth's history. From improved life support systems to alternative energy sources, Mars is a testing ground for technology that could one day help Earth's biosphere. Mars encourages us to dream large, to face the unknown with bravery and curiosity, as we are on the brink of these future expeditions and colony plans. The idea presents a compelling image of a future where humans are not limited to just one planet, but rather a multi-planetary species that flourishes in the boundless universe of space. In this incredible journey, Mars is more than just a stop. It ignites progress, creativity, and the indomitable human will to discover. The path ahead will demand our utmost creativity, resourcefulness, and resolve. But the payoff, the growth of human understanding, the preservation of our species, and the coming together of people around a common goal, promises to be one of the greatest triumphs of our species. As we plan for Mars exploration's future, we appreciate you being here with us. A new era for mankind among the stars awaits us on the red planet, which calls out to us with the prospect of fresh challenges, discoveries, and chapters. Encourage space exploration, maintain a sense of wonder, and never stop gazing up. We are almost to the next horizon. Join us on a remarkable journey to Jupiter, the enormous protector of our solar system. Jupiter is a celestial wonder that floats magnificently in the night sky. It is the biggest planet in our solar system and a mysterious and violent globe full of stunning natural beauty. This gas giant beckons us to explore its vast atmosphere in search of the mysteries it conceals, with its whirling clouds of brilliant hues and storms bigger than Earth. We have always marveled at Jupiter, a dazzling star in the night sky from the safety of our own planet. and we have often wondered what forces operate under the surface of its thick clouds. Jupiter, the ruler of the Roman gods, has been known to humans from ancient times and has always fascinated and intrigued them due to its immense size and prominence. We will investigate the creation of Jupiter, its enormous and chaotic atmosphere, the famous Great Red Spot, and the secrets of its strong magnetic field as we go off on our journey. While passing this gas giant, we will see its faint rings and its vast system of moons, each of which is a planet in its own right. We are on the verge of discovering Jupiter's long-lost mysteries, thanks to state-of-the-art research and the observations of spacecraft that have traveled great distances from Earth. Come with us as we explore the hidden depths of Jupiter, the gas giant and solar system influencer, and its whirling clouds and mists. The gas giant Jupiter, a planet prone to storms and crucial to deciphering the cosmic neighborhood's beginnings, is the protagonist of this tale. As we continue our cosmic tour, we reach Jupiter, the gas giant and mysterious guardian of the outer solar system. Over 5 billion years ago, Jupiter was born from the same gas and dust cloud that formed the Sun and the rest of our solar system. Its genesis represents a significant milestone in the cosmic narrative. When our solar system was young, the Sun had only just begun to spin, and the dust and debris from creation were still whirling about in the frozen depths of space. Jupiter took form inside this primordial cradle. Because of its enormous gravitational pull, the planet was able to collect and store a large amount of the primordial gases, hydrogen and helium, that were present in the early solar system. The gas monster we see today is the result of this buildup of dust and gas spiraling together. Hydrogen and helium, the two most plentiful elements in the universe, make up the bulk of Jupiter's composition, which reflects that of the original solar nebula and provides evidence of the planet's beginnings. With the exception of the mass needed to trigger nuclear fusion at its core, this magnificent planet is basically a dwarf star. The planet's metallic core is formed at the depths of a sea of hydrogen that is subjected to tremendous pressure under the planet's storms and spinning clouds. As a byproduct of its internal dynamic processes, Jupiter's magnetic field, the strongest of all the planets in our solar system, is produced by this metallic hydrogen. Jupiter is unique among terrestrial planets like Earth in that it does not have a solid surface. Rather, its structure is defined by changes between gas and liquid phases. The hydrogen that makes up the majority of the planet is composed of liquid and metallic hydrogen, and the atmosphere extends deep inside the planet. Inside is still much speculation as to whether Jupiter's core is rocky or a thick mixture of heavy elements. Either way, the immense pressure and heat inside are incomprehensible to us here on Earth. In addition to illuminating Jupiter's status as the gas giant ruler of our solar system, the processes that formed it and its composition provide information on the early universe's shaping. We are pushed to further our knowledge of planetary formation, the behavior of strange materials under harsh circumstances, and the variety of celestial bodies in our cosmos by its presence, which in turn pushes us to increase our grasp of planetary science. Our cosmic neighborhood has been shaped by a complex web of events, and the immensity of space is becoming more apparent as we explore Jupiter's secrets. Jupiter, with its whirling bands of clouds and intense storms, is a cosmic guardian and a huge key to understanding our solar system's past. The gaseous atmosphere of Jupiter encases the whole planet and extends to depths of hundreds of kilometers. A sophisticated weather system unlike any other in our solar system resides inside this gaseous envelope, which is dominated by hydrogen and helium, the same atoms that comprise the Sun. Cloud bands called belts and zones encircle Jupiter's atmosphere, formed by the planet's fast rotation and the increasing heat from its core. Cloud kinds and storm systems are shown by the band's varying colors, which range from deep reds and browns to whites and blues. In Jupiter's atmosphere, the Great Red Spot stands out as a prominent feature. It is a massive storm that has been raging for at least 400 years, and perhaps much longer. This enormous storm is so huge that it might contain 3 Earths. The complicated chemical processes triggered by Jupiter's UV radiation acting on the molecules in the atmosphere are believed to be responsible for the swirling crimson colors of the Great Red Spot. As the storm spins counterclockwise, wind gusts of up to 430 kph, 267 miles per hour, are recorded. Research on the Great Red Spot's magnitude and longevity continues at a fever pitch. Jupiter doesn't have a solid surface as Earth does. Thus, the Great Red Spot can keep spinning without losing power to friction with landforms, which is why this storm has persisted for so long, according to scientists. The Great Red Spot has been diminishing in recent observations, which has sparked concern about its future and the lessons it might teach us about the dynamics of Jupiter's and other planets' atmospheres. In addition to the Great Red Spot, Jupiter's atmosphere is rife with many more storms and vortices, some of which are as powerful as hurricanes on Earth, but far smaller in comparison to Jupiter itself. Internal heat, fast spin, and complicated chemical interactions drive the dynamic processes that regulate Jupiter's atmosphere, and these storms provide a window into these processes. Observing and studying Jupiter with advanced telescopes and spacecraft brings us nearer to understanding the workings of the universe. Jupiter's magnetic field is a marvel of our solar system, standing as the biggest and strongest planetary magnetic field among all the planets. By studying the atmosphere of Jupiter and its iconic Great Red Spot, scientists gain insights into its climate and weather patterns across the solar system, as well as beyond. The magnetic field that surrounds Jupiter, its moons, and even interacts with the solar wind is created by the motion of metallic hydrogen in Jupiter's core and stretches into space for millions of kilometers. The solar system's most remarkable occurrences may be traced back to this enormous magnetic field. At Jupiter's poles, the gas giant's magnetic field interacts with solar particles to produce auroras that are more spectacular than those seen on Earth, lighting up the gas giant's atmosphere with breathtaking light shows. On the other hand, Jupiter's powerful magnetic field has its drawbacks. It ensnares a great deal of charged particles, which in turn creates strong radiation belts that surround the planet. Spacecraft face formidable obstacles from these radiation bands, which are far stronger than Earth's Van Allen belts. Potential future expeditions to explore the planet and its moons are jeopardized by the high radiation levels inside these belts, which may harm equipment. In order to navigate Jupiter and its system, spacecraft must be designed to endure extreme temperatures, pressure, and radiation. Juno, a NASA mission, has been prepared to face these difficulties head-on by being overly protected and outfitted to endure the extreme weather. We can still investigate Jupiter up close despite the strong irradiation thanks to missions like NASA's Juno, which were built with these constraints in mind. Juno's orbits are meticulously planned to minimize exposure, allowing the spacecraft to collect priceless data while safeguarding its delicate sensors from the harsh radiation belts of Jupiter. We can learn a lot about the operation of magnetic fields surrounding other planets, and whether or not moons and planets may be habitable in such harsh conditions by studying Jupiter's radiation belts and magnetic field, which helps in the design of future missions. We will learn more about Jupiter's internal structure, atmosphere, and the ever-changing space environment via our continued exploration of the planet's radiation and magnetic field. By expanding our knowledge of Jupiter's radiation belts and magnetic field, we are expanding the limits of human space travel capability and gaining a better appreciation for the wonders of this gas giant. The magnificent and extensive ring system around Saturn is the first thing that comes to mind when we consider planetary rings. But the gas giant Jupiter also has its own ring system, which is less well known but no less interesting. The Voyager 1 probe surprised scientists in 1979 by discovering Jupiter's rings, which added a new dimension to their knowledge of this enormous planet. Jupiter has dimmer rings made mostly of dust rather than the brilliant ice rings of Saturn. It is thought that these particles are ejected when interplanetary debris hits the surfaces of Jupiter's minor moons, or when meteoroids strike the moons themselves. This causes the rings to form a complex structure that is hard to see from Earth and can only be understood by a close inspection by spacecraft. There are three primary parts to Jupiter's ring system: the halo ring, the main ring, and the gossamer rings. The halo ring encircles Jupiter around its equator and is composed of a dense inner torus of particles. Its apparent thickness is about 20,000 kilometers. Next to the halo, Jupiter's most prominent ring, the main ring, lies, narrow yet brilliant. Meti, and maybe Adrastea, two minor moons that orbit close to the ring, are the main sources of its composition. The ethereal, see-through gossamer rings extend beyond the main ring. One reason for their ethereal, see-through look is because these rings are really two distinct pieces. In reality, these rings originate from two different celestial bodies: the moon, Amalthea, and Thebe. These gauzy rings are made up of small, dust-sized particles that spread out from their moon origins. They are broader and extend far into space, but they are far less dense. Finding and studying Jupiter's rings has reshaped our conception of ring systems, revealing that similar structures do not just exist on Saturn, and that even dust may produce a breathtakingly magnificent cosmic event. As new missions to the gas giant learn more about its intricate structure, Jupiter's rings serve as a constant reminder of how our solar system is dynamic and ever-changing. As our investigation of Jupiter and its surroundings progresses, the rings provide a fresh angle on the dynamic Jovian system, the mechanisms that determine the moon's existence, and the planet's relationship with its moons. Our understanding of Jupiter and its cosmic role will be enhanced if, via the use of future spacecraft and cutting-edge technology, we are able to learn more about the planet's rings, with a mass more than 5 times that of all the other planets put together. Jupiter, the gigantic protector of our solar system, displays some of the most intriguing orbital and rotational characteristics seen in our heavenly neighborhood. Its gravitational pull is so strong that it determines the destiny of many things that go too near. Jupiter takes around 12 Earth years to complete one orbit around the Sun, making it a very long trip. Its fast revolution every day stands in stark contrast to our leisurely journey across space. Jupiter is located outside the asteroid belt and marks the beginning of the outer solar system with its orbit, which is an average of around 2 astronomical units from the Sun. Its elliptical, rather than perfect orbit around the Sun, causes subtle but significant changes to the structure of the solar system, especially to the orbits of nearby asteroids and other minor bodies. The gas giant is the fastest spinning planet in our solar system, spinning at an incredible speed on its axis and completing a revolution in little under 10 hours. Equatorial bulging describes how Jupiter's surface bulges near the equator and flattens toward the poles as a result of its fast rotation. Because of this phenomenon, Jupiter appears oblate, with a broader equator than the circumference. The complicated atmospheric dynamics that give Jupiter its distinctive banded look are driven by the rapid rotation of the planet. Winds traveling perpendicular to the equator form these bands. Cloud layers traveling at varying speeds and altitudes are shown by the brilliant zones and dark belts. A clear manifestation of the tremendous force of Jupiter's rotational energy is the differential rotation, which exhibits varied speeds at various latitudes. The most powerful magnetic field in our solar system is produced by Jupiter, which is impacted by its rotation. A huge magnetic field that stretches millions of kilometers into space is generated by the internal dynamo, which is controlled by the spinning of a metallic hydrogen core. This field forms a large magnetosphere, which traps charged particles and causes the poles to display breathtaking auroras. The physical properties of Jupiter are defined by its orbit and spin, which also have an important impact on the dynamics of the solar system as a whole. Its gravitational pull works as a cosmic vacuum cleaner, preventing asteroids and comets from crashing into the inner solar system and stabilizing the planet's trajectories. Jupiter is the gas giant ruler of our solar system, and its orbit and revolution form the bedrock of its identity. They shape its atmosphere, power its magnetic phenomena, and protect our solar system's monarch planet. The planetary order in our cosmic vicinity is protected by these forces, which also shape its atmospheric properties and drive its magnetic events. More mysteries about the birth, development, and dynamic processes that control our solar system are being revealed as our exploration of Jupiter and its complex system progresses. Discovering everything there is to know about the gas giant Jupiter has been an enormous undertaking, requiring us to travel billions of kilometers away from Earth. Pioneer 10 and 11 spacecraft launched in the 1970s were the first to get a close look at Jupiter, illuminating the planet's complicated atmosphere and plethora of moons for the first time in human history. Pictures of Jupiter that show its many moons and complicated atmosphere. The Voyager 1 and 2 spacecraft continued the exploration of the outer planets after their 1977 launches, following in the footsteps of the pioneers. During their 1979 flybys of Jupiter, they provided new information on the gas giant's magnetosphere, atmosphere, and moons. Our knowledge of the Jovian system was completely transformed by the findings made by Voyager, which included the potential of a deep ocean on Europa and volcanic activity on Io. The subsequent giant stride in our exploration was the 1995 arrival of the Galileo spacecraft to Jupiter. During his 8 years in Jupiter's orbit, Galileo studied the planet's magnetic field, atmosphere, and moons in great detail. Before succumbing to the tremendous pressure, it released a probe into Jupiter's atmosphere, which it used to transmit data on the composition and dynamics of the gas. The idea that the Galilean moons may have habitable habitats was further cemented by Galileo's views of them. The idea that the Galilean moons may have habitable habitats was further cemented by Galileo's views of them. The Juno spacecraft has been studying Jupiter's auroras, atmosphere, and structure since it landed in 2016 and peered behind the planet's thick clouds. Juno's goal is to learn about Jupiter's past and present by exploring its interior and searching for artifacts from the early solar system. Its precise measurements of Jupiter's magnetic and gravitational fields, together with its breathtaking photographs of the planet's poles, are shedding light on the composition, core, and enormous cyclones that rage there. The Europa Clipper mission is slated to launch in the 2020s and will conduct in-depth studies of Jupiter's moon Europa. The mission's goal is to find life on Europa by exploring its icy surface and deep water. It is clear from this voyage that research into Jupiter's moons as potential habitable planets has replaced earlier efforts. As new information about Jupiter has been uncovered by successive missions, our solar system ideas have been called into question. These endeavors show that humans have an unquenchable curiosity in the planet and are also remarkable technological and scientific accomplishments. We may be about to discover something new about Jupiter and its moons that might alter our place in the cosmos. So far, we have barely touched Jupiter's surface. The desire to explore space and beyond will inspire people of all ages, and this is only the beginning. In the intricate dance of the solar system, the moon and the planets, the gigantic Jupiter is an essential dancing partner. Changes to the environment extend well beyond its close proximity as a result of its massive size and strong gravitational attraction. Jupiter is primarily responsible for protecting our inner solar system and acting as a cosmic vacuum cleaner. Asteroids and comets that may cause harm to Earth are redirected by its gravitational attraction. When Jupiter catches or ejects these space rocks into the outer solar system, it reduces the number of potential impactors that can cause catastrophic disasters on Earth, which is crucial for the long-term stability of Earth and the preservation of life as we know it. Jupiter may influence even the blueprints of our planetary system. Its gravity has affected the placement of asteroid belts and the orbits of the planets. The major reason these rocks in the asteroid belt between Jupiter and Mars don't merge into planets is Jupiter's gravitational pull. The significance of Jupiter in maintaining the structure and balance of our planetary neighborhood is shown by this dynamic. In instance, the Galilean moons provide light on yet another aspect of Jupiter's significance. Two moons, Ganymede and Europa, have caught the attention of space sleuths searching for extraterrestrial life. Seas under the surfaces of both moons are possible. Planet formation, evolution, and the possibility of life on other celestial bodies may be better understood by looking at Jupiter's dwarf solar system. Because of its movement during system formation, Jupiter is thought to have significantly impacted the shape of the early solar system. Theoretical speculations state that Jupiter initially retraced its steps to its current location after moving inward toward the Sun. This migration may have impacted the evolution of Earth and the other terrestrial planets, as well as the distribution of water in the inner solar system, which is crucial for life. At long last, Jupiter can serve as a natural laboratory for research into gas giants and planetary atmospheres. Investigating Jupiter's complex internal structure, magnetic field, and atmospheric dynamics can provide light on other gas giants in our solar system, as well as exoplanets orbiting other stars. As we near the end of our celestial tour of Jupiter, the largest planet in our solar system, its immense size and intricate structure continue to astound us. Jupiter celebrates the wonders of the cosmos with its spinning storms, powerful magnetic fields, and multitude of diverse moons. Besides being a breathtaking natural phenomenon, this gas giant also contains information that might explain the origins of our solar system. We can learn more about the formation of the terrestrial planets, like Earth, by studying Jupiter and its satellites. Europa and Ganymede's deep oceans in particular pose a threat to our understanding of planetary systems and the possibility of extraterrestrial life. Jupiter will continue to entice explorers and scientists with its mysteries. Every mission, from Juno's groundbreaking explorations to the European Space Agency's JUICE, the Jupiter Icy Moons Explorer, adds to our growing understanding of the mysteries surrounding the massive planet. Not only are these missions incredible demonstrations of human ingenuity and curiosity, but they also contribute significantly to our understanding of the universe and our place in it. These are the building blocks of our understanding of the universe. Exploring Jupiter represents humanity's aspiration to broaden our understanding beyond our current boundaries, discover uncharted territories, and continuously challenge our preconceived notions. In their shared quest for wisdom, participants in this voyage hail from all walks of life and all corners of the globe. Let us carry forth the daring spirit that Jupiter stands for. We need to persist in our explorations, inquisitiveness, and awe towards the universe. The story of Jupiter is far from over. Maybe the most astounding findings are yet to come, concealed from prying eyes of generations to come. Thank you for sharing this amazing voyage with us to Jupiter. You should be inspired to pursue information, broaden your views, and speculate about what more the cosmos has in store by the immense extent of space. Your time is much appreciated. The universe will always astound us, so long as we keep seeking answers and asking questions. Outside of its ring system, Saturn extends greatly. The sixth planet from our Sun, Saturn, is a gas giant mainly composed of hydrogen and helium, similar to Jupiter, Uranus, and Neptune. With its mysterious core, complex atmosphere, and fascinating moons, this odd planet continues to confound scientists. Saturn is an intriguing topic that will be chronicled in this film, beginning with its formation billions of years ago and continuing with current scientific endeavors that seek to decipher the secrets of this enormous planet and its many moons. The composition and structure of its rings, the functioning of its atmosphere, the intriguing peculiarities of its moons, and its purpose within our solar system will all be explored. Come along as we explore the cosmos in search of the mystery, and beauty of Saturn. The secrets and marvels of this planet have enchanted humans for generations, and you are about to be astounded and enthralled as they have always been. Saturn is a gas giant with ice and rock rings. As we travel through space and time, we learn more about this fascinating planet and become nearer to understanding the vastness of the universe around us. Saturn, the planet that embodies the mystique and complexity of our solar system, is the next stop on our cosmic trip. All of the planets in our solar system, including Saturn, arose from the same primordial gas and dust cloud around 4-5 billion years ago. Since it contains a large amount of hydrogen and helium, two elements that were abundant in the early solar system, this object is classified as a gas giant. Hydrogen makes up the bulk of Saturn's mass, with helium coming in second. This makes Saturn's composition intriguingly similar to that of the Sun's. All of the moons and planets in our solar system have a common origin, as this similarity shows. But Saturn stands out because of its peculiarities, which make it an endless well of curiosity and study. One of the most remarkable aspects of Saturn's composition is its density. While Saturn is the second largest planet in our solar system, its very low density makes it capable of floating in sufficiently huge bodies of water. Because they lack solid surfaces, gaseous planets have lower overall densities than terrestrial planets like Earth, which makes them uncommon. Legend has it that rock, iron, and nickel make up Saturn's cloud tops, which hide the planet's solid core, which is encircled by flowing helium and hydrogen. The massive increase in temperature and pressure as one reaches the core creates conditions that scientists still don't fully understand. The formation of Saturn also had a significant effect on the distribution of materials in the early solar system. The immense gravitational pull of the planet molded not just its formation, but also the expansion of its moons and the distinctive rings that define its look, drawing in and retaining a great deal of the primordial dust and gas. Our growing knowledge of the mysterious planet Saturn sheds insight on the processes that shaped our solar system, from its gaseous layers to its solid core and beyond, thanks to findings on its composition and origin. Saturn inspires a sense of wonder and curiosity, making us want to explore the universe deeper to uncover its secrets. The rings of Saturn are the main attraction of this celestial body, which are a distinguishing feature that sets it apart from every other planet in our solar system. Despite having a surface that is less than 1 kilometer thick, it extends over 280,000 kilometers from Earth. Astounding as celestial engineering gets, the Saturn rings stand out. The rings consist mostly of water ice, but also include some stony material and a great variety of particles, from the size of dust grains to that of mountains. The rings' composition causes them to shimmer in sunlight, creating a light display that has fascinated onlookers of all political persuasions for decades. The scientists have argued and studied the subject of Saturn's ring origins. The conventional wisdom is that Saturn's rings formed when moons were either destroyed in collisions or pulled apart from the planet by Saturn's strong gravitational pull. When they first formed in the primordial gas and dust disk that surrounded Saturn, they may not have been able to condense into moons due to the planet's enormous tidal forces. In other words, Saturn's rings are dynamic, meaning they're always evolving. Their discovery order dictates the order in which they are organized into several main divisions, which are named alphabetically, starting with the innermost D ring and working their way out to the outermost E ring. Due to the gravitational attraction of Saturn's moons and ring particles, some of the minuscule ringlets in each ring congregate while others separate, each with its own distinct set of characteristics. The dynamics of the ring system are impacted by orbital resonance, which is particularly noticeable for moons that orbit close to or within the ring gaps. Moons like this, which are also known as shepherd moons, hold the ring system together. They provide complexity and aesthetic appeal to the system by helping to contain particles and create gaps. New insights into Saturn's rings, provided by missions like Cassini and others, have revealed hitherto unseen structures and phenomena such as propeller patterns, whirling density waves, and bending waves caused by the planet's moons and wobbles. These results provide a quick astronomical overview of these breathtaking natural wonders, and they imply that Saturn's rings are several 100 million years younger than the planet itself. Any spectator will be captivated by Saturn's rings due to their unearthly beauty and the knowledge they provide about the processes that generated and developed our solar system. They serve as a continual reminder of the universe's vitality and constancy while inviting us to study and understand the mysteries within and beyond. A fascinating and complex picture of atmospheric dynamics and weather patterns that are substantially different from Earth's is painted by Saturn's enormous hydrogen and helium atmosphere. The bands in the upper atmosphere of this gas giant are just as visible as those on Jupiter, but much fainter, due to the thick haze that envelops the planet and makes it harder to see the atmospheric storms below. The atmospheric bands of Saturn are a result of the planet's upper atmosphere being home to some of the fastest winds in the solar system. The highest possible speed of these winds is 1,800 kph, or about 1,118 miles per hour. Because of these winds, Saturn's cloud patterns are dynamic and ever-changing, much like the planet's atmosphere. The mysterious hexagonal storm that encircles Saturn's north pole stands out and lingers for quite some time in Saturn's weather. This long-lived hexagon has larger sides than Earth's diameter and has been in existence for at least a century. Current thinking sees it as an atmospheric standing wave pattern, but scientists are still attempting to nail it down precisely. The hexagon is unlike anything else in our solar system, with its jagged edges and spinning huge storm system demonstrating the extraordinary weather phenomena that may occur on gas giants. Superstorms, like as Saturn's hexagonal storm, may be hundreds of kilometers wide and include lightning bolts that are 10 times stronger than Earth's. Observable from space, these intense storms may alter Earth's atmosphere in mysterious ways before fading away for years. The weather on Saturn follows a similar pattern to Earth's because the planet's interior heat reacts with solar light. Complex weather systems are formed as a result of these interactions. Even in the absence of a solid surface, they create an environment that is active and turbulent. Examining Saturn's weather patterns teaches astronomers a lot about the inner workings of the atmosphere on Earth and other gas giants and exoplanets, environment on planets outside of our solar system and other gas giants. As astronomers continue to study and observe Saturn, we are learning more about the gas giant's intricate and beautiful weather cycles. Saturn, with its mesmerizing rings and enigmatic atmosphere, is one of the most fascinating subjects in the quest to comprehend the myriad of environments and conditions that exist beyond our home planet. Saturn's magnetic field, although not as strong as Jupiter's, has a substantial impact on Saturn's space environment. The rapid rotation of Saturn's metallic hydrogen core generates this immense magnetic field, which encases the planet in a magnetic bubble known as a magnetosphere. The solar wind is a stream of charged particles that originates from the Sun. Saturn's magnetic barrier shields it from this wind. The northern and southern lights of Earth, or auroras, are created by Saturn's magnetic field and are among the most interesting occurrences. These breathtaking spectacles are caused by charged particles from the solar wind being guided towards the poles by lines of a planet's magnetic field. As they collide with atoms and molecules in the upper atmosphere, they release energy in the form of light. The auroras on Saturn, however, aren't only visible to the human eye. Their powerful UV and infrared radiation makes them interesting to astronomers. Unlike Earth's auroras, which usually remain within a relatively small radius of the polar regions, Saturn's auroras may sometimes reach great distances, engulfing the whole pole. These hypnotic light shows don't happen all the time. Its intensity changes depending on the Sun's activity and Saturn's atmospheric conditions. Saturnian auroras are the result of a complex and dynamic interaction between the solar wind and Saturn's magnetic field. Astronomers may be able to learn more about Saturn's atmosphere, magnetic field, and place in the solar system by studying its auroras. In addition, it compares auroral processes, including Earth's, on several planets. Observing the aurora borealis and the Saturnian magnetic field is about more than simply looking cool. They represent how our solar system is dynamic and interdependent. As our space research activities continue, the mysteries of Saturn's magnetic field and the beauty of its auroras are continual reminders of the infinite wonders waiting to be discovered in the expanse of space. Saturn, the gem in our solar system, conducts a spectacular round around the Sun, completing its rotation around the Sun at about 29.5 Earth years intervals. As you travel through space, you'll observe the seasons and the passage of time in a way that's hard to fathom here on Earth. The rapid orbit of Saturn is essential to its everyday existence. One of the fastest spinning speeds in our solar system is Saturn's 7-hour cycle. The oblate form of the planet is mostly due to its fast rotation, which alters its overall appearance. Saturn is much flatter in the poles and bulged at the equator due to its rapid rotation and long orbit, which enables the gas giant to exhibit complicated seasonal changes. Seasons on Saturn last longer than 7 Earth years due to the polarity of the planet's axial tilt as it rounds the Sun. These longer seasons alter more than only the weather and atmospheric events, but from Earth, we can observe the planet's famed rings. Also, the way the Sun reflects off Saturn's rings changes considerably as the planet travels around its orbit. During the equinoxes, Saturn's rings cast a barely perceptible shadow on Earth due to their proximity to the Sun. Alternatively, the solstices highlight the tilt of the rings, revealing their whole magnificence in a breathtaking celestial beauty exhibition. Even the most furthest planets undergo changes and cycles that resemble, if not precisely match, the ones we see here on Earth. This fact is not lost on astronomers and scientists. These seasonal fluctuations are both interesting and a reminder of how big and dynamic our universe is. Nonetheless, the changing seasons on Saturn serve as a stark reminder of the vastness of space and the complexity of planetary systems as a result of these factors. We will continue to study Saturn's orbit, rotation, and the resulting seasonal variations, since they teach us a lot about gas giants and the solar system overall. Our understanding of the complex universe we inhabit deepens as we decipher the riddle surrounding our magnificent planet with each fresh observation and nugget of data. Beyond their role as mere clocks, Saturn's orbit and spin function as a cosmic thread. Their hypnotic interplay of light and shadow is evidence of the universe's dynamic character. Observing Saturn is similar to peeping through a cosmic seasonal spectacle that beyond anything we can observe from Earth. Discovering more and more about the gas giant Saturn via a series of groundbreaking missions has been one of the most exciting eras in space exploration history. The exploration of Saturn began with the flybys of Voyager 1 and 11 in the late 1970s and early 1980s. Through these trips, humans were able to capture the first ever up-close images of Saturn, its moons, and rings. The Cassini-Huygens mission, one of the most audacious and successful space exploration undertakings ever, was made possible by these preparatory trips. With the Huygens probe on board, Cassini began its journey to Saturn in 1997 and finally arrived in 2004. With the Huygens probe on board, the Cassini spacecraft sailed over 7 years until it arrived at Saturn in 2004. Cassini set out to investigate Saturn, its moons and rings in a way never done before. Cassini, during its 13-year orbit around Saturn, made a wealth of findings that have changed the way we understand the massive planet, its complex ring system, and its many moons. One of Cassini's crowning achievements was the 2005 landing of Saturn's largest moon, Titan, on the moon's surface by the Huygens spacecraft. Huygens sent images and data as it descended and touched down, depicting a world encased in a dense nitrogen atmosphere with lakes, rivers, and seas comprised of liquid ethane and methane. Understanding Titan's present status will depend on the data collected from this historic visit, the first of its kind in the outer solar system. In addition to discovering new rings and illuminating these interactions, Cassini also demonstrated the dynamic structure of Saturn's rings and the intricate relationships between them and the moons. Plumes of water expelled from the south pole of Enceladus were among the geologically active features discovered by the mission. This could point to the presence of an ocean under the moon's surface that is habitable. The mission's dramatic finale, Cassini's 2017 descent into Saturn's atmosphere, aimed to save the Saturnian moons from contamination, preserving their pristine ecosystems for possible future exploration. This tragic Cassini mission finale demonstrated the need of responsible exploration and the extent scientists would go to guarantee that future worlds may stay habitable. The work of Cassini and earlier missions serves as a springboard for future discoveries. International teams of scientists and engineers are hard at work organizing future trips to Saturn and its moons in an effort to fill the numerous gaps left by Cassini's exploration of the Saturnian system. Future space missions will aim to learn more about Saturn's atmosphere, the makeup and history of its rings, and whether or not moons like Titan and Enceladus are habitable. Every new mission to Saturn adds to our knowledge of this magnificent planet, which in turn sheds light on the inner workings of our solar system and the possibility of life in cosmos beyond our own. The discovery of Saturn highlights the infinite human curiosity to understand more about the cosmos. Understanding Saturn's unique role in our solar system is crucial as we delve further into its mysteries. The planetary system. Saturn plays a significant role in the solar system planetary symphony because of its complex ring structure, many moons, and immense gravitational attraction. First, asteroids and comets in our solar system are guided by Saturn's gravitational field. Because it has the potential to redirect potentially dangerous objects from the inner solar system, where Earth is situated, this gravitational force is vital to Earth's defense. Similarly, Jupiter and Saturn collaborate to prevent minor asteroid belt objects from either colliding with Earth or scattering too far, so preventing potential harm to Earth and other planets. Not only are Saturn's rings beautiful to look at, but they also reveal some interesting things about how planetary ring systems work. The icy and rock rings provide light on the solar system's primordial disk, which astronomers believe is responsible for the formation of the planets. A closer look at Saturn's rings might provide light on how the solar system and planets came to be. Titan and Enceladus, two of Saturn's moons, have also changed the way we think about possible homes for life beyond Earth. Titan raises questions about our assumptions about habitability due to its thick atmosphere and liquid hydrocarbon lakes, which show that circumstances favorable to life may exist in forms distinct from Earth. Enceladus, with its subterranean ocean and water released into space by geysers, provides compelling evidence for the possibility of life on icy worlds. The search for extraterrestrial life, known as astrobiology, would benefit from further exploration of these moons. Saturn is an excellent natural laboratory for studies of the atmosphere because of its complex dynamics, peculiar hexagonal jet stream close to its north pole, and intense storms. These events provide information on the dynamics of fluids and weather patterns, as well as the solar system and its gas giants. Last but not least, Saturn is more than just a heavenly jewel. We get a deeper understanding of planetary science, celestial mechanics, and the potential for extraterrestrial life from this crucial part of our solar system. As our knowledge of it grows, our perspectives broaden, and our comprehension of the universe and our place in it develops. The more we study and explore this incredible planet, the more we may hope to understand its inner workings and, by extension, the intricate structure of our solar system and beyond. Saturn, with its plethora of moons and rings, are a cosmic mystery that compels us to seek out more information about the cosmos. Saturn, the gas giant that has long captivated dreamers and astrologers, stands as a stark reminder of the immense beauty and complexity of our solar system as we complete our last orbit around it. Saturn, with its unique rings and plenty of moons, represents the boundless wonders that lie beyond our solar system. Glowing bands of ice and rock encircle this amazing planet, which not only offers a stunning glimpse of nature but also serves as a valuable study tool in understanding the inner workings of our solar system. We now know more about how planets evolve, how ring systems work, and whether or not very alien settings might support life thanks to studies of Saturn and its moons. Future generations of scientists and explorers will never forget Cassini-Huygens and similar expeditions. We are filled with awe as we gaze above, scrutinize what we see, and persistently pursue answers. Exploring the depths of Saturn's atmosphere, Titan's methane lakes, and Enceladus's ice geysers are just a few examples of the planets whose mysteries need more exploration. In the face of what is ahead, may the wonder that Saturn bestows stay with us. Our planet's vastness and magnificence serve as a constant reminder of the boundless possibilities in the cosmos. It motivates us to go for the stars, push ourselves to our limitations, and never give up on finding the answers that will define our species. Going to Saturn is more than just going on an outer space adventure. It's a journey through the infinite potential of human imagination and wonder. Without your assistance, we could not have made it to Saturn, the gem in our solar system. May you be captivated by the enigmatic workings of the universe and driven by an unquenchable need for understanding our place in it. Your time is much appreciated. As long as our need for knowledge remains unquenchable, the mysteries and marvels of our enormous universe will never cease to astound us. From the warmth of the sun, set sail on a magical journey to Uranus, the frigid seventh planet in our solar system, planetary system. Although its larger neighbors get all the attention, Uranus has a unique place in our solar system as the ice giant. This name is fitting given the planet's mostly frozen atmosphere and material composition. An enchanting example of the diversity and beauty of the solar system is Uranus, with its hypnotic blue-green hue. In 1781, the first planet to be discovered with a telescope was Uranus, which was made famous by William Herschel. Our astronomical ideas were put to the test, and the boundaries of our solar system were expanded by this revelation. Scientists have long been perplexed by Uranus's atmospheric conditions, weather patterns, and seasonal fluctuations, all of which are impacted by the planet's lack of an axial tilt. Uranus is a world of extreme cold, peculiar features, and unanswered questions, and we are about to explore it. With its peculiar axial tilt, faint ring system, and intriguing moons, Uranus is an enthralling and educational planetary body. The stars reveal the complex beauty of the cosmos beyond our solar system, so come along on our journey to this ice monster. Uranus is notable in our solar system for more than just its unique features. The planet also has deep historical significance in the field of astronomy. Uranus was the first planet to be found using a telescope, which had just begun to transform our view of the night sky a century earlier. William Herschel, a German-born British astronomer, made the discovery on March 13, 1781. When Herschel made his discovery, it was the first of its kind in modern times. It also presented a formidable obstacle to how humans had previously conceptualized our place in the cosmos. Closer examination dispelled Herschel's first suspicion that he had discovered a comet. This new planet was located far outside of Saturn's orbit. Discovering Uranus overnight doubled the known solar system's size, ushered in a new era of space study, and proved the power of technology and human curiosity. Choosing a name from Roman mythology for Uranus was unconventional. A planet named Georgium Sidus, which translates to George's star, was first proposed by Herschel as a tribute to his patron, King George III of Great Britain. However, outside of Britain, this name failed to get any attention. The name Uranus was bestowed by Johann Elert Bode in homage to the ancient Greek sky god Uranus, who was the grandfather of Zeus, Roman Jupiter, and the father of Cronus, Roman Saturn. This choice, which drew attention to the planet's standing among the ancient deities of the pantheon, was eventually recognized globally and perpetuated the custom of naming celestial bodies after their respective gods. The discovery of Uranus and the related name debate marked a turning moment in astronomy history and provided light on the global conversation that shapes our understanding of the universe and the collaborative nature of scientific discovery. The oddities and distant orbit of Uranus serve as a continual reminder of the ravenous human desire to understand the universe, intrigue that compels individuals to seek more understanding. Among the many planets in our solar system, Uranus stands out as a unique and intriguing world. It is the seventh planet in our solar system, and a stately one at that, taking around 84 Earth years to complete one full orbit around the Sun. In addition to its slow motion through space, Uranus stands out from the other planets in our solar system due to its extraordinary spin. Unlike every other planet in our solar system, Uranus rotates on its side. With an axial tilt of around 98 degrees, Uranus gradually exposes its poles to the Sun as it travels around the solar system, resulting in the harshest seasons. Due to its peculiar direction, the Sun either entirely illuminates or obscures large portions of the Earth for extended periods of time. Since its discovery, astronomers and scientists have struggled to make sense of its peculiar rotation. It is believed that a chain reaction of collisions or a tremendous impact with an object of the size of Earth caused Uranus to begin its present tilted orbit early in its history. This tilt has far-reaching ramifications for the planet's magnetic field generating process, as well as its temperature and atmosphere. So, the seasons on Uranus are totally different from the ones we experience on Earth. Around 42 Earth years of non-stop brightness and the equivalent amount of darkness follow at each pole. Our current knowledge of these impacts on Earth's atmosphere and weather patterns is incomplete because of the small sample sizes of these phenomena. The orbit and spin of Uranus demonstrate the dynamic diversity of the planets in our solar system and serve as a reminder of their violent and tumultuous past. As it makes its way around the Sun, Uranus serves as a continual reminder of the complexities and mysteries that envelop our understanding of the universe. We are encouraged to think about the cosmic forces that show up in the planetary behavior and motion as we study Uranus's orbit and spin. Since Uranus is slanted toward the Sun, it compels us to question our presumptions and delve deeper into the mysteries of our solar system. The ice giant Uranus is one of the most intriguing planets to study because of its mysterious makeup and atmosphere. Unlike the rocky terrestrial planets and gas giants like Jupiter and Saturn, Uranus stands out in our solar system with its odd blend of gases, ices, and even an interior ocean. Most of Uranus's atmosphere consists of the lightest and most abundant elements in the universe, hydrogen and helium. But Uranus's characteristic blue-green hue is caused by the presence of methane gas. Methane in the planet's upper atmosphere absorbs the red light from the Sun and reflects it back to Earth, giving the planet its distinctive blue-green hue. After this layer of methane is removed, the atmosphere of Uranus becomes denser and colder, cools down and thickens. While Uranus isn't the furthest distant planet from the Sun, it does have some of the lowest temperatures, with potential dips of 224–371 degrees. The unusual ice sheets seen on ice giants are partly generated by the very cold conditions that also aid in solidifying other hydrocarbons, like as water and ammonia, that have been compressed to extremely high pressures. Because of its peculiar form and composition, Uranus challenges the traditional notion of what a planet is. The myriad of heavenly bodies that round our Sun, each with its own unique characteristics and mysteries, are powerfully shown by this item. Our knowledge of the ice giants is enhanced by investigations into Uranus's atmosphere and composition, which also provide light on the creation of planets and the potential for life in hostile conditions. As we continue to gaze upwards, Uranus illuminates the sky and motivates us to get a deeper understanding of the vast, frigid solar system. There may be a solution to the age-old mystery of our place in the universe hidden in this planet's makeup and atmosphere, which might lead to a better knowledge of the outer planets. One outstanding feature in the wide solar system is Uranus's elaborate and enigmatic rings. We were wrong about Saturn being the sole planet having rings. The discovery of these rings in 1977 proved it. Uranus's complex ring system is intriguing, albeit less striking, than Saturn's. Originating from the fragmentation of moons that formerly circled Uranus, the rings of the planet are made up of black particles, with sizes varying from micrometers to several meters. Many people think they're brand new. The stark contrast between Saturn's dark color and the icy brightness of its rings suggests a possible distinct composition or maybe a covering of cosmic dust. 13 recognized rings surround Uranus. Each ring is named after a literary character from Shakespearean or Popean literature. The rings are of varying sizes and intensities, with the epsilon ring being particularly noticeable. The thin and faint rings of Uranus, in contrast to the wide and reflective rings of Saturn, can only be seen with the help of large telescopes or spacecraft flybys. About flybys by spacecraft or massive telescopes. The rings of Uranus were unintentionally found when the planet was seen to obstruct a distant star. The star's brightness seemed to momentarily dim both before and after Uranus passed in front of it, since the planet's rings obstruct a portion of the star's light. New insights into the cosmos were highlighted by this method of discovery. We can't help but speculate about the rings' origins and how they evolved throughout time due to their structure and content. Whether the rings around Uranus are brand new structures or the shattered remains of moons from past encounters is a mystery to astronomers. Much debate and investigation has focused on the mechanisms that constrained the ring particles to such narrow bands, as well as their exact properties. Researching Uranus's rings is a once-in-a-lifetime chance to get insight into planetary ring systems and their role in the formation of our solar system. These enigmatic formations may hold the key to unlocking the mysteries of how planetary entities arise and perish in the universe. The 1986 flyby by Voyager 2, the only spacecraft to have visited Uranus, provided vital data, yet much remains unclear about the rings. If future spacecraft are able to investigate Uranus, we may have a better understanding of the components that compose its rings, and the processes that cause them to form their intricate patterns. The rings of Uranus serve as a continual visual reminder to planetary scientists of the diversity and complexity of the other planets in our solar system. They beckon us to explore the depths, to go beyond our current understanding, and to discover the stories that lay beneath. The rings of Uranus are a constant reminder that, no matter how far we go across space and time, the most minute of connections may sometimes lead to the most profound insights. One of the most intriguing aspects of Uranus is its magnetic field, which is not seen on any other planet. In contrast to Earth, whose magnetic field is almost perpendicular to the rotational axis, Uranus stands out. Its magnetic field is surprisingly angled at a 60-degree angle relative to its spinning axis. Also, the epicenter of the planet's magnetic field is not in exact alignment with the planet's true center. In fact, it is about a third of the planet's radius away. And very imbalanced magnetic field and a complex, uneven magnetosphere are the end results of this strange configuration. This slanted magnetosphere causes Uranus's magnetic field to rapidly change in both intensity and direction as the planet clumsily round the Sun. Due to its peculiar magnetic arrangement, Uranus does not get auroras as often as Jupiter and Earth. However, when they do emerge, they reveal the complexity and dynamic nature of the planet's magnetic environment. The origin of Uranus's peculiar magnetic field remains a mystery to scientists who are actively seeking answers. According to academics, the unusual feature might be caused by the structure of Uranus. They postulate that action in the planet's frozen mantle, rather than the core, might generate the magnetic field. In light of this new information, the long-held belief that planetary magnetic fields are generated by the movement of molten metal inside the planet's core is no longer supported. The mysteries surrounding the magnetic phenomena of ice giant Uranus and other celestial bodies, such exoplanets in other solar systems, can only be solved with knowledge of Uranus's magnetic field. Studying Uranus's magnetosphere helps fill gaps in our understanding of planetary science and the universe by revealing the diversity of planetary magnetic fields. The enigmatic nature of Uranus's magnetic field serves as a continual reminder that our solar system is brimming with secrets, a reality that is further solidified by our continuous discovery and investigation of the planet. We need further missions to Uranus to analyze its complex magnetic field and learn about the ice giants and beyond. And this discovery lends credence to that notion. It has been a significant but solitary endeavor to learn more about Uranus, the eighth planet from the Sun. The only spacecraft to ever fly by Uranus, the Voyager 2 launched by NASA in 1977, has provided a fleeting glimpse of the ice giant's mysteries. In January 1986, at Voyager 2's closest approach to Uranus, scientists were able to uncover long-hidden details about the planet. Voyager 2 increased the number of known moons of Uranus to 15 during this historic visit by adding 10 additional moons to the planet's orbit. The complex system of weak rings that round the planet was another little-known element prior to the meeting. Contrasted with Saturn's bright ice rings, these dark particle rings provide a new perspective on ring dynamics around gas giants. The blue-green hue that Voyager 2's instruments captured on Uranus is a result of methane absorption of red light and reflection of blue light from the Sun back into space. By measuring its temperature, the probe also verified that Uranus has one of the solar system's coldest atmospheres. Voyager 2's most intriguing finding was that Uranus's magnetic field was 59 degrees angled away from the planet's rotation axis, which meant it was displaced from the planet's core. This unusual magnetic configuration causes auroras, which are complex and ever-changing phenomena that are quite different from Earth's auroras. Even though Voyager 2 collected an abundance of data, the mission nevertheless could not resolve all of our doubts. Our brief encounter with Uranus taught us virtually little about the dwarf planet's innards, its climate, or the composition of its moons. Clearly, further research is required. More astronomical and scientific missions to Uranus are urgently needed to shed light on this baffling planet. Proposed missions seek to conduct more in-depth investigations of the planet's atmosphere, interior, rings, and moons in order to get a deeper understanding of the processes that regulate the weather, the characteristics of the planet's magnetic field, and the moon's geological past. On the cusp of new revelations, Uranus, as a boundary of secrets yet to be revealed, calls out to us. Uranus investigation has limitless potential for future discoveries about this enigmatic ice giant. Investigating its secrets may provide light on the origins and development of our solar system and Uranus in particular. Understanding the formation and evolution of planetary systems is a key goal of Uranus study. As an ice giant, Uranus provides a unique window into the early solar system's formation. Uranus, one of the icy giants, provides a unique window into the cosmic processes that shaped our solar system many, many years ago. The planetary scientists still don't know what causes Uranus to have such a high axial tilt. Uranus spins counterclockwise to the rest of the planets, which spin horizontally on their axes. Many theories have been proposed to account for this unusual orientation, including strong formation phase collisions and gravitational interactions with neighboring stars. Investigating Uranus's interior structure reveals yet another intriguing enigma. Scientists think it contains a rocky core under its thick atmosphere and ice mantle, but we don't know its exact composition or features. Investigating Uranus might provide valuable information on the formation and development of ice giants, which could shed light on their role in shaping the diversity of planetary systems. Another intriguing aspect is the possibility of an ocean under the frozen surface of Uranus. If this subterranean ocean is really habitable, it may hold strange life forms or provide light on what it takes to make other planets habitable. You may learn a lot about the existence and behavior of this ocean by studying the magnetic field, auroral activity, and interactions of Uranus with its moons. Among the solar system's planets, Uranus has received the least amount of exploration, even after the historic 1986 encounter by Voyager 2. The mysterious axial tilt, internal structure, and possibility of life on Uranus are just a few of the mysteries that may be solved by future space probes. Understanding planetary creation, development, and the cosmic forces that govern our world is enhanced by delving into the secrets of Uranus. As we keep looking into space, Uranus is a reminder of how inventive and inquisitive humans can be. Its mysteries spread throughout the universe, beckoning us to probe its depths and learn everything there is to know about it. Our expedition to the frozen interior of Uranus has left us with an insatiable need for knowledge about this mysterious world and its role in the universe. Uranus, with its frozen atmosphere, rings, and moons, as well as its unusual axial tilt, presents a formidable challenge to our current knowledge of planetary science and an invitation to explore the solar system's hidden secrets further. Even though Uranus is far away and icy, it is crucial to our understanding of how planetary systems formed and evolved. Planet Uranus can teach us a lot about the cosmic processes that molded Earth and the other planets in our solar system. Its complex magnetic field and severe axial tilt are two of its most distinctive features, and they provide important insights into the formation of life and the dynamics of planetary bodies. Uranus is still a mostly uncharted globe with incalculable mysteries, despite the abundance of information gathered from the Voyager 2 visit and following studies. The origin of its rings and the nature of its interior are two of its many mysteries, which will hopefully be solved by the explorers and scientists of the future. Let us not let go of the adventurous spirit that propels us to seek out the unknown as we say goodbye to Uranus. The cosmos is a place of wonder and amazement. Let us not stop exploring it, learning more, and expanding our horizons. We appreciate you coming along as we visit the ice giant on the outside of our solar system, Uranus. The endless possibilities that exist outside our ken are boundless, and may the enigmas of this faraway planet encourage us to keep seeking them out. Much obliged for your time. Keep asking questions, keep looking for answers, and never cease being amazed by the cosmos we live in. Neptune, a planet cloaked in azure mystery and raging winds, is our destination today as we set sail on our cosmic adventure. Neptune, which is far from the Sun, stands sentry over the farthest reaches of our solar system, a reminder of how enormous and incredible our cosmos is. Come explore this faraway planet with us as we uncover its mysteries. from how it was found in the night sky to the incredible events that cause waves in its ice-blue atmosphere. The tale of Neptune, the most windy planet in our solar system, will enthrall you as you see the mesmerizing dance of gases and ice that creates an ethereal tableau. This mysterious behemoth is a wonder of our solar system. Therefore, let's start investigating it. The fact that Neptune is the 8th planet in our solar system is proof of how incredible our solar system is. The windiest planet is a fitting moniker for Neptune, a celestial body known for its vibrant blue hue and some of the solar system's most powerful winds. Neptune is unique among planets in that it was the first to be found and cannot be seen by the human eye. This finding demonstrates the strength of human imagination and curiosity by illuminating a universe beyond our immediate sensory perception via mathematical forecasts, ratheth, and first-hand observation. Neptune's composition is hinted at by its oceanic blue tint, which is more than simply an attractive surface feature. The main reason Neptune appears blue is because the gas methane in its atmosphere absorbs red light and reflects back the blue light, giving the planet its distinctive hue. With its ever-changing weather patterns and lightning-fast clouds, Neptune is a beautiful and mysterious planet that begs us to explore its furthest reaches. An important turning point in the history of astronomy occurred in the middle of the 19th century when the concept of Neptune was brought to life via mathematical calculations. Its finding did not occur by chance when peering through a telescope. It was really the result of the separate but complementary efforts of two very gifted astronomers, Urbain Le Verrier of France and John Couch Adams of Britain. In addition to the gravitational attraction of the known planets, both men had seen anomalies in Uranus's orbit that defied explanation. They located a previously undiscovered planet by painstakingly calculating its location. People were racing to be the first to see this anticipated planet. Johann Galle, at the Berlin Observatory on September 23, 1846, exactly where Le Verrier had said it would be, was given the distinction of being the first to see it. Significantly, this finding demonstrated the efficacy of predictive mathematics in astronomy and provided strong support for Newton's law of universal gravitation. The job of giving the newly discovered planet a name came up soon after its discovery. It was called Neptune, after the Roman deity of the sea, in accordance with the practice of naming planets after Roman deities. The planet's name seemed appropriate for a number of reasons, including its oceanic blue hue and a reference to Neptune's enigmatic and potent character. We learned more about the size and rules of the solar system with the discovery of Neptune, which marked a turning point in scientific history by bringing together theoretical physics and empirical astronomy. An incredible one. 64. 8 Earth years pass when Neptune, the faraway guardian of our solar system, sets off on its grand round around the Sun. This extensive journey proves that it is the 8th planet from our star. Located in the frigid, black expanse of space, Neptune's orbit, which averages about 5 billion kilometers, or 8 billion miles from the Sun, illustrates the immense area beyond the inner planets and the breadth of our solar system. An intriguing characteristic of planetary motion is shown by Neptune as it travels on its elliptical course. In Neptunian time, 1 day, or 16 hours, Neptune completes one full revolution on its axis, regardless of its distance. This object provides a fresh angle on the variety of planetary habitats in our cosmic vicinity due to its fast spin and long orbital period. Beyond its massive size, Neptune's orbit has far-reaching consequences for the planet's weather, atmospheric dynamics, and maybe even its internal geological and magnetic phenomena. Sunlight is quite dim because of the great distance from the Sun. It is not nearly as bright or warm as what we experience on Earth. The frozen surface of Neptune and the intricate dynamics inside its atmosphere are both shaped by this distance. Along its orbit, Neptune interacts with other gas giants and dances delicately with other celestial entities, most notably its biggest moon Triton. For generations, astronomers have been captivated by the complexities of Neptune's orbital dynamics, which are further complicated by these connections, which include nuanced variations and resonances. The enormity and intricacy of the cosmos are brought to light when we consider Neptune's orbit. In its long, arduous orbit around the Sun, this faraway planet exemplifies the tenacity and perseverance of nature. As we investigate Neptune's role in the cosmic ballet, we learn more about the planet and its people, and develop a greater respect for the countless other worlds in our solar system, each with its own history and mysteries just waiting to be unearthed. As a gas giant cloaked in mystery and subject to harsh weather, Neptune's magnetism stems from more than simply its distance from Earth. There is a composition near Neptune's core that resists easy classification. At first look, this planet may be mistaken for a gigantic ice ball drifting aimlessly across space. However, this is only a superficial overview of everything Neptune stands for. Neptune and Uranus are both ice giants with compositions close to hydrogen, helium, and a trace amount of methane. But Neptune's hue is what really stands out. Any observer is captivated by the deep, hypnotic blue that envelops the globe. Its atmospheric chemistry causes this, not some subjective issue of taste. Gaseous methane from Neptune's upper atmosphere is crucial to this process. What gives Neptune its distinctive color is its ability to soak up the sun's red radiation while reflecting its blue light back into space. In the vastness of space, this hue serves as a unique identifier for Neptune. As one delves more into Neptune's physical features, a universe of extremes becomes apparent. It is the fourth biggest planet in our solar system due to its size, which measures around 49,744 kilometers in diameter. Even though it is far from the Sun and very small, Neptune produces an astonishing quantity of heat. We still don't completely comprehend the planet's inner workings, but we do know that it emits around 61 times as much energy as it gets from the Sun. The magnetic field of Neptune further complicates the already complicated nature of the planet. At least 55 radii out from the planet's actual core, it is slanted 47 degrees in relation to its axis of rotation. An odd magnetic alignment like this might be the result of a dynamo effect on Neptune's interior, where the magnetic field is created by the motion of conductive materials. Scientists find this feature of Neptune fascinating, and it also shows that the planet's interior is far from being a static ball of ice and gas. Everything about Neptune, its composition, color, heat emission, and magnetic field, offers a window into the complexity of planetary science, and the planet itself is a monument to the variety and magnificence of our solar system. As we continue our journey to comprehend the cosmic marvels, Neptune urges us to see beyond the surface, to explore its secrets further, and to keep looking for answers. The whirling blue canvas of Neptune's atmosphere conceals a stormy nature behind its peaceful look, making it one of the most fascinating and active solar system atmospheres. The methane that Neptune contains gives it its mesmerizing blue color by absorbing red light and releasing blue light into space. The other components of the gaseous planet include hydrogen, helium, and trace amounts of other elements. However, there is often an element of extreme beauty in the universe. When compared to all other planets, Neptune has the most violent weather. When compared to all other planets, Neptune has the most violent weather. Extremely high winds, exceeding 2,000 kilometers per hour, roar across this area. Extremely fast, the quickest planet in the solar system, make the strongest storm ever seen on Earth even stronger and faster than it already is. A typical day on Neptune looks like that. The Great Dark Spot sits in the heart of Neptune's planetary atmosphere. During its historic 1989 flyby, Voyager 2 caught sight of a gigantic storm on Neptune that resembled Jupiter's Great Red Spot, but with a peculiar twist. The storm was about the size of Earth. The planet's ever-changing weather patterns are on full display as the winds on the edge of this black anticyclonic storm whip around at incredible speeds. Nevertheless, storms on Neptune do not last forever. After a few years of using the Hubble Space Telescope, scientists saw that the Great Dark Spot had disappeared. However, other storms had appeared in other parts of the world, proving that Earth's weather is always changing. Clouds at great heights add to Neptune's dramatic charm by obscuring the blue sky below. Clouds like this emerge from the frozen methane gas, which forms ice crystals that reflect the sun's rays in a dazzling display, providing a brief window into the intricate relationship between pressure and temperature on Neptune. The strange weather on Neptune is more than simply an interesting fact. It's a mystery that tests our knowledge of planetary atmospheres. Why do planets so distant from the Sun produce winds so much stronger than Earth's? They only get a small fraction of the Sun's heat. The planet's core temperature is the key. In contrast to Earth, where the weather is mostly dictated by the Sun, Neptune emits almost twice as much energy as it gets from the Sun. The planet's atmosphere is constantly shifting due to its interior heat, causing the winds and storms to dance in a beautiful but relentless ballet. Every new observation of Neptune from afar, whether from a spacecraft in transit or a telescope, fills in a little more of the picture. Planetary science and the dynamics of other worlds' atmospheres are both enhanced by research into Neptune's weather and atmosphere, which satisfies our natural interest about this faraway globe. Delving further into Neptune's secrets reveals its enchanting ring system that encircles the planet and its captivating assortment of moons. The 14 moons of Neptune have their own distinct personalities and secrets. The diamond in the crown, nevertheless, is Triton among these heavenly bodies. The biggest moon of Neptune, Triton, is a magnificent frozen landscape that never fails to captivate. Since Triton circles Neptune in a retrograde manner, it is believed that it was grabbed by the planet's gravity rather than produced in orbit around Neptune, unlike any other huge moon in our solar system. Made it to Neptune's orbit, but the gravity of the planet pulled it in. Surfacey temperatures on this fascinating moon dropped to -235 degrees Celsius, making it one of the solar system's coldest locations. Astonishingly, Triton's geologic activity is on full display in its geysers, which eject nitrogen ice and dust over 8 kilometers into the moon's thin atmosphere, despite the freezing climate. However, Triton isn't the only one doing a tango with Neptune. Proteus, Nereid, and Larissa are just a few of Neptune's numerous moons that add their own cosmic ballet tales to the intricate dynamics of the planet's gravitational embrace. Moons of varying sizes and compositions provide a rich tapestry of planets that provide light on the turbulent history of our solar system. Circumscribing this faraway planet, Neptune is adorned with a series of delicate rings. Neptune has more thinner and sparser rings than Saturn, which are made of a mixture of dust and ice. These rings are commemorated by astronomers Adams, Leverrier, Lasalle, and Gallet, who all made notable contributions to the study of Neptune. Arcs, which are out of the ordinary collections of dust and debris in the Adams ring, stand out because they don't spread out uniformly, suggesting intricate gravitational interactions. The enchanting rings and moons of Neptune beg scientists to uncover their mysteries, a testimony to the planet's irresistible charm. Intertwined, they form an ethereal symphony of movement and intrigue, unfolding in the vast, far-off regions of our solar system. The first and only close contact between humans to Neptune occurred during the historic flyby of Voyager 2 in 1989. This historic space mission yielded a plethora of data that revolutionized our knowledge of the faraway planet. Voyager 2 took breathtaking pictures of Neptune as it flew by the gas giant, revealing its complex ring system, varied moons, and most notably, the fascinating Triton, which was accompanied by active geysers and a retrograde orbit. Lots of time has passed since Voyager 2 visited Neptune, but it hasn't stopped scientists from studying and being fascinated by the planet. Astronomers may now stare at Neptune from afar using space telescopes and ground-based telescopes outfitted with adaptive optics, thanks to technological breakthroughs. Through these studies, scientists have been able to get a better understanding of the planet's weather patterns, magnetic field, and intricate ring structure, as well as the atmospheric dynamics, such as the emergence and dissipation of storm systems. A new expedition to Neptune is being considered and discussed in the scientific community as a potential future endeavor. An orbiter and a probe to explore Neptune's atmosphere might be part of this daring mission. By conducting this expedition, our understanding of Neptune would be greatly expanded, allowing us to put to rest long-standing mysteries about the planet's interior structure, atmospheric dynamics, and enigmatic magnetic field. Triton, the biggest moon of Neptune, is also an attractive exploration target. Researchers are hopeful that Triton, which may have originated in the Kuiper Belt, may provide light on how our solar system evolved and how the outer solar system came to be. Geysers and surface composition studies on this frozen body may also provide light on cryovolcanism and the possibility of seas under the surface. Neptune continues to represent the enormous mysteries of our cosmos, even as we teeter on the edge of new understandings. The more we learn about this faraway planet, the more we understand about the solar system's periphery, and the more motivated we are to seek out other, as yet undiscovered worlds in space. Neptune is the most mysterious and beautiful planet in our solar system, and it shines out as we near the conclusion of our voyage through the icy furthest regions. Symbolic of the unexplored horizons beyond our present reach, Neptune captivates our imaginations with its rich blue colors and strong supersonic winds that rush over its atmosphere. Mathematical predictions and the unquenchable human curiosity drove the investigation and discovery of Neptune, highlighting our relentless pursuit of cosmic knowledge. We are becoming more and more fascinated with the frozen behemoth Neptune, despite the enormous distances that divide us from it. The data collected by Voyager 2 during its historic flyby in 1989 opened us a world of possibilities. It showed us a planet full of interesting moons, weather systems that are always changing, and faint rings that make us question how planets create and evolve. Let us consider Neptune's role in space exploration in the larger perspective as we wrap up. The immensity of space and the infinity of uncharted potential are both echoed in its enormity. The enigmas of Neptune inspire both realists and idealists to keep exploring, expanding our horizons, and understanding the world around us. Exploring Neptune and the solar system's outer regions is more than simply a space adventure. It's a voyage through humankind's boundless curiosity and inventiveness. I appreciate you coming along on this journey of Neptune with me. As we keep looking up at the stars, let us not forget that they are more than simply points of light. They are portals to other universes that beg us to explore, study, and imagine. Keep asking questions and looking for answers. The cosmos is big and wonderful, and we never know what mysteries lie beyond its horizons. What mysteries lie beyond the gorgeous, expansive cosmos that we will soon unravel? Pluto, the former 9th planet in our solar system, awaits discovery at the furthest frontier of our planetary system. This dwarf planet is located in the Kuiper Belt, a chilly and mysterious space system beyond Neptune. Pluto, the enigmatic cold ball at the edge of our heavenly neighborhood, served as the last guardian planet for many years. The reclassification of Pluto to dwarf planet in 2006 has not dampened its fascination for astronomers, scientists, and space fans. By providing insight into the early solar system via its complicated surface, fascinating moons, and unusual location, it challenges our assumptions and deepens our knowledge of planets. Before we set sail on our exploration, let's learn about Pluto, its background, personality, and everlasting charm. This faraway planet, despite its little size, occupies a colossal position in our imagination and our pursuit of knowledge. We will explore its history, from its contentious discovery to the revolutionary discoveries made by the New Horizons expedition. Come with us as we explore Pluto, a planet with a beating heart but no official designation, in search of its hidden mysteries. Inconsistencies in Neptune's and Uranus's orbits, which pointed to the gravitational pull of an invisible body, sparked the search for a 9th planet in the late 19th century. In search of this enigmatic planet, astronomers from all around the world pointed their telescopes upwards. At the Lowell Observatory in Flagstaff, Arizona, the hunt finally reached a spectacular end in 1930. A student astronomer by the name of Clyde Tombaugh saw a moving object while laboriously comparing photographic plates of the night sky. Nothing about this celestial body seemed typical. Its motion against the cosmic background indicated that it was distant. Worldwide, the news spread like wildfire. The new planet was officially named by the Lowell Observatory, which had begun the search in response to Percival Lowell's predictions. Pluto was the winner after extensive public input and lengthy debate. As befits a planet in the furthest corners of our solar system, the name was chosen to commemorate both the Roman deity of the underworld and Percival Lowell, whose initials are reflected in the first 2 letters of Pluto. The discovery of Pluto was a watershed moment in astronomy, bringing an end to the hunt for the ninth planet in our solar system and launching a new age of investigation beyond Neptune. This dwarf planet, barely larger than the Moon, captivated viewers all across the globe and served as a metaphor for the enormous, unexplored space in our cosmic backyard. Unknown regions of our cosmic backyard that have yet to be explored. Pluto is a mysterious and faraway planet located in the solar system's icy outer regions, much beyond Neptune's orbit. Pluto is an intriguing object that scientists are always curious in, and this section explores its composition, atmosphere, and dynamic environment. Large valleys, rough mountains, and expansive plains make up Pluto's surface terrain. Among its most remarkable characteristics are the soaring ice mountains, which may reach heights of several kilometers and are mostly made of water ice. The flat, broad plains of places like Sputnik Planitia, a huge ice field composed of nitrogen ice that is a portion of Pluto's famous heart-shaped area, stand in stark contrast to these snowy peaks. The tenuous atmosphere of the dwarf planet is mostly nitrogen with trace amounts of carbon monoxide and methane. The air pressure on Pluto fluctuates dramatically due to the planet's wildly fluctuating distance from the Sun as it revolves. Pluto experiences atmospheric thickening and the formation of a fleeting blue haze as its surface ice sublimates during its closest approach to the Sun. The atmosphere freezes and falls back to the surface as Pluto advances away, creating an endless loop of this process. One further thing that makes Pluto unique among the planets in our solar system is its orbit. Its path around the Sun is very elliptical, taking Pluto 248 years to complete one revolution, during which it may approach the Sun closer than Neptune and then recede to the solar system's farthest regions. Another feature that distinguishes Pluto is its peculiar trajectory, which is inclined at a 17-degree inclination to the ecliptic plane. Pluto may be little. Its diameter is just over 2,177 kilometers, but its gravity has ensnared 5 moons, the closest of which is Charon, so big that Pluto and Charon are sometimes thought of as a binary system. Even more nuanced aspects of Pluto's personality emerge from the existence and interplay of these moons. Pluto isn't the only celestial body making its way to the solar system's furthest limits. 5 moons, each with its own set of peculiarities and secrets, circle this faraway planet. Discovered in 1978, nearly 50 years after Pluto itself, Charon is the biggest and most well-known of these moons. A twin dwarf planet system describes the relationship between Pluto and Charon because of Charon's size in comparison to Pluto. Their mutual gravitational pull causes them to circle an object outside of each other, setting in motion an unusual and intriguing cosmic ballet. Hydra, Styx, Nix, and Kerberos are the 4 smaller moons beyond Charon. Discoveries of these moons occurred more recently. The Hubble Space Telescope was instrumental in the 2005 identification of Nix and Hydra, the 2011 discovery of Kerberos, and the 2012 discovery of Styx. Even though they are far smaller than Charon, with diameters ranging from 10 to 50 kilometers, they contribute much to our knowledge of the Pluto system. These smaller moons are believed to have a composition similar to Pluto's, consisting of water ice and rock. Their gravitational interaction with Pluto and Charon causes their orbits to be erratic, which in turn causes them to follow routes that defy our comprehension of astronomical physics. Understanding the past and present of the Pluto system is greatly aided by the discovery of these moons. They imply that, like the Earth-Moon system, Pluto and Charon may have originated as a result of a massive collision. A look into the dynamic and sometimes violent processes that form our solar system may be seen in the possibility that the smaller moons formed from debris that condensed from this tumultuous beginning. Research into Pluto and its satellites is yielding new insights into the dynamic forces at work at our solar system's periphery. Pluto is one of the most fascinating planets in our solar system, and these little moons play an important role in its history and character. Pluto is a faraway cold planet at the periphery of our solar system, and the voyage of the NASA spacecraft New Horizons, which departed on January 19, 2006, signifies a watershed moment in space research. Embarking on a 9-year journey across more than 3 billion miles to reach its main destination, New Horizons were sent into space aboard a rocket. the spacecraft started sending back to Earth the most comprehensive pictures and data ever taken of the dwarf planet as it got closer to Pluto in July 2015. This completely changed our perception of this faraway world. Norge Montes and Hillary Montes, named after the first people to summit Mount Everest, are towering mountains of water ice that were discovered during the flyby as part of the incredibly varied environment. These peaks, which may reach elevations of up to 11,000 feet above Pluto's surface, are indicative of recent volcanic activity. Discoveries like as the enormous heart-shaped plain Sputnik Planitia, a flat, brilliant region composed of frozen nitrogen, methane, and carbon monoxide, were among the most fascinating. Geologists in this area have pieced together clues about the planet's dynamic and complicated history, which point to a youthful surface warmed from inside and maybe an ocean underneath. Atmospheric evidence was also found by New Horizons. The thin atmosphere of Pluto, which is mostly nitrogen with tiny amounts of methane and carbon monoxide, freezes and returns to the surface as snow as the planet recedes from the sun. A dynamic and ever-changing atmosphere is created by the cycle of snowfall and evaporation. Not only did the expedition illuminate Pluto, but it also uncovered priceless information about its moons, most notably Charon, the biggest moon of Pluto. The topography of Charon is diverse, with canyons, mountains, and plains. Its north pole has a distinctive crimson hue, which is probably the result of organic molecules from tholin created when the sun's UV radiation hits methane in Charon's atmosphere. When the sun's UV rays strike the methane in Charon's atmosphere, Pluto flyby by New Horizons was only the beginning of our journey into the solar system. In order to learn more about how our solar system came to be, the spacecraft continued its voyage after its collision with Pluto into the Kuiper Belt, an area beyond Neptune that is home to frozen objects and dwarf planets. With its groundbreaking discoveries concerning the solar system's furthest regions and their implications for our knowledge of the universe, the New Horizons project is a monument to the inquisitiveness and resourcefulness of the human race. The eccentric path that Pluto has taken through the cosmic lexicon mirrors its orbit around the Sun. Its 1930 discovery made headlines as the solar system's ninth planet, a faraway frozen world that stood in stark contrast to the rocky and gaseous planets that orbited our star. The definition of a planet, however, has evolved in tandem with our knowledge of the universe. A problem with the stars arose in 2006 for the International Astronomical Union. The notion of a planet was put to the test as additional huge objects in the Kuiper Belt, an area beyond Neptune filled with ice bodies, were discovered. 3 criteria for planethood were established by the IAU to resolve this. In order to be considered a celestial body, an object must be round in form, a result of gravity, and free of debris in its orbit around the Sun. Pluto satisfies the first 2 conditions, but fails to fulfill the third. Not only does it share space with other ice objects in the Kuiper Belt, but its orbit also overlaps with Neptune's. The International Astronomical Union, IAU, categorized Pluto as a dwarf planet using these criteria, which caused a controversy that is still going on. Pluto, according to some astronomers, is an example of a complex planet with mountain ranges, huge plains, and indications of previous and potentially continuing geological activity. The IAU's definition, they say, is too limited and fails to take this complexity into account. Consideration of a planet's inherent qualities, in addition to its orbital dynamics, should be given more weight, according to their argument. Some people were upset over Pluto's reclassification because they felt a special connection to the planet they had known all their lives as the 9th planet in our solar system. The nature of planthood and the categorization system have been the subject of continuous studies and disputes because to this emotional link. Pluto, despite its demotion, is still fascinating both experts and the general public. Both experts and the general public are enthralled with Pluto. Even though it is now considered a dwarf planet, it doesn't mean it is any less important to our investigation of the solar system's inner workings. If anything, the ongoing discussion about Pluto's status has served to emphasize how science is a constantly expanding field, where definitions are always being tested and improved upon as our understanding and knowledge expand. The difference between Pluto being referred to be a planet and a dwarf planet may seem little in the vastness of the universe. However, the fundamental issues surrounding our ability to classify and comprehend the cosmos are raised by this dispute. Who knows what additional celestial bodies may pop out as we keep exploring the cosmos and beyond, testing our assumptions and broadening our cosmological perspective. The history of Pluto is an ode to the infinite curiosity of humans. It serves as a timely reminder that, just like in space, there is much more to learn about the universe. The reclassification and discovery of Pluto have impacted popular culture in ways that scientists and space enthusiasts could never have imagined. Pluto, formerly an ice world far away in the solar system, has become a symbol of perseverance and mystery, inspiring creative thinking and heated discussion for decades. A captivating introduction to the intricacies of our solar system, Pluto's narrative is a valuable tool in children's scientific education. It is a real-life illustration of how science is always altering depending on new findings, because textbooks formerly identified it as the eighth planet, but that status changed in 2006. Because of this change, students are more interested in learning about the components of a planet and how we classify the cosmos. Outside of the classroom, Pluto has been all over the literary and cultural landscapes, playing the role of the underappreciated planet that manages to hold its own against the more famous ones. The extent to which it has permeated popular culture is shown by the fact that its demoting to dwarf planet status has sparked protests, jokes, and cartoons. Aside from scientists, the public has been drawn into the discussion over Pluto's categorization, which has sparked a larger conversation about how celestial planets are classified and the emotional ties individuals have with them. Pluto is sometimes seen as a symbol of the underdog, a little planet in an expansive cosmos that still has great symbolic weight. As a result of this personal connection, people are still curious in Pluto and its potential mysteries, and they support trips to the planet. The cultural significance of Pluto is seen even in the naming conventions and jargon that surround it. Extending beyond Neptune in the Kuiper Belt, dwarf planets like as Pluto are now referred to as Plutoids. Locate in the Kuiper Belt beyond Neptune. This naming convention guarantees that Pluto will remain an important topic in future talks about our solar system and preserves its reputation among scientists. We are reminded of the limitless curiosity that propels mankind to seek the unknown as our voyage to the faraway and mysterious planet Pluto nears its end. Scientists, visionaries, and adventurers have all been captivated by Pluto, a little dot in the enormous universe. There has been no change to its importance in our pursuit of knowledge since it was downgraded to dwarf planet status. Not only has the New Horizons mission increased our knowledge of Pluto, but it has also piqued our interest in the solar system's furthest reaches and the enigmatic Kuiper Belt. More fascinating discoveries are sure to be made in the years to come. In order to discover what surprises lie below Pluto's frozen core, scientists are planning more missions to investigate the dwarf planet more thoroughly. We get closer to understanding the cosmos, how planets develop, and what conditions are required for life with each trip. The narrative of Pluto sheds light on the scientific method in a priceless way. Discoveries and arguments propel its constant evolution. As with few other subjects, the discussion around Pluto's categorization has roused people's interest in and participation in astronomy, serving as a reminder of the insatiable curiosity that drives human nature. Whether Pluto is described as a planet, a dwarf planet, or any other designation does not detract from its significance. It is proof that humans will never stop wondering about the universe and the mysteries it holds. Pluto continues to represent the unknowns that lie beyond our solar system's light, encouraging us to go on in our pursuit of understanding as we study the night sky and beyond. Let us then eagerly anticipate the future discoveries that lie ahead in the vast, unexplored regions of space as we wrap up our journey to Pluto. The saga of Pluto is but a little piece of the enormous puzzle that is the exploration of our cosmos, an undertaking that will enthrall and motivate future generations. As we near the end of our cosmic adventure, we are once again at the crossroads where curiosity meets knowledge. Discoveries about our heavenly neighbors have led us throughout the whole solar system, from Pluto's frozen plains to Mercury's scorching surface. However, there remains a great deal of uncharted territory in the cosmos. Think of this as the start of an even greater journey if the marvels we've shared today have enchanted you. We rely on your support to continue our cosmic adventure, so please like our post if you like it. Subscribing to Cosmic Crossroads will put you in the middle of the cosmos, where secrets lurk around every corner. The cosmos has now opened up new doors for you to discover. To continue your space adventure, click on the video that is next on the list of recommendations. Every click at Cosmic Crossroads leads to fresh discoveries, and the future holds miracles galore. At Cosmic Crossroads, the cosmos is always only a click away. So keep your eyes on the sky and your soul ready for adventure until our next astronomical expedition. Thank you for joining us. Here we are, embarking on a voyage across the annals of space and time. Discover the incredible stories that have molded the universe, beginning with the Big Bang and continuing into the far future. Come with us as we unravel the universe's amazing narrative by solving the riddles of space and time. The Big Bang, the cosmic explosion that started it all, is where our tale starts. Everything that came after was laid down in motion by the instantaneous creation of matter and energy. Cosmic microwave background radiation, which provides a window into the early cosmos, is one piece of strong evidence that scientists have found to support this notion. During the inflationary phase that followed the Big Bang, the cosmos expanded at a rate greater than the speed of light. At this period, the building blocks of matter began to take shape. The first atomic nuclei were formed when quarks fused to form protons and neutrons. Primordial nucleosynthesis was the process by which the first elements were formed when the cosmos cooled further. Stars and galaxies were constructed from the most basic components, hydrogen and helium. As they expanded throughout space, these luminous components paved the way for the next stage of the universe's history. After then, a time called the Dark Ages began in the cosmos. Since the first atoms hadn't formed yet, there was complete darkness at this period. The cosmos cooled down to a point where electrons could join protons to form neutral hydrogen atoms. A key piece of evidence supporting the Big Bang hypothesis, the cosmic microwave background radiation, was emitted as a result of this. The emergence of the first stars coincided with the waning of the Dark Ages. Population 3 stars were huge, very short-lived stars that were crucial in the nuclear fusion process that produced heavier materials. As a result of the light emitted by these stars, the first galaxies emerged and started to mold the cosmos. Massive star systems made out of gas and dark matter began to take shape and change over time. The formation and evolution of stars, gas, and dark matter began. They evolved into the wide variety of galaxies we see today as a result of mergers and interactions. These interactions gave rise to galaxy clusters, the biggest formations in the cosmos, and the cosmic web that characterizes the structure of the universe at massive scale. Invisible and enigmatic dark matter is essential to galaxy formation and development. The gravitational pull of dark matter is seen in the shifting of galaxy clusters and the rotation of individual galaxies, even though it is invisible to the naked eye. Dark matter is still a mystery, and scientists are trying to figure out what it is and where it came from. Is an effort to learn more about dark matter and its history. A crucial part of the universe's history is its expansion. Through his studies of faraway galaxies, Edwin Hubble proved that the cosmos is expanding and that galaxies are receding from Earth at rates directly proportionate to their distance. A more recent finding indicates that this expansion is speeding up, propelled by an enigmatic entity called dark energy. A number of hypotheses propose various results, such as the Big Freeze, the Big Crunch, or the Big Rip. We want to learn more about the universe's and our part in its ultimate fate as our space exploration efforts progress. The part of the cosmos that is visible and quantifiable is called the observable universe. Light travels at a certain speed, and the cosmos is finite in age. We can only see things whose light has traveled far enough to reach us because of how long it takes for light to travel. The vast, maybe endless cosmos extends beyond the visible universe. These faraway places are invisible to us, and our instruments can't detect them since their light hasn't traveled far enough to reach us. Due to this restriction, there is a cosmic horizon beyond which our understanding becomes severely constrained. A diameter of about 93 billion light-years is attributed to the visible cosmos. This enormous space encompasses all the celestial objects, stars, and galaxy clusters that our present-day instruments can detect. Its enormous immensity belies its tiny proportions in relation to the cosmos. Cosmology relies on knowing how the visible world differs from the whole cosmos. In doing so, it aids researchers in developing hypotheses and models about the universe's beginnings and development. Researching what we can see allows us to draw conclusions about the cosmos as a whole. According to cosmic inflation, the universe is much bigger than what we can see because of the fast expansion that occurred just after the Big Bang. Space expanded at a rate greater than the speed of light for a short instant, causing certain parts of the cosmos to pass beyond our line of sight. An analogous concept to the event horizon around a black hole, the visible universe offers the notion of a cosmic horizon. There is no such thing as seeing beyond the cosmic horizon, just as there is no such thing as seeing beyond the event horizon of a black hole. This limit is always becoming wider as the cosmos becomes older. Our knowledge of the universe's size and form is influenced by several models, including the flat, open, and closed models. Cosmological microwave background radiation measurements, galaxy distributions, and other data provide the basis of these theories. The observable universe is defined in part by the curvature of space. Parallel lines stay parallel, and geometry is Euclidean if the universe is flat. The viewable horizon might be different in a curving universe due to the different geometry. A novel approach to cosmos exploration is provided by gravitational waves, which are ripples in space-time generated by enormous cosmic events. Indirectly revealing what is beyond the observable cosmos, scientists may collect data on places beyond it by detecting these waves. Dark energy influences the pace of expansion of the cosmos, which in turn impacts our visible universe. It is already challenging to examine the cosmos, and as the expansion speeds up, more and more places will be beyond of our observational grasp. It is already challenging to investigate the whole cosmos, and as the expansion speeds up, more and more places will be beyond of our observational grasp. This quickening makes it harder for us to comprehend the universe. There are hypotheses that suggest several universes, with our one being only one of them. It is possible that the physical laws and constants in these parallel realities are different. Even while we can't see into these parallel worlds, knowing they exist can help us make sense of the riddles here on Earth. One of the most important tools for investigating the visible cosmos is the cosmic microwave background radiation. Offering a glimpse into the early circumstances and energy distribution of the universe at a mere 380,000 years old, it gives a snapshot of that time. In order to create a map of the visible cosmos, massive surveys of galaxies and other cosmic structures are necessary. Through the cataloging of millions of galaxies, projects such as the Sloan Digital Sky Survey have shed light on structures and patterns that aid in our comprehension of the universe's development. Technological progress, including the creation of ever more powerful space observatories and telescopes, keeps expanding the limits of what can be seen in the cosmos. With the use of these tools, we can view further into space, which has opened our eyes to things we hadn't seen before. The study of the observable universe is an attempt by scientists to deduce answers to basic cosmic problems. Even if some of the universe's mysteries are still beyond our direct observational capabilities, we are getting closer with each new discovery. Here we are, embarking on a voyage across the annals of space and time. From its beginnings to the present day, the universe has been molded by a series of major events, which we will examine in this video. A thorough comprehension of the universe's development will be provided by delving into a certain epoch in each segment. First, we'll take a brief overview of the cosmos to provide the groundwork for our journey. We will separate the whole universe from the observable universe and define the universe here. Having this background information will allow us to fully grasp the magnitude and intricacy of what we are going to discover. The Big Bang, the cosmic explosion that began it all, will be our next topic of study. We will go into the factors that led up to the fast inflation that followed, as well as the data that supports this view. If we want to know how the cosmos came to be, we must know these early times. After the Big Bang, we'll talk about how the first components were formed. Primordial nucleosynthesis produced the building blocks of stars and galaxies, including hydrogen and helium. The role of these light components in the expansion of the universe is discussed in this section. Once the first ingredients have come into being, we will enter a period called the Dark Ages. Up to the formation of the first atoms, this time in the universe had no light. The cosmic microwave background radiation, which gives a picture of the cosmos at this period, will be our focus. The emergence of the first stars coincided with the waning of the Dark Ages. These huge, short-lived stars of population 3 were essential in the formation of heavy elements. Learn how the universe's early light sources came to be and how they shaped later cosmic architectures in this section. What follows is a discussion on galaxy development and formation. We'll take a look at the evolution and evolution of these huge star systems as well as their gas and dark matter components. The interesting variety of galaxies we see now is the result of dynamic processes which will be unveiled in this section. The mysterious element known as dark matter is essential to the structure of the cosmos. We will explore dark matter's supporting evidence, its role in galaxy formation, and the never-ending search for its nature. In this part, we'll look at one of the most fascinating parts of contemporary cosmology. The expansion of the cosmos is another important subject. We will talk about dark energy, Hubble's law, and the finding that the universe is expanding at an accelerating rate. What these occurrences mean for the future of our knowledge of the universe is enormous. The cosmic web and superclusters, which make up the universe's large-scale structure, will be our next focus. We'll take a look at the formation of these enormous structures and what they tell us about the structure of the universe as a whole. Here, you will find a cosmic overview at a macroscopic level. Quasars and black holes are two of the cosmos's most intriguing features. We'll go over how they come to be, what makes them unique, and how they impact the environment. This section will focus on the tremendous occurrences and harsh conditions linked to these celestial bodies. Extraterrestrial events and strange occurrences will also be covered. Among other remarkable happenings, we will discuss gamma-ray bursts and gravitational waves. These occurrences provide light on the universe's most dynamic and enigmatic processes. Lots of people are interested in studying and speculating about the cosmos's potential future. Various hypotheses, such as the Big Freeze, Big Crunch, and Big Rip, will be considered on its eventual demise. In this section, we shall take into account, according to our present scientific knowledge, the cosmic development over the long duration. As we go, we will also pass by places where the technology and instruments used to examine the cosmos are discussed. All of these tools, from space probes to telescopes, have completely changed the way we study the cosmos. We'll focus on the most noteworthy developments in this area. The never-ending search for the universe's mysteries will be front and center in this video. New information adds to what we already know, bringing us closer to a complete picture of the universe. The story will highlight the ever-changing and dynamic character of cosmological studies. When asked to explain the Big Bang, most people still point to it as the most plausible scenario. According to this hypothesis, the cosmos expanded from a dense and very hot singularity at the beginning, and this expansion took place in a split second. This notion is backed by strong and varied data. Cosmic microwave background radiation is a key piece of evidence. This faint light, which was found in 1965 and is pervasive across the universe, provides a picture of the newborn universe at its youngest age of 380,000 years. As a remnant of the Big Bang's heat, it reveals important details about the early cosmos. Edwin Hubble's 1920s observations of the universe's expansion provide further evidence in favor of the Big Bang hypothesis. The more distant the galaxies are, the quicker they are retreating from us, according to Hubble's discovery. According to this finding, the cosmos is expanding, which means it was once denser and smaller. The formation of new atomic nuclei, a process known as nucleosynthesis, provides more proof. The Big Bang hypothesis predicts that the cosmos is relatively abundant in light elements such as lithium, helium, and hydrogen. During Big Bang nucleosynthesis, which occurred in the first minutes after the Big Bang, these elements were created. The universe's grand structure provides yet another piece of corroborating evidence. According to the Big Bang hypothesis, there are patterns in the dispersion of galaxies and cosmic structures. Consistent with the predictions of the theory, observations reveal a large-scale cosmos that is uniform and isotropic. Another piece of evidence is galactic redshift, anticipated by theory. Another piece of evidence is galactic redshift. The expanding cosmos stretches the light from faraway galaxies, making it lean more toward the red end of the spectrum as it makes its way to Earth. This redshift is inversely proportional to the galaxy's distance, lending credence to the idea that the cosmos has been expanding since its singularity. The Big Bang theory is backed up by data on galaxy clusters as well. The movement and dispersion of these clusters are consistent with Big Bang theory-based simulations. There is large-scale evidence from these clusters that the cosmos has changed from a hot, dense condition to its present expansive shape. Elements are abundant in the first stars, which supports the Big Bang idea. The early universe's makeup is mirrored by these stars, which are mostly hydrogen and helium. According to their elemental composition, nucleosynthesis was predicted to have occurred after the Big Bang. It is backed by the uniformity of the cosmic microwave background radiation, the theory of cosmic inflation, which states that the universe expanded rapidly after the Big Bang. The homogeneity of the cosmic microwave background radiation provides support for the idea that inflation explains the universe's isotropic and homogeneous evolution. The structure we see in the cosmos today is the result of inflation, which explains why the universe was so uniform and flattening out any early imperfections. There is a connection between the Big Bang hypothesis and the finding of gravitational waves, which are ripples in space-time brought about by enormous cosmic events. These waves provide us a fresh window into the early cosmos, allowing us to maybe piece together what happened immediately after the Big Bang. The theory's predictions of dynamic processes are corroborated by the discovery of these waves. The circumstances immediately after the Big Bang are replicated in high-energy particle physics experiments. Scientists learn more about the early universe's basic particles and forces' behavior via these accelerator experiments. The Big Bang theory is consistently backed by the results of these studies. We may learn about the early cosmos from observations of faraway galaxies and how they have changed over the years. From the Big Bang up to the current day, astronomers may follow the expansion and evolution of the universe by analyzing these galaxies. These findings provide an ongoing chronicle of the universe's past. From the Big Bang up to the present day, cosmological simulations use sophisticated computer models to recreate the universe's development. Structures and patterns generated by these physics-based simulations match those seen in the night sky. They provide a potent instrument for evaluating and enhancing the Big Bang hypothesis. The Big Bang theory is backed by the fact that the cosmos is isotropic, meaning it is uniform in all directions. The cosmos is very constant on vast sizes according to measurements, with small fluctuations explained by inflationary theory. The Big Bang theory predicts this consistency. Last but not least, the Big Bang timeframe is consistent with the ages of the universe found by other means. Consistent with the predictions of the Big Bang hypothesis, observations of the earliest stars, the rate of cosmic expansion, and the cosmic microwave background all indicate that the universe is about 8 billion years old. There was a highly dense, very hot condition of the cosmos at the beginning. Modern particles couldn't have existed in their present state due to the very high temperatures. On the contrary, basic particles and energy were a disorganized mess. The cosmos shrank to the size of an atom at this early stage. A singularity with infinite density and temperature was formed when the whole cosmos's matter and energy were crushed into one tiny point. The subsequent fast growth was made possible by this status. Quarks and gluons were born from the cosmos as it shrank and expanded in the first second. The nucleon and the proton are both composed of these elementary particles. In this hot, dense plasma, quarks existed freely at these very high temperatures. Due to the increased cooling that occurred as the cosmos expanded, quarks were able to unite into protons and neutrons. In the first few minutes, this process took place, paving the way for the creation of atomic nuclei. The quark epoch describes this pivotal time in the early cosmos. Assembling the first atomic nuclei started with the combination of protons and neutrons. The lightest elements, namely hydrogen and helium, were created by this process known as nucleosynthesis. Star creation and the expansion of the universe were both powered by these elements in the distant future. The distribution of energy in the cosmos was likewise impacted by the fast expansion. The development of galaxies and other bigger structures was triggered by minute changes brought about by density and temperature fluctuations. Subtle changes that, in time, would result in the creation of galaxies and other bigger structures. The cosmic microwave background radiation bears the fingerprint of these primordial variations. There were major shifts in the universe's underlying forces in the first few minutes. After coming together during the Big Bang, these forces started to drift apart as the cosmos cooled. The strong and weak nuclear forces, electromagnetic and gravity, all developed independently. The structure of the early cosmos was greatly affected by the occurrences that broke symmetry. A roughly equal quantity of matter and antimatter were created as a result of these events. But a little misalignment let matter take over, and the universe as we know it came into being. To grasp the starting point, one must be familiar with the idea of inflation. In the blink of an eye, the cosmos underwent a fast exponential expansion that, in preparation for its large-scale structure, smoothed away imperfections. The cosmic microwave background is seen as uniform, and this idea helps to explain why. The seeds for galaxy creation were planted by inflation, which also stretched microscopic quantum fluctuations to macroscopic sizes. As time progressed, these variations intensified due to gravitational pull, and the intricate galactic network of clusters and galaxies was born. The cosmos went from a period dominated by radiation to one dominated by matter as it cooled. Gravity was able to exert its dominion over the universe's structure-forming processes after this change. To piece together how the cosmos evolved from its hot, dense birth, knowledge of this transition is essential. The production of stable atoms, signaling the end of the plasma stage, was made possible by the cooling universe. The cosmos became radioactively transparent when electrons merged with protons and helium to create neutral atoms. During this time, which is called recombination, matter and radiation were uncoupled. As a consequence of the disconnection between matter and radiation, the cosmic microwave background radiation was released. These remnants of radioactive decay give light on the early universe and its development by providing a picture of the cosmos at the time of recombination. Additionally, the quantity of various elements in the cosmos is determined by the original circumstances. Consistent with expectations from Big Bang nucleosynthesis, the current abundances of hydrogen, helium, and small quantities of other light elements validate our knowledge of these early moments. To make sense of the enormous cosmic history that followed, it is necessary to understand the universe's beginning circumstances. From the tiniest particles to the biggest galaxies, everything we see today had its origins in these pivotal events, which shaped the magnificent structure of the universe. The cosmos expanded at a dizzying rate during the inflationary epoch. This exponential growth in the extent of the cosmos occurred in a split second. Inflation was postulated as a solution to several cosmological issues, including the horizon and flatness concerns. On a vast scale, the cosmos is now homogeneous and isotropic due to inflation, which masked any early anomalies. The cosmic microwave background radiation demonstrates this consistency by displaying an exceptionally flat temperature distribution throughout the sky. The fact that magnetic monopoles do not exist is also explained by inflation. Although they have never been seen, these hypothetical particles were anticipated by early models of the cosmos. Their rarity in the visible cosmos is due to inflation, which would have reduced their impact. Macroscopic scales were extended to quantum fluctuations that occurred during the inflationary epoch. all the formations we see in the universe today, such galaxies, stars, and clusters, originated from these minute changes in temperature and density. The inflaton field is a hypothetical field that is believed to be the source of the energy that drives inflation. This field's energy dissipated into particles and radiation as the cosmos expanded, creating the dense, hot state envisioned by the Big Bang theory. According to inflation theory, the cosmos is flat. Cosmic microwave background and galaxy distribution observations corroborate this prediction, demonstrating that the universe's geometry is almost flat. The consistency provides further support for the inflationary concept. We go from an inflationary universe to one loaded with particles and radiation when the reheating phase ends. The early cosmos was hot and dense because the energy from the inflaton field was transferred to standard particles during reheating. The idea of inflation also explains how the universe's large-scale structure came to be. Eventually, galaxies and clusters formed as a result of the gravitational pull on changes in density caused by the first quantum fluctuations stretched during inflation. As a result of inflation's fast growth, formerly close-knit parts of space are now far separated. This explains why, ever since the Big Bang, apart parts of the cosmos have shared characteristics, even though they have been causally separated from one another. Contemporary conceptions of the cosmos include the inflationary phase as a crucial component. Giving a fuller picture of how the universe came to be, it clarifies a number of important points that the standard Big Bang hypothesis failed to address. Cosmic microwave background measurements challenge inflation's predictions. Insights into the early universe circumstances and support for the inflationary theory are provided by precise measurements of the condensed matter, black holes' temperature variations, and polarization. The precise characteristics of the inflaton field remain a mystery to scientists. Even though it has a solid theoretical foundation, cosmologists still don't know what actual particle or field caused inflation. Several inflationary models have been developed as a result of the effectiveness of inflation theory in describing the large-scale structure of the cosmos. Our knowledge of the early cosmos is enhanced by these models, which investigate many possibilities about the inflatant field and its behavior. The multiverse idea is also affected by inflation. Multiple, perhaps endless worlds with different physical rules may be created if inflation were to occur again, according to some theories. Our understanding of reality itself is broadened by this concept. We will keep testing and refining the inflationary hypothesis as our observational skills increase. New evidence or insights into this crucial epoch in the universe's history may be revealed by future discoveries, particularly in the field of gravitational waves. The cosmos kept expanding and cooling after the inflationary phase ended. Even in the early 10th of a second, the density and extreme heat persisted. Particles, the smallest units of matter, may have formed in this ideal setting. It was quarks and leptons that first materialized. Protons and neutrons are made up of quarks, while electrons and neutrinos are leptons. Quarks and gluons were in a free state called a quark-gluon plasma at these very high temperatures. Quarks may merge to create protons and neutrons once the cosmos cooled enough to do so. This happened in the first few microseconds. These more stable particles were formed when quarks were bonded together by the strong nuclear force, which was mediated by gluons. Early on, neutrinos separated from the rest of the particles, despite their very weak interactions with matter. With their boundless energy and knowledge of the early cosmos, they floated effortlessly across space. Even though they are very hard to detect, these remnant neutrinos are still there today. Additionally, electrons, a different kind of lepton, were pivotal. Neutral hydrogen atoms were formed as electrons fused with protons when the cosmos cooled even further. Although recombination wasn't a process that happened until much later, electrons were there from the start. In the early cosmos, interactions between photons were the norm. In a state of thermal equilibrium, photons, particles of light, were always interacting with one another. At this point in time, the cosmos was opaque, because to the constant scattering of photons by unbound electrons and protons, the matter density dropped as the cosmos cooled more. The result was a gradual decoupling of photons caused by particles interacting less often. The cosmic microwave background radiation that we can see now is a result of this decoupling. Nucleosynthesis could not have begun without the creation of protons and neutrons. The smallest elements, including hydrogen, helium, and trace quantities of lithium and beryllium, have their nuclei formed during the first minutes of this process. Big Bang nucleosynthesis refers to this time frame. The introduction of quark confinement was a watershed moment. Because quarks could never again exist independently under typical circumstances as the cosmos cooled, they were trapped within protons and neutrons. A key component of the theory that describes strong interactions, quantum chromodynamics, is this process. Antiparticles were also created during the synthesis of basic particles. An antiparticle, which has the opposite charge of a particle, exists for every particle in the universe. Photons are the result of the annihilation of antiparticles when they collide. An essential part of the early universe's formation was this destruction. The cosmos was dominated by matter because to a small imbalance between matter and antimatter. The fact that some matter persisted after the majority of particles and antiparticles had destroyed each other is due to this imbalance, which is called baryon asymmetry. Research is ongoing to determine the precise reason for this imbalance. Furthermore, unusual particles were able to arise due to the early universe's harsh circumstances. Some of these ideas go beyond the current mainstream model of particle physics and predict the existence of hypothetical particles. If we could decipher these particles, we might learn more about the universe's underlying structure. Particle accelerators, such as the Large Hadron Collider, reproduce high-energy particle collisions that occurred in the early cosmos. Scientists may learn more about the circumstances immediately after the Big Bang, thanks to these studies that examine the characteristics and interactions of elementary particles. Particle mass is imparted by the Higgs field, which was validated by the 2012 finding of the Higgs boson. An important step in comprehending how elementary particles behaved and formed in the early cosmos was reached with this finding. New insights into the building blocks of matter are being explored. Our knowledge of these processes is expanding thanks to technological advancements and theoretical models, and it is illuminating the complex and intriguing history of the early cosmos. Singularity characterized the cosmos in the first second after the Big Bang. The concept of time and space as we know it started with this. It was a very hot, dense, and quickly growing cosmos. Inflation began within a billionth of a second after the Big Bang. As the cosmos expanded exponentially during inflation, it smoothed out any early imperfections and prepared the way for structures on a grand scale to arise. The expansion of the cosmos cooled it to a point where quarks and gluons could be formed. Protons and neutrons were formed when these elementary particles fused in order to develop. The creation of protons and neutrons occurs when these elementary particles unite. This happened in the very first microseconds when the cosmos came into being. Neutrinos began to flow freely across space around 1 second after the Big Bang when they separated from matter. Neutrinos were able to transport energy and data about the early cosmos because of this decoupling. Nuclear fusion started during the first 3 minutes, combining neutrons and protons to create the nuclei of the lightest elements. Hydrogen, helium, and small quantities of beryllium and lithium were all created at this stage of nucleosynthesis. The cosmos entered a radiation-dominated era after the first few minutes. Constant interactions between photons, electrons, and protons kept the cosmos opaque and ensured thermal homeostasis. Neutral hydrogen atoms were formed when electrons combined with protons, some 380,000 years after the Big Bang, when the cosmos had cooled down. Recombination was the mechanism that liberated the cosmic microwave background radiation by letting photons flow freely. One may see the cosmos as it was during recombination via the cosmic microwave background radiation. The cosmos has expanded this remnant radiation to longer wavelengths, yet it still contains important information about the early cosmos. The cosmos descended into the so-called Dark Ages after recombination. Neutral hydrogen blanketed the cosmos at this time, and stars and galaxies did not yet exist. This period persisted for a good 150 million years. On the order of 100–200 million years after the Big Bang, star formation got underway. Massive and very brief in their lives, these stars of population 3 synthesized the first heavy metals via nuclear fusion and supernova explosions. The Dark Ages ended with the birth of the first stars, which ushered in the reionization era. With time, the hydrogen gas around these stars became ionized by the ultraviolet light from the stars, and the cosmos became more transparent to ultraviolet light. Huge formations seen in the cosmos today are the result of stars and galaxies congregating as a result of gravity. Even after billions of years, structures with clear hierarchies were still taking shape. Galaxy clusters and individual galaxies started to stand out around 1 billion years after the Big Bang. The cosmic network of filaments and voids started to take shape, and the large-scale structure of the universe started to resemble what we observe today. An unknown element called dark energy continued to accelerate the expansion of the cosmos. The ultimate destiny of the cosmos is affected by this acceleration, which has far-reaching consequences. There were distinct epochs in the universe's history, each marked by a unique set of defining processes and components. Every step along the cosmic timeline, from the birth of subatomic particles to the development of stars and galaxies, has added to the complexity and flux of the universe as we know it today. During the first moments of the universe's existence, there was primordial nucleosynthesis, which is also called Big Bang nucleosynthesis. The first atomic nuclei were formed during this short epoch when the cosmos was hot and dense enough to support nuclear reactions. The procedure started as soon as the temperature fell below about 1 billion degrees Kelvin. The nuclei of the lightest elements were produced as quarks started to collide and cling together, creating protons and neutrons. Deuterium and helium-3, two heavy hydrogen isotopes, were the first nuclei to appear. A chain reaction involving protons and neutrons created these nuclei. An essential stage in creating heavier nuclei was the synthesis of deuterium. Rapidly joining with protons and neutrons, deuterium nuclei created helium-4, the most stable and abundant byproduct of initial nucleosynthesis during subsequent reactions. It was possible to produce large amounts of helium-4 nuclei, which had 2 protons and 2 neutrons. Helium-4 was not the only light nucleus that was created. Deuterium, lithium-7, and helium-3 were all formed in modest quantities. But heavier elements, which would eventually develop in star cores, were not conducive to formation in the early cosmos. These light elements' relative abundances pose a serious challenge to the Big Bang hypothesis. The quantities of hydrogen, helium, and lithium seen in the interstellar medium and in the earliest stars are in agreement with the predictions given by models of primordial nucleosynthesis. Only about 20 minutes were required for primordial nucleosynthesis to complete. Nuclear reactions were rendered impossible beyond this point in time due to the expansion and cooling of the cosmos. The plethora of light components remained mostly unchanged. The chemical development of the universe was set forth in motion by the production of these elements. The building blocks of stars and galaxies were hydrogen and helium, the principal byproducts of early nucleosynthesis. Information on the density of baryonic matter in the early cosmos may be gleaned from the abundance of deuterium in particular. Nucleosynthesis. Normal matter abundance may be inferred by comparing measured deuterium abundance with theoretical expectations. The ratio of neutrons to protons, as dictated by interactions of the weak nuclear force in the early post-Big Bang seconds, was also crucial to the process. During nucleosynthesis, this ratio affected the relative quantities of helium and hydrogen. Cosmic microwave background radiation observations corroborate the hypothesized primordial nucleosynthesis as well. Consistent with the abundances of light elements, the small temperature changes seen in the cosmic microwave background, CMB, give light on the early universe's circumstances. A crucial component of the Big Bang hypothesis, primordial nucleosynthesis, connects the circumstances of the early cosmos to the chemical makeup that we see in the present day. It shows how the universe evolved as a result of basic activities in the early cosmos. Research into primordial nucleosynthesis is a dynamic field. To better comprehend this pivotal epoch, which sheds light on the early history of the cosmos and basic physics, scientists use both observable evidence and theoretical models. More accurate assessments of nucleosynthesis hypotheses may be forthcoming from future data, particularly those pertaining to primordial elements in faraway old galaxies and stars. We may learn more about the universe's beginnings and find answers to unanswered questions if these findings pan up. An outstanding illustration of how the generation of the first elements was controlled by the initial circumstances and subsequent expansion of the universe is primordial nucleosynthesis. Modern observations of the universe's intricate chemistry and structure have their origins in this process. The creation of hydrogen and helium was an essential event in the early cosmos. Primordial nucleosynthesis mostly produced these two elements since they were the lightest and easiest to produce. The primordial molecule consisted of a hydrogen atom and an electron. Deuterium, a heavy hydrogen isotope consisting of one proton and one neutron, might have formed when the cosmos cooled. Helium could not have been formed without deuterium. The most stable and abundant form of helium, helium-4, is formed when deuterium nuclei fuse with protons to make helium-3. This stable form of helium is further enhanced by fusing with additional deuterium or helium-3 nuclei. Generate helium-4, the stablest and most common form of the nucleus. A large number of helium-4 nuclei, which consist of 2 protons and 2 neutrons, were created in the first moments after the Big Bang. Since helium-4 is the most common isotope of helium in the cosmos, this technique worked well. These light elements formed in an environment that was favorable to their creation in the early cosmos. A stable nucleus could be formed when protons and neutrons combined because to the ideal conditions of density and temperature for nuclear processes. What we see in the current abundance of hydrogen and helium is a reflection of what happened during the early stages of nucleosynthesis. Hydrogen makes up about 75% of the universe's baryonic mass, helium-4 around 25%, and a few other light elements make up the rest. An important piece of evidence that supports the Big Bang hypothesis is this ratio of hydrogen to helium, confirming the predictions provided by models of the early cosmos. Observations of faraway galaxies and the earliest stars reveal the same proportions. The creation of hydrogen and helium was a watershed moment in cosmic history. These elements served as the foundation for the earliest stars and galaxies, allowing for the production of heavier elements and the birth of new star generations. Nuclear fusion transformed hydrogen into helium in the early stars' cores, producing energy that powered the star's brilliance. The process is still ongoing in stars like our Sun and many others, and it's what gives them their light and heat. The evolution of cosmic microwave background radiation was also affected by helium production during the Big Bang. We can see the effects of the early universe's density and temperature, which are influenced by the helium abundance, on the cosmic microwave background, CMB. Scientists learn more about the early cosmos via studying the creation of hydrogen and helium. Scientists might improve their theories of primordial nucleosynthesis by comparing the abundances of these elements in different cosmic contexts. Additional information on the density of baryonic matter in the early cosmos may be derived from observations of deuterium, a critical intermediary in helium synthesis. Predictions of an abundance of deuterium in old gas clouds and stars are in agreement with observations, lending credence to the Big Bang theory. The chemical complexity of the cosmos was also laid down by the production of hydrogen and helium. The heavier elements needed for planets, life, and the other structures we see in the universe were created when these elements fused with other nuclei via stellar processes. Our knowledge of the early cosmos is being filled in piecemeal as scientists investigate how hydrogen and helium were formed. More information on the beginnings of the universe's elemental makeup may be uncovered by using new observational methods and theoretical models to go deeper into this vital epoch. In order to investigate the latter phases of cosmic development, it is necessary to understand how hydrogen and helium were formed. The complex web of physical and chemical processes that have molded the cosmos over the course of billions of years begins with these components. Protons and neutrons were essential building blocks of the early cosmos. Atomic nuclei are composed of these particles, which are called nucleons. Their mutual influences dictated how the first pieces came to be. When the Big Bang occurred, the cosmos was heated to a point where quarks and gluons could coexist without restriction. Protons and neutrons were created by quarks combining when it cooled and expanded. The hadronization process was completed in a matter of microseconds. A proton has 3 quarks, 2 up and 1 down, and they all add up to a positive charge. There is no electric charge in a neutron, which consists of 2 down quarks and a single up quark. The powerful nuclear force keeps the 2 particles together despite their differences. To carry out nucleosynthesis, a precise ratio of protons to neutrons was required. Because neutrons are somewhat heavier than protons, there were initially slightly more protons than neutrons. Elements of different sorts and quantities were affected by this imbalance. Unstable neutrons decay into protons, electrons, and antineutrinos every 10 minutes or so while they're free. There were fewer neutrons than protons in the early cosmos because some of them decayed before combining. Deuterium, a heavy hydrogen isotope, was created when protons and neutrons merged. The synthesis of heavier elements began with deuterium nuclei, which consisted of a proton and a neutron. The temperature and density have to be just right for this procedure. Deuterium was an immediate participant in subsequent nuclear processes after its formation. A helium-3 nucleus could be formed by fusing 2 deuterium nuclei. A helium-4 nucleus could be formed by fusing 2 helium-3 nuclei. In order to construct the light components, these reactions were crucial. The production of various elements was dictated by the ratio of protons to neutrons. Hydrogen would have been more abundant had the neutron-to-proton ratio been lower, but helium and other heavier elements would have been more abundant with a higher ratio. Heavier elements instead of hydrogen, which would have been more likely to form with a lower ratio. When it came to hydrogen, the most common element in the cosmos, protons were still the most important component. The fundamental units for the creation of stars and galaxies were hydrogen atoms, which comprised of a single proton and an electron. The creation of helium and other light elements relied on neutrons, which were essential but very rare. By virtue of their existence, stable nuclei containing more than 1 proton were able to be formed, thereby circumventing the electrostatic attraction between protons with positive charges. A powerful nuclear force controlled the neutron-proton interaction. Quarks and nucleons are bound together in atomic nuclei by this basic force. With gravity and wind, it forms one of nature's 4 basic forces. In order to recreate the circumstances of primordial nuclear synthesis, scientists need to understand the function of protons and neutrons in the early cosmos. To validate or improve our hypotheses on the origins of the universe, observations of elemental abundances serve as crucial tests for these models. Modern physics is also affected by how neutrons and protons behave. We learn more about nuclear forces, particle physics, and the basic structure of matter via studies of their interactions. Studying the actions of neutrons and protons is an ever-evolving area of research. Studying the actions of neutrons and protons is an ever-evolving area of research. Our understanding of these particles' functions in the early cosmos and modern physics is being enhanced by cutting-edge observations and experiments, such as astronomical surveys and particle accelerators. Evidence of the complex processes that molded the universe may be seen in the history of neutrons and protons. Their interactions shaped the universe's chemical makeup and structural variety, impacting processes as diverse as star formation and the atoms that comprise Earth. A key piece of evidence supporting the Big Bang hypothesis is the abundance of light elements in the cosmos. Hydrogen, helium, and trace quantities of lithium were among the elements created in the first moments after the Big Bang. With a baryonic mass of around 75%, hydrogen is by far the most plentiful element in the cosmos. Its abundance is due to primordial nucleosynthesis and the early universe's starting circumstances. Approximately 25% of the baryonic mass is helium, the element with the second highest abundance. The Big Bang hypothesis accurately predicted that the early universe's nuclear processes would lead to the production of helium-4. A sensitive probe of the circumstances during nucleosynthesis may be found in the quantity of deuterium, an isotope of hydrogen. The measured abundance of deuterium gives a picture of the density and temperature of the early cosmos, because it is readily destroyed in star interiors. Primordial nucleosynthesis also produced lithium, but at a somewhat lower abundance than helium and hydrogen. Nevertheless, there are notable differences between the amounts of lithium-7 that have been found and those that have been predicted theoretically. This is called the cosmic lithium conundrum. In order to learn about the abundances of light elements, scientists measure them precisely in different cosmic settings. By comparing spectroscopic data with theoretical models, astronomers are able to deduce the chemical makeup of stars, gas clouds, and faraway galaxies. The predicted abundances of these light elements in the Big Bang nucleosynthesis hypothesis are in good agreement with the known abundances. We can now validate our knowledge of the early cosmos thanks to this agreement, which lends significant support to the model. Galaxy evolution and history may also be uncovered by differences in the amount of light components. Variegated deuterium abundances, for example, may point to distinct processes and histories of star formation in some areas. Models of star development and the interstellar medium may be improved by accurate measurements of helium abundance, especially helium-3 and helium-4. If we want to know how galaxies and stars transfer and process materials, we need these observations. Scientists may analyze the abundances of light elements in the early cosmos using high redshift studies. Ancient gas clouds and faraway quasars help scientists understand the early universe and its formation. Particularly important for testing cosmological ideas is the amount of deuterium. Due to its unique production and destruction processes, the measured abundance of deuterium may provide insight into the density of baryonic matter in the cosmos. Comprehending nucleosynthesis is difficult and fraught with difficulty, as the cosmic lithium issue shows. We may be missing some details about stellar activities or nuclear reactions if the anticipated and measured lithium-7 abundances are so different. We are learning more and more about the early cosmos as a result of studies into the abundances of light elements. To fix unanswered questions and make our cosmological models more accurate, new theoretical breakthroughs and observational methods are being developed. There are ramifications for other branches of astronomy when we comprehend the abundance of light elements. From the beginning of time to the present, it provides insight into the chemical enrichment of the universe, star formation, and galaxy history. Light element distributions and patterns provide light on the early cosmos, shedding information on the circumstances and processes that shaped that period. These abundances are like a fingerprint of the Big Bang. They show us where the cosmos came from. An important turning point in the history of the cosmos is the assumption of a transparent universe. Recombination was the dominant process in the universe for around 380,000 years after the Big Bang. Neutral hydrogen atoms were formed when electrons reacted with protons when the cosmos cooled sufficiently for this process to occur. This procedure initially made it possible for photons to flow freely by substantially reducing the amount of unbound electrons. The cosmos discharged its cosmic microwave background radiation as it became more see-through. This remnant radiation records the early cosmos as it was just before recombination, giving us a picture of its state at that time. The cosmos was once a dense, hot plasma where photons continually interacted with free protons and electrons before recombination. Light could not reach great distances because the cosmos remained opaque due to this dispersion. As the cosmos cooled, electrons were able to attach to protons, which reduced photon scattering. Since matter and radiation were no longer coupled, photons could travel freely, allowing the cosmos to become see-through. Caused the cosmos to become see-through because photons could now travel unfettered. The red-shifted leftover light from recombination is what we see as cosmic microwave background radiation today. The expansion of the cosmos over billions of years has compressed it to microwave wavelengths. Additionally, recombination signified the transition from an epoch dominated by radiation to one dominated by matter. Clusters and galaxies came into being as a result of gravity taking control once neutral atoms formed. Stars and galaxies might begin to emerge as the cosmos shifted to a more transparent state. The cosmic microwave background, which records temperature changes, served as a seedbed for the development of cosmic structures when photons could freely flow across it. there are small anisotropies in the very homogeneous cosmic microwave background radiation. These minute shifts in temperature mirror the density changes of the early cosmos, which gave rise to the massive structure we see now. Cosmos, as a result of which the massive structure we see today came to be. The cosmic microwave background has been measured in detail by spacecraft like as COBE, WMAP, and Planck. The expansion pace, cosmic makeup, and age of the universe have all been elucidated by these discoveries. Scientists are able to test and improve cosmological theories by deciphering the information hidden in the cosmic microwave background. It provides a plethora of information on the early cosmos, including the densities of various components such as dark energy and dark matter. What happens in later periods of spacetime is affected by the shift to a transparent cosmos. The moment at which light can travel across the cosmos, allowing complex structures to emerge and the visible universe to evolve, is marked by it. Although recombination has been thoroughly studied, new information on this crucial stage is still being uncovered. Recent developments in theoretical modeling and observational technologies have allowed us to have a better grasp on the process by which the cosmos became transparent. Using theoretical modeling, we were able to get a better grasp on the process by which the cosmos become transparent. Through studying this shift, scientists were able to piece together the history of the cosmos, from its early, hot, dense days to its present-day condition. Researchers may learn more about the processes that molded the big-scale structure of the cosmos by studying recombination. One of the most important questions in cosmology is how see-through the cosmos is. In order to better understand how the universe came to be, scientists set out to learn more about this time period in the hopes of gaining insight into the basic forces and particles that controlled it. A pivotal period in cosmic history occurred during the recombination era. It started when protons and electrons fused to create neutral hydrogen atoms, which occurred around 380,000 years after the Big Bang. Electrons were able to connect with protons when the cosmos cooled and energy levels decreased. The number of free charge particles was reduced, photon scattering was decreased, and the cosmos became transparent as a result of this process. Light could not travel far before being dispersed by free electrons in the hot, dense plasma that constituted the cosmos before recombination. The cosmos remained opaque due to this continual interaction. Photons were less likely to be dispersed when neutral hydrogen was formed. The liberation of light from its confines led to the emission of the cosmic microwave background radiation that is visible to our modern eyes. A picture of the cosmos at the instant of recombination is given by the cosmic microwave background radiation. As a result of the density variations that were present at that time, it provides important clues about the early cosmos. The shift from a cosmos dominated by radiation to one dominated by matter was signaled by recombination. Because there were less free electrons, photons could separate from matter, allowing us to see into the cosmos for the first time. Cosmic structures were subsequently formed during this period. Galaxy, star, and cluster formation was initiated by the density variations seen on the cosmic microwave background. Cosmic microwave background temperature changes, which are very small, are a reflection of density variances in the early cosmos. In order to deduce how matter finally fused into the massive structures we see today, these anisotropies are crucial. Extensive maps of these temperature variations have been produced by measurements of the cosmic microwave background taken by missions including as COBE, WMAP, and Planck. The age, composition, and pace of expansion of the universe have been better understood because to these findings. The chemical composition of the age, composition, and pace of expansion of the cosmos were also affected by the recombination epoch. The universe's chemical composition was likewise affected during the recombination phase. In this period, neutral hydrogen and helium atoms were formed, which set the stage for the basic chemical makeup that would subsequently be enhanced by stellar activities. Cosmology relies on a firm grasp of recombination. This allows scientists to analyze the early circumstances that contributed to cosmic development by drawing a distinct border between the opaque early cosmos and the transparent world we experience today. The recombination period is still a dynamic field of study. More information about this crucial epoch is being uncovered by developments in theoretical models and observational methods, which improves our knowledge of the universe's shift to transparency. Dark matter and dark energy may be better understood via research on recombination. These enigmatic universe components may be better understood by analyzing the patterns seen in the cosmic microwave background. The mechanisms that controlled the early cosmos are becoming better understood as scientists go further into the recombination period. The cosmic timescale, beginning with the Big Bang and continuing through the birth of the first galaxies and beyond, may be better understood with this information. In cosmic history, the recombination epoch is a watershed moment. By delving into this time frame, scientists are able to piece together the mysteries of the early cosmos and better understand the basic particles and forces that formed our universe. In cosmic history, the cosmic microwave background's appearance stands as a watershed moment. The cosmos as it was 380,000 years ago may be seen via this remnant radiation. Photons could finally flow freely as the cosmos emerged from the recombination era's opaque condition. The cosmic microwave background came into being as a result of the disconnection between matter and radiation. An afterglow from the Big Bang is known as the cosmic microwave background. It encompasses the whole cosmos and captures the early universe just as matter was recombining. Even though it includes minute temperature variations, this radiation is surprisingly homogeneous in every direction. The differences in density that were present in the early cosmos are mirrored by these oscillations. In 1965, Arno Penzias and Robert Wilson found the cosmic microwave background, which strongly supported the Big Bang idea. It proved what had been predicted about the existence of such background radiation. Multiple missions have taken precise measurements of the cosmic microwave background. They include Planck, COBE, and WMAP. The very fine temperature changes have been precisely mapped out by these measurements. The temperature of the cosmic microwave background is around 2.7 Kelvin, which is slightly higher than 0. The redshift of the radiation caused by the expansion of the cosmos over billions of years is responsible for the chilly temperature. To comprehend the universe's structure on a grand scale, one must be able to decipher the minute variations in the cosmic microwave background. Their relative densities point to potential locations where galaxies and clusters might form as a result of gravitational pull. Knowledge of the universe's makeup may also be gleaned from the cosmic microwave background. Its variations allow scientists to quantify dark matter, dark energy, and regular matter in relation to one another. Cosmic microwave background polarization provides further information about the early cosmos. The gravitational waves and density variations of the inflationary era impact this polarization pattern. The cosmic microwave background's isotropy is one of its most striking characteristics. It is believed that the cosmos experienced a fast inflationary expansion soon after the Big Bang, since this radiation is uniform in all directions. One cosmic backdrop against which the expansion of the universe may be investigated is the cosmic microwave background, or CMB. It is a point of reference for calculating the expansion rate and for comprehending the general geometry of the cosmos. We are learning more and more about the early cosmos because to studies of the cosmic microwave background. The intricate image of the universe's birth and development is being filled in with each fresh observation. Additional information on basic physics may be found in the cosmic microwave background. Dark matter and dark energy, as well as hypotheses on the early universe and particle physics, may be tested in this one-of-a-kind laboratory. Light could once again flow freely once the cosmic microwave background emerged, signaling the end of the first opaque period of the cosmos. The cosmos we see now was shaped by this change, which paved the way for the birth of stars and galaxies. To comprehend the cosmos, one must be familiar with the characteristics of the cosmic microwave background, or CMB. Its almost absolute zero temperature, about 2.7 Kelvin, is one of its most notable characteristics. The CMB exhibits negligible temperature variations on the scale of 1 part in 100,000, notwithstanding its homogeneity. The development of galaxies and other large-scale formations was prompted by density fluctuations in the early cosmos, which these minute changes represent. Being a blackbody radiation, the cosmic microwave background, CMB, exhibits a temperature-dependent spectral pattern. The microwave portion of this spectrum is where the emission from a blackbody reaches its maximum at 2.7 K. The isotropy of the CMB is a notable feature. Its near uniformity in all directions points to a large-scale homogeneity and isotropy in the early cosmos. According to this finding, cosmic inflation is correct. Ultrasound waves traveling through the early universe's thick, hot plasma are responsible for the minute temperature variations, or anisotropies, in the cosmic microwave background, CMB. We can still see the effects of these acoustic oscillations on the cosmic microwave background, CMB. Extra details are revealed by the CMB's polarization. This polarization incorporates the effects of density fluctuations and gravitational waves from the early cosmos, and it is a byproduct of photons scattering off electrons during the recombination phase. Multiple peaks and valleys may be seen in the cosmic microwave background, CMB power spectrum, which is a plot of the amplitude of temperature fluctuations against the angular scale. These characteristics provide details about the geometry and composition of the early cosmos, and they are in correspondence with the sound waves that traveled across it. The cosmic microwave background, CMB, provides information on the densities of baryons, dark matter, and dark energy. These basic cosmological parameters may be inferred from the relative locations and heights of the power spectrum peaks. We may also estimate the rate of expansion of the universe, the Hubble constant, using the cosmic microwave background, CMB. Scientists may determine the universe's present expansion rate by comparing the measured CMB variations to theoretical predictions. We now know how old the cosmos is because to CMB observations, careful calculations using the amount of time required for the known structures to develop from the first oscillations provide an age for the universe of around 13.8 billion years. Consistent with the features of the CMB, we find proof that the universe is curved. The flatness of the cosmos, as predicted by inflationary theory, is confirmed by observations which reveal that parallel lines maintain their parallelism throughout cosmic distances. Dark energy may be shown by observing the integrated Sachs-Wolf effect in the cosmic microwave background, CMB. A faster universe is indicated by this phenomenon, which happens when photons from the cosmic microwave background, CMB, gather energy as they travel through potential wells in the structure of the cosmos. The scattering of cosmic microwave background, CMB, photons off heated electrons in galactic clusters is known as the Sunyaev-Zeldovich effect, which is one of the CMB's other properties. Galaxy cluster features and the dispersion of cosmic matter may be measured with the assistance of this effect. The regularity and small variations in the cosmic microwave background, CMB, also give limitations on the primordial universe's particle types. Although they do allow for novel physics, the observed qualities are in agreement with the conventional model of particle physics. A wealth of information on the early universe, its composition, its expansion, and its large-scale structure may be gleaned from the features of the cosmic microwave background, CMB. For cosmologists, the cosmic microwave background, CMB, is an important instrument for studying the universe and gaining a better grasp of basic physical principles. New insights into the cosmos have been unveiled by the discovery and study of the cosmic microwave background. Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1965 for their discovery of the cosmic microwave background, CMB, which offered clear proof of the Big Bang. The first accurate observations of the CMB's temperature variations were taken by the Kobe spacecraft, which was launched in 1989. The results obtained by Kobe established the CMB's blackbody nature and identified the small anisotropies, paving the way for more research. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, succeeded Kobe in delivering CMB maps with much improved resolution. The data collected by WMAP helped scientists improve their estimates of the universe's age, dark matter and dark energy composition, and the Hubble constant. With the launch of the Planck spacecraft in 2009, our knowledge was considerably improved thanks to the satellite's increased sensitivity and resolution. The Planck observations provided a plethora of information on the early cosmos by detailing the temperature changes and polarization of the cosmic microwave background, CMB. The cosmos is about 13.8 billion years old, according to Planck's findings. The discovery further solidified the age of the universe at about 13.8 billion years and shed light on its shape. Furthermore, it provided further information on the shape of the cosmos, lending credence to the inflationary model's predictions that it is almost flat. The electromagnetic background, CMB power spectrum, as measured by Planck and WMAP, displays a sequence of audible peaks. The density, composition, and expansion rate of the early cosmos may be inferred from these peaks, which are corresponding to sound waves in the plasma of that universe. Results from the cosmic microwave background, CMB, have shown the presence of dark energy and matter. These unexplained components account for the vast majority of the mass energy in the universe, and their quantities may be inferred by studying the variations in the cosmic microwave background, CMB. The trace of primordial gravitational waves has been detected with the aid of polarization measurements taken by Planck and other experiments. The unique pattern in the CMB's polarization that these waves produce during inflation provide information about the dynamics of the early cosmos. The cosmic microwave background, CMB, has been studied at high resolution, which has provided new information on the structure of the universe at large. Scientists are able to track the evolution of cosmic structures across time by analyzing patterns of temperature changes that match to the seeds of galaxies and clusters. Extra proof for dark energy comes from the CMB-observed integrated Sachs-Wolf effect. This effect is caused by the fact that cosmic microwave background, CMB photons, acquire energy when they travel through changing gravitational potential wells, which suggests that the universe is expanding at a faster rate. Interactions between cosmic microwave background CMB photons and heated gas in galaxy clusters are quantified by the Sunyaev-Zeldovich effect. This effect is useful for studying cluster features and cosmic matter dispersal. To supplement satellite observations, there are ground-based and balloon-borne projects like the South Pole Telescope and the Atacama Cosmology Telescope. In addition to probing its small-scale properties, these investigations provide high-resolution maps of the CMB. The detection of the CMB's polarization is the primary goal of the BICEP and Keck-Array investigations. Their work helps fill gaps in our knowledge of cosmic inflation and primordial gravitational waves. Improving our CMB measurements is a primary goal of future flights and experiments. More precise maps will be produced by initiatives like as the Simons Observatory and the CMB-S4 experiment, which will deepen our knowledge of the early cosmos. Cosmology is being shaped by discoveries and observations of the cosmic microwave background, CMB. Consistent with the Big Bang theory and illuminating the basic processes that have molded the universe, each new finding sheds light on its beginnings, composition, and development. A cosmic turning point occurred at the end of the Dark Ages. Neutral hydrogen and helium flooded the cosmos after the recombination epoch, and for hundreds of millions of years it remained black and starless. Around this period, gravity started to magnify small density changes in the cosmic microwave background. The first cosmic structures were created as a result of these oscillations. The first stars, called population 3 stars, were created as these denser regions collapsed. Massive, very hot, and relatively short-lived, these stars were almost completely hydrogen and helium. As soon as stars began to appear, the Dark Ages came to a close. Ionized gas bubbles formed in the intergalactic medium as a result of the strong ultraviolet light generated by these population 3 stars, which started to ionize the hydrogen gas around them. Reionization was a watershed moment in the universe's past. Over time, it made the cosmos less dense and less resistant to ultraviolet light, making it more transparent and reopening space to light. Reionization took place gradually over a period of hundreds of millions of years, rather than all at once. Because their powerful radiation kept ionizing the gas around them, the early stars and galaxies were instrumental in this process. After the first stars were born, galaxies began to form. Small and dim, these early galaxies eventually merged to create bigger and more complicated formations. Reionization was further aided by quasars, which are supermassive black hole-fueled, incredibly bright nuclei of young galaxies. The intergalactic medium was further ionized by their tremendous energy output. Data from faraway quasars and galaxies confirm the reionization timeframe. Ionized bubbles are detected in their spectra because neutral hydrogen absorbs light from these particles. One way to probe the end of the dark ages is to analyze the 21 centimeters line, which is a particular wavelength of light released by neutral hydrogen. By following this line, astronomers may plot the early universe's hydrogen distribution and track the ionization process. The ionization period and the subsequent end of the dark ages shaped the expansion of the cosmos in significant ways. It affected galaxy distribution and attributes, and paved the way for the creation of bigger cosmic structures. Scientists are able to better understand the history of the universe by gaining a better grasp of this epoch. Researchers may learn more about the mechanisms that created the universe as varied and rich as it is now by examining the last stages of the Dark Ages. James Webb Space Telescope and similar future instruments will attempt to view the first stars and galaxies up close. With these findings, the origins of light sources and the development of reionization may be better understood. A fundamental shift from a featureless black world to one rich with light and structure occurs at the conclusion of the Black Ages. Here, the first galaxies emerged to light up the cosmos and start molding its destiny, signaling the beginning of the cosmic dawn. Studying this time period further sheds light on the complex mechanisms that altered the early cosmos. With each new finding, we get a little bit closer to knowing how the universe's stars, galaxies, and large-scale structure came to be. Ever since the Big Bang's first spectacular expansion, the cosmos has been slowly but surely cooling. Subatomic particles and radiation cooled and shrank in density as the cosmos became larger. The cosmos was thick and scorching in its early moments. Protons and neutrons, due to the very high temperatures, were unable to create stable nuclear structures at that time. Quarks, gluons, and other basic particles were instead a heated plasma across the cosmos. The first atomic nuclei were formed when protons and neutrons were able to unite due to the temperature decrease that occurred during the first few minutes. During this time, which is called nucleosynthesis, the light elements such as hydrogen, helium, and small quantities of lithium were created. Cooling occurred at a faster rate as the cosmos expanded. When the temperature fell low enough, protons and electrons could unite to create neutral hydrogen atoms, which occurred around 380,000 years after the Big Bang. Recombination was the initial step that allowed light to penetrate the cosmos. The cosmic microwave background radiation was released when photons were able to freely travel due to the production of neutral hydrogen. By capturing the cosmos at the instant of recombination, this radiation paints a picture of a very cold cosmos. Even after millions of years, the temperature dropped. The average gas temperature dropped as the cosmos expanded. The first gravitational instabilities were able to expand because, to this cooling, which in turn caused the birth of stars and galaxies. Areas with somewhat more density started to collapse due to the effects of gravity under these colder circumstances. It was from these gas clouds that the earliest stars, according to the population 3 star type, emerged. They cooled the cosmos even more and reionized it with their powerful radiation. The synthesis of molecular hydrogen was also enabled by the cosmos's cooling. Gas clouds could cool down and collapse more effectively with the help of these molecules, which led to the formation of stars and galaxies. Radiation and supernova explosions heated the universe as stars and galaxies were born. On a grander scale, nevertheless, the expansion of the cosmos did not stop it from cooling. The expansion of the cosmos and the warmth caused by stars both had a role in shaping its development. There were consequences for the construction of cosmic structures as a result of the cosmos cooling. Gradually, galaxies and clusters of galaxies were able to form because to the lower temperatures. The intricate cosmic network we see today is the result of these structures expanding and changing over billions of years. A variety of star types were impacted by cooling as well. Massive stars predominated at the beginning of time, but as the cosmos cooled, stars with smaller masses proliferated. The heavier components in the interstellar medium were enriched by these stars, which had longer lives. By studying the cosmic microwave background and the universe's large-scale structure, we may determine how the universe cooled. Scientists may piece together the universe's thermal history by analyzing these leftovers. Learn how galaxies, stars, and planets came to be by delving into the universe's cooling history. This theory lays down the groundwork for deducing the driving forces behind the expansion of the cosmos. More research and theoretical advancements will help us comprehend the cooling of the cosmos even better in the future. Our modern, cold, organized universe evolved from a hot, dense plasma, and scientists want to learn more about this process by delving farther into the cosmos's distant past. A crucial part of the universe's history is the cooling process. It paved the way for the creation of everything in the cosmos, including galaxies, stars, and the circumstances that allowed life to arise. The first stars to emerge from the cosmos were members of population 3. There were hardly any heavier components in these stars. They were practically totally hydrogen and helium. In the early cosmos, when density variations first occurred, thick gas clouds formed, which later gave rise to stars of population 3. Due to gravity's pulling on these clouds, they warmed up until they were hot enough to undergo nuclear fusion. Stars in the population 3 were far larger than the typical star in our galaxy. Their masses were hundreds of times greater than the Sun's. Their massive bodies caused their interiors to become very hot, and they didn't last very long, sometimes only a few million years. Massive and very bright, population 3 stars burned through their fuel very rapidly. They were instrumental in ionizing the cosmos and making it transparent to UV light because of the massive quantities of UV radiation they released. Population 3 stars' powerful radiation ionized the hydrogen gas around them, forming expanding gas bubbles. To get from the dark ages into a light-filled world, this reionization process was crucial. Supernova explosions were the stunning finale to the lives of stars in population 3. Heavy elements including as carbon, oxygen, and iron were created and dispersed into the interstellar medium by these explosive explosions. These new elements were enriched into the primordial gas by the supernovae of stars in the population 3, which paved the way for the production of stars in later generations and the chemical complexity needed for planets and life. It is thought that population 3 stars were pivotal in the early cosmos's development. The early galaxies were shaped by their powerful radiation and supernova explosions, which also impacted the creation of subsequent star populations. Population 3 stars are important, although they haven't been seen directly yet. Based on theoretical theories of star formation and the chemical makeup of old stars and gas clouds, we may deduce their presence. We are aiming to discover the feeble traces of these old stars using modern and forthcoming observatories, like the James Webb Space Telescope. It would be a direct proof of the earliest light sources in the cosmos if we could find population 3 stars. Scientists are able to better understand the 3 stars' populations and use that knowledge to reconstruct the universe's history chronology. These stars formed the first heavier elements, setting the stage for the vast chemical variety we see in the cosmos today. Insights on star formation and development may also be gleaned from studies of population 3 stars. Researchers may learn more about the formation and evolution of later star and galaxy generations by studying these early stars. The formation of population 3 stars in gaseous, dense areas and the effects of their supernova explosions on their environments are shown in early universe simulations. The amount and distribution of elements in the cosmos can be better understood with the assistance of these models. A star in population 3 will have an effect much beyond its local area. Their bursts of radiation and supernovae impacted the evolution of galaxy clusters and galaxies as a whole. The chemical makeup of the interstellar medium and the oldest stars today is a testament to the heritage of population 3 stars. More and more scientists have learned about the early stars and their impact on the cosmos via analyzing these artifacts. A new era of profound change began with the birth of the universe's light. Population 3 stars, the first stars to form, marked the beginning of this period. These stars broke through the cosmic night's obscurity and were the first to radiate light. These stars broke through the cosmic night's obscurity and were the first to radiate light. Hydrogen gas around the earliest stars started to get ionized as a result of their powerful ultraviolet light as they burned. The cosmos was progressively reionized as a result of this process, which produced areas of ionized gas. To put a stop to the cosmic dark ages, these early light sources were pivotal. An important factor in the expansion of the cosmos was the light from these early stars. As a result of the gas's heating, it was able to slow its collapse and impact the development of stars and galaxies that came after it. The early universe's star creation was controlled by this feedback process. Ionization was aided by radiation from the first stars as well. Due to their intense radiation, these stars were able to change the intergalactic medium from neutral hydrogen into ionized plasma. Because of this reionization, light could now flow freely across space. The early stars' brilliance was very intense. Due to their much higher mass and luminosity compared to modern stars, stars in population 3 produced vast quantities of UV and even X-ray radiation. The temperature and chemical development of the early cosmos was greatly influenced by this bright light. Heavy elements were added to the cosmos during the supernova explosions of the earliest stars. New stars and planets were born from the carbon, oxygen, and iron that were released into space in these explosions. More complicated structures could not have evolved without this enrichment. Chemical processes in the surrounding gas were also driven by the light from the earliest stars. As a result of these processes, molecules were formed that could cool clouds of gas, which in turn allowed new galaxies and stars to form. Much research has focused on the early light period. To learn about the early stars' formation, their effects on their surroundings, and their role in ionizing the cosmos, astronomers use both observation and modeling. James Webb Space Telescope and similar future instruments will seek to view the first stars and galaxies up close. The characteristics of the first light sources and their influence on the early cosmos may be better understood with the help of these data. Galaxy creation was initiated by the first burst of cosmic light. The first galaxies were created as stars grouped together due to gravity. The intricate structures we see today evolved from these young galaxies, which expanded via gas accretion and mergers. A light-filled world emerged from the dark ages after a long and winding road. It comprised the interaction of the intergalactic medium's ionization, the radiation from the earliest stars, and their creation. All subsequent cosmic evolution had its roots in this epoch. The circumstances of the early cosmos may be better understood via the study of the first light. Researchers may learn about the physical conditions and processes of the past by looking at the light from old galaxies and stars. The cosmos is still being illuminated by the light of the earliest stars. Through the study of faraway objects, astronomers are able to see into the past and learn about the universe's characteristics when it was much younger. Important details on the early phases of the cosmos may be gleaned from this glimpse into the past. Even in the modern day, the impact of the first light may be felt. Ancient stars and interstellar gas contain chemical elements made by the earliest stars, which may teach us a lot about what happened when the universe was young. Our knowledge of the history of the cosmos is shaped by this lasting legacy. An essential turning point that altered the universe was the appearance of the first light. It ushered in the age of stars, galaxies, and intricate structures, laying the groundwork for the vast and varied cosmos we see around us today. The development of subsequent elements was greatly influenced by the early stars. These huge stars, which are called population 3 stars, quickly depleted their nuclear fuel supply. From primordial hydrogen and helium, heavier atoms were produced by nuclear fusion reactions. These stars died in catastrophic supernova explosions when they ran out of nuclear fuel. Carbon, oxygen, and iron were among the heavier elements created and dispersed into space by these explosions. These supernovae enriched the interstellar medium with the building blocks needed to make new stars and planets when their components mingled with the primordial gas. Population 2 stars, the next generation, were born because of this enrichment process. The gas clouds that gave rise to the stars of population 2 were enriched by the earliest supernova. More sophisticated nuclear fusion processes and the creation of a larger variety of elements were possible in these stars because they contained greater levels of heavy elements compared to population 3 stars. Every generation of stars added additional heavy elements to the interstellar medium via star formation and supernova explosions. The metallicity of the cosmos, defined as the abundance of elements heavier than helium, grew throughout time as a result of this continuous nucleosynthesis process. Eventually, population 1 stars like our Sun were formed from the elements created by successive generations of stars. These stars were able to develop with a greater metallicity because they were located in areas of space that had been heavily enriched by supernovae in the past. Aside from creating heavy metals, the development of complex molecules was also influenced by the earliest stars. Molecules such as molecular hydrogen were formed in the gas around these stars as a result of chemical processes driven by their radiation. These molecules were crucial in cooling the gas clouds and allowing for the development of future stars. Clouds of gas changed in physical characteristics due to heavier molecules and elements in the interstellar medium, which altered their collapse potential and thus their capacity to generate new stars. The early universe's star formation rate was partially controlled by this feedback process. There were ramifications for planetary system evolution from the production of heavy metals as well. The development of rocky planets and the complicated chemistry required for life depend on elements such as carbon, oxygen, silicon, and iron. The first stellar explosions paved the way for livable planets to form later on. The first star's supernova explosions also contributed to the process of star creation. Nearby gas clouds collapsed under the pressure of the shock waves from these explosions, allowing new stars to emerge. Stellar populations and galaxy evolution were both aided by this approach. A major focus of astrophysical research is the part played by the early stars in the process of element creation. Scientists may learn more about the chemical history of the cosmos and the beginnings of the atoms that comprise planets and life by figuring out how these stars created and distributed heavy metals. The evidence of the early universe's enrichment processes may be found in observations of old stars and gas clouds. Astronomers may learn about the origins of nuclear synthesis and the role of the early stars by analyzing the chemical makeup of these objects. Scientists may learn more about the origins of nuclear synthesis and the role of the early stars using theoretical models and computer simulations. Scientists are able to make sense of the interplay between star formation, supernova explosions, and interstellar medium enrichment via the use of theoretical models and simulations. The mechanisms that determine the chemical development of the cosmos may be better understood with the help of these models. We will continue to enhance our knowledge of the early stars' involvement in element production via future studies, especially with powerful telescopes. The goal of astronomers studying the early stars and galaxies is to find evidence of the initial nucleosynthesis reactions. An essential part of the development of the universe is the function of the earliest stars in the subsequent production of elements. The intricate structures and varied elements that comprise the universe today may be traced back to their chemical enrichment of the cosmos. In the first billion years of the cosmos, galaxies started to form. As a result of gravity, tiny variations in matter density that persisted after the Big Bang expanded, bringing gas and dark matter together to create the first structures of the galaxy. Compared to modern galaxies, these early ones were much smaller and less structured. They were spherical in form and primarily gas with a scattering of stars. These galaxies started to expand and change as more stuff came to them. Giant ephemeral stars were the first inhabitants of these young galaxies. Their supernova explosions and extreme radiation were critical in forming galaxies, which in turn affected gas dispersion and star formation in following generations. The surrounding gas was additionally enhanced with heavier elements due to the supernova explosions of these big stars. A crucial factor in galaxy development, this chemical enrichment paved the way for the creation of increasingly complicated molecules. The early galaxies became bigger and more organized as they fused with one another. The formation and development of galaxies were accelerated by these mergers, which occurred often in the early universe. Galactic mergers were violent and chaotic processes that often resulted in starbursts. The fast production of new stars was set in motion by the compression of gas during these mergers when gas clouds collided. More solid and ordered structures were formed when these merging galaxies settled into space throughout time. Elliptical galaxies, characterized by a more spherical shape and older star populations, evolved from spiral galaxies with whirling gas and star disks. During the early stages of galaxy creation and development, dark matter played a pivotal role. The development of galaxies was driven by the dynamics of dark matter, which acted as a gravitational scaffolding and helped to collect the gas required for galaxy formation. Along with being locations of powerful radiation and energetic activities, the early galaxies played an important role in gas collection and drove the dynamics of galaxy formation. There was a lot of energy and radiation in the early galaxies. Quasars, which were fueled by supermassive black holes in the middle of some of the galaxies, released a lot of it and affected the gas and star formation in the area. These early phases of galaxy development may be somewhat understood by looking at faraway galaxies. Astronomers may learn more about the processes that formed galaxies by seeing into their distant past, which is billions of light years away. Images of early galaxies, captured in great detail by modern observatories like the Hubble Space Telescope, have shown their sizes, forms, and the processes by which stars were formed. If we want to know how the universe came to be, we need these findings. The intricate interplay of gas, stars, and dark matter may be better understood via simulations of galaxy formation. Scientists may use these models to compare theory with empirical evidence about the development and formation of galaxies. Early galaxies laid the groundwork for the universe's large-scale structure. Clusters of galaxies and their overall placement in the cosmic web are affected by the distribution and characteristics of these galaxies. There is a thriving community of researchers interested in studying early galaxies. The mechanisms that controlled the formation and development of galaxies in the early universe may be better understood via future studies conducted with increasingly powerful observatories. We can better understand the cosmic history of the universe if we know how early galaxies were formed. These galaxies formed the framework of the universe and, as they evolved, molded the intricate and ever-changing universe that we see around us today. Many different types of galaxies exist, each with its own distinct form and size. The Hubble sequence, created by Edwin Hubble in the 1920s, is the best-known method of categorization. One of the most common types of galaxies is the spiral galaxy. A flat spinning disk of gas, dust, and stars characterizes these objects, with a center bulge made up mostly of older stars. Active star creation occurs in the disk's spiral arms. Spiral galaxies include barred spiral galaxies as a subclass. Their starry core forms a bar that radiates out from the bulge in the middle, and in many cases, joins the spiral arms. A barred spiral galaxy is like our Milky Way. Galaxies that are elliptical in form lack the characteristic spiral arms and have a more rounded or extended appearance. Little gas or dust and a preponderance of older, redder stars suggest that star production is low in this group. From very extended to almost spherical elliptical galaxies span the galactic spectrum. Huge ellipticals with trillions of stars are possible, as are dwarf ellipticals with millions of stars. As a third form of galaxy, lenticular galaxies fall somewhere in the middle between spiral and elliptical. They resemble spiral galaxies in appearance, with a central bulge and a disk, but they do not have visible spiral arms. An SO classification is used to lenticular galaxies in the Hubble series. The spiral and elliptical models do not describe irregular galaxies. They don't have a clear outline and often seem disorganized, with gas, dust, and stars all over the place. The abundance of gas and dust in irregular galaxies causes them to be hotspots for star formation. In comparison to regular galaxies, dwarf galaxies are both smaller and fainter. Dwarf ellipticals, dwarf spheroidals, and dwarf irregulars are the three ways to describe them. Small as they may be, dwarf galaxies are crucial to understanding the cosmos and its history. Unlike regular galaxies, peculiar galaxies have peculiar forms and characteristics. Disrupted structures caused by gravitational interactions or galaxy mergers are a common cause of these anomalies. An unusual galaxy type known as a ring galaxy has a central core surrounded by a ring of gas and stars. In most cases, a galactic collision is the culprit responsible for the formation of these rings. A wide variety of galaxies may be born from the regular occurrence of galaxy mergers. What emerges after a merger of two galaxies can be a combination of the two, or something completely different. The very rapid star creation is the defining feature of starburst galaxies. Interactions or mergers with neighboring galaxies often set off this tremendous activity, which results in the fast accumulation of young, massive stars. ENS, or active galactic nuclei, are stellar bodies characterized by very active cores. These are often driven by supermassive black holes that absorb matter and emit tremendous radiation at different wavelengths. Among AGNs, quasars stand out for their extreme luminosity. Being among the most luminous objects in the cosmos, they have the ability to surpass even their host galaxies in brightness. Being among the most luminous objects in the cosmos, they have the ability to surpass even their host galaxies in brightness. Understanding the formation of supermassive black holes and the early cosmos relies heavily on quasars. As astronomers learn more about the many kinds of galaxies and the traits they share, they are better able to put together the universe's development and history. The mechanisms that control star formation, galactic dynamics, and cosmic structure may be better understood by examining different types of galaxies. Interactions and mergers of galaxies are basic cosmological processes. The development and structure of galaxies may be drastically changed by these occurrences. Galaxies produce tidal effects as they approach one another via the force of their mutual gravitational pull. Tidal tails and gas bridges may be formed when these forces alter the morphologies of galaxies. In a galaxy merger, two galaxies merge into one bigger galaxy as a result of a collision. When gas clouds meet and compress, it may cause starbursts, which are explosive bursts of star formation. When galaxies of comparable size combine, it's a major event. The initial structures are disrupted, and the stars, gas, and dust are mixed in spiral galaxies that become elliptical galaxies as a result of these occurrences. Large galaxies may absorb smaller ones in minor mergers. Frequently, the smaller galaxy is ripped apart and absorbed by the bigger one, enriching the host galaxy with gas and stars. Tidal dwarf galaxies may also arise as a result of interactions. These dwarf galaxies, which contain gas and newborn stars, evolved from the remnants of bigger galaxies in the course of their interactions. As they expand, supermassive black holes rely heavily on mergers and interactions. Black holes may be fueled by gas that flows in during these occurrences, which can cause galactic nuclei and quasars to be active. Collisions between galaxies may cause ring galaxies to develop. It is possible for a smaller galaxy to build a star formation ring around a bigger galaxy's core as it passes through its center. Interacting galaxies often display unusual forms and characteristics. A good example would be the antennae galaxies, which are merging and have lengthy gas and star tidal tails. At this very moment, the Andromeda galaxy is barreling into our Milky Way. The two galaxies will eventually combine into one bigger galaxy, maybe an elliptical one, after about 4 billion years. Galaxies may also lose gas via mergers. The two galaxies will eventually combine into one bigger galaxy, maybe an elliptical, after 1 billion years. Another consequence of galaxy mergers is the loss of gas, which may cause ellipticals and other gas-poor galaxies to develop. Due to a decrease in gas production, the stellar populations are becoming older as a result of gas removal. Astronomers learn about the hierarchical structure of galaxy formation via studying galaxy mergers. Both theoretical and empirical evidence suggests that massive galaxies often evolve from the gradual merger of smaller ones. Interactions and mergers are commonplace in galaxy clusters. Clusters of galaxies are more likely to collide due to the high density of the galaxies there. We can learn about the frequency and effect of mergers in the early cosmos by looking at faraway galaxies. These findings are useful for determining how galaxies have changed and expanded over cosmic history. Interactions and mergers are intricate and ever-changing processes that have a major impact on galaxy development. The structures we see in the cosmos now are shaped by them, and they add to the continuing tale of cosmic history. Among the universe's most massive formations are galactic clusters. They are made up of galaxies that are gravitationally bonded together, numbering in the hundreds of millions. Clusters like this provide a one-of-a-kind setting for research into the history and dynamics of galaxy interactions. Cluster galaxies may be elliptical, irregular, or spiral in shape. Several events, such starbursts and galaxy mergers, may result from these galaxies interacting with one another. Clusters of galaxies are dense enough to often collide and interact with one another because to gravity. Gatherings of galaxies are not the only thing that clusters are. Additionally, they hold a great deal of heated ionized gas. Clusters are among the most intense X-ray sources in the sky because of the X-rays emitted by this gas. Clusters must be subject to very strong gravitational forces for this hot gas to be present. In the formation of galaxy clusters, dark matter is pivotal. Even though it doesn't give out any visible light, its gravitational pull can be felt in the way galaxies move and how hot gas behaves. The bulk of the material in a cluster is composed of dark matter. Massive elliptical galaxies, called the brightest cluster galaxy, frequently reside in the cluster's core. Central galaxies that have formed via the gradual assimilation of smaller galaxies are usually encircled by a thick halo of hot gas and dark matter. Throughout evolution, clusters have been seen. Galaxies and subclusters are combining to form bigger structures, while some clusters are still developing. The factors that contribute to the creation and development of clusters may be better understood by studying them at various stages. One interesting occurrence in galaxy clusters is gravitational lensing. Images are warped and multiplied due to the cluster's enormous gravitational field, which amplifies and bends the light from objects in the background. Because of this impact, astronomers may examine galaxies far away as well as the cluster itself. Clusters of galaxies may teach us a lot about the cosmos at large. A huge cosmic web is formed by clusters, which are not scattered randomly, but rather in superclusters, filaments, and voids. On cosmic scales, this web represents the dispersion of dark matter. Additionally, clusters may be used as cosmic laboratories to learn about dark energy and its characteristics. The expansion of the cosmos, which is impacted by dark energy, determines the pace of cluster development throughout time. Scientists may learn more about this enigmatic force by analyzing clusters. Heavy elements are more abundant in the intracluster medium, which is the heated gas within clusters. Stars and supernovae in the member galaxies created these elements, which were ejected into the intracluster medium. Star formation and supernova activity in the cluster's history may be inferred from this enrichment. Active galactic nuclei may also produce strong jets and radio emission lobes inside galaxy clusters. The intracluster medium may be heated by these jets, which in turn can affect the matter distribution within the cluster. Galaxy clusters are perfect for investigating galaxy evolution because to their dynamic environment. Interactions with the intracluster medium may drain gas from cluster galaxies, which in turn can halt star formation and change spiral galaxies into ellipticals. The structure and content of clusters may be fully understood by studying them in a variety of wavelengths, from radio waves to X-rays. By illuminating distinct features of the cluster at each wavelength, a more comprehensive understanding of these intricate systems may be achieved. We will continue to get a better knowledge of galaxy clusters via future studies conducted with sophisticated telescopes and observatories. These findings will provide light on the structure of the universe at massive scales, the origins of galaxies, and the characteristics of dark matter. In order to understand the cosmos, research into galaxy clusters is crucial. These enormous formations are fundamental for deducing the nature of dark energy and matter, the processes that mold galaxies, and the history of the universe as a whole. Galaxies undergo a complicated and ever-changing process of evolution as time passes. The process is propelled by a conglomeration of both internal and external forces, including star formation and supernova explosions. Galaxies originated from primordial gas clouds in the early cosmos. Through gas accretion and mergers, these tiny, atypical early galaxies expanded and changed. The wide variety of galaxies we see now is a direct result of this hierarchical expansion. A major factor in the development of the galaxy is star formation. Star formation is a powerful process that produces new stars from the gas and dust contained in young galaxies. Conditions in starburst galaxies are ideal for the fast production of stars. Hence, this process is very active there. The star generation rates of galaxies tend to decrease with age. Possible causes of this decrease include gas loss via interactions with neighboring galaxies, feedback from supernovae and active galactic nuclei, or gas depletion inside the galaxy itself. Redder, more developed stars are more often seen in older galaxies. One important step in the development of galaxies is the process of galactic mergers. The architecture of merging galaxies may be disturbed during collisions, which can result in the birth of new stars and even other kinds of galaxies, such elliptical galaxies that form when spirals combine. Galaxy morphological changes occur over billions of years. Interactions with the intra-cluster medium in galaxy clusters may deplete spirals of gas, slowing star formation and changing them into lenticular galaxies. Mergers can also cause spirals to become elliptical. Additionally, dark matter plays an essential part in the development of galaxies. Halos of dark matter influence the formation and interactions of galaxies by providing their gravitational foundation. Galaxies' dynamics and expansion are impacted by the presence and behavior of dark matter. Supernovae and active galactic nuclei are examples of feedback mechanisms that control gas distribution in galaxies and star formation. The structure of the galaxy may be influenced by these feedback processes, which can either accelerate outflows or heat the gas to the point where it cannot cool and produce new stars. Environmental variables may also impact galactic evolution. Clusters and groupings of galaxies are more likely to merge or interact with one another than individual galaxies. The general shape of galaxies and the rate of star creation are both impacted by these settings. By keeping an eye on other galaxies, astronomers can trace the history of our galaxy from its first moments. According to these findings, star formation was more vigorous in the early universe, and galaxies were smaller and less regular. We can learn more about the mechanisms that mold galaxies across time by simulating their origin and development. These models account for the variety of galaxies by include dark matter, gas dynamics, star formation, and feedback. Galaxies' chemical development is an additional crucial component. The interstellar medium is enriched with heavy metals when stars develop and die. Both future star generations and the galaxy's general development are impacted by this chemical enrichment. Galaxies are still interacting with their surroundings, merging with other galaxies, and producing stars. Example, the Milky Way is now engaging in galactic interactions with the dwarf galaxy in Sagittarius, and will join with the Andromeda galaxy in the future. Even more profound understanding of galaxy development will be revealed by future studies conducted with more sophisticated telescopes. Throughout cosmic time, astronomers have been able to put together the evolution of galaxies by observing them at different phases of growth. The development of galaxies sheds light on the cosmos's larger evolutionary trajectory. From galactic clusters to the cosmic web, it shows the formation and evolution of large-scale structures spanning billions of years. Several important astronomical and cosmological observations provide evidence for dark matter. The rotation curves of spiral galaxies were among the first pieces of evidence. Stars and galaxies were discovered to be spinning at rates far higher than what was predicted from their apparent masses alone when the rotational velocities were measured. This disparity points to the existence of extra invisible material, often called dark matter, which exerts the required gravitational force to maintain the orbits of these stars. The outer stars would just float away if this additional mass weren't there. Clusters of galaxies also provide strong evidence. The mass of galaxy clusters, as determined by the visible light of their individual galaxies, is inadequate to explain the gravitational effects that have been seen. To account for these findings, more mass from dark matter is required. Additional evidence for dark matter may be found by gravitational lensing. Galaxy clusters and other massive objects may distort and even produce several pictures by bending the light from things in the backdrop. In many cases, the quantity of lensing that can be explained by visible matter alone is insufficient, suggesting that dark matter is present. Dark matter must exist, according to the cosmic microwave background radiation. Missions like SWMAP and Planck have been able to detect minute variations in this radiation, which have revealed details on the early universe's matter quantity and distribution. All of these facts point to a cosmos containing dark matter. Dark matter is also hinted to by the cosmic web, the universe's large-scale structure consisting of galaxies and clusters. Incorporating dark matter into cosmic evolution models improves their agreement with the known galaxy distribution compared to models that just account for visible matter. The development of galaxies is greatly influenced by dark matter. Gas in the early cosmos could not have clumped together to create stars and galaxies at the rate it did without its gravitational pull. The observations of bullet clusters provide compelling proof of the existence of dark matter. The hot gas seen in X-rays is isolated from the rest of the mass, as deduced from gravitational lensing in this collision of galaxy clusters. This dispersion implies that the collision has no effect on dark matter, as it does not interact with the electromagnetic field. It is also possible to deduce dark matter from the movements of cluster galaxies. There must be more dark matter to provide the required gravitational binding, as the speeds of these galaxies cannot be explained by their observable mass alone. The presence of non-baryonic dark matter is hinted at by patterns seen in the cosmic microwave background radiation upon careful analysis. Electromagnetic measurements cannot detect this kind of dark matter since it interacts mostly via gravity and does not produce, absorb, or reflect light. Gravitational lensing, galaxy cluster dynamics, galaxy rotation curves, and the cosmic microwave background are all separate pieces of evidence that point to the existence of dark matter. They provide strong evidence for its presence, even if it cannot be seen with the naked eye. Continuous efforts are being made to directly detect dark matter particles by subterranean experiments that aim to protect other particles that might potentially imitate dark matter signals. Although there has been no proven direct discovery as of yet, these investigations are helping to refine the possible characteristics of dark matter particles. Dark matter theories and models are still developing, with sterile neutrinos, WIMPs, and axions being some of the most explored options. When it comes to dark matter interactions and potential detection methods, each of these contenders has unique consequences. One of the biggest unanswered questions in contemporary physics is dark matter. To fully grasp the makeup and development of the cosmos, one must comprehend its nature. With any luck, the real composition of this enigmatic molecule will be revealed as study progresses. Cosmic structures were formed in large part by dark matter in the early cosmos. Dark matter existed in the early cosmos, but it had no effect on the visible stuff at that time. The cosmos was hot and dense. The dominance of dark matter in the gravitational field emerged when the cosmos cooled and expanded. Dark matter may easily condense under its own gravity since it is unaffected by electromagnetic forces and light. The large-scale structures we see now originated from these clusters of dark matter. The first stars and galaxies were formed as a result of their gravitational attraction, which attracted gaseous hydrogen and helium. Overcoming the pressure of hot gas in the early cosmos was made possible by dark matter. Its gravitational pull was crucial in compressing the gas into the dense areas that sparked star formation. Otherwise, the gas would still have been too dispersed. Dark matter's impact at this time may be better understood by analyzing cosmic microwave background radiation. Minor changes in density and temperature detected by observations point to areas where dark matter has started to cluster and impact the distribution of normal matter. Over time, these initial dark matter clusters expanded, merged, and eventually formed even bigger structures. Galaxies, galaxy clusters, and the enormous cosmic web as we know it now all originated from this hierarchical process of creation. Additionally, computational models corroborate the function of dark matter in the early cosmos. The critical significance of dark matter in cosmic history is shown by models that include it, which faithfully reflect the observed distribution of galaxies and large-scale structures. The cosmos was ionized by the light and radiation of the earliest stars that emerged from dark matter halos. The cosmic dark ages came to a close during this ionization period, which also had an impact on how the universe developed and expanded. Supermassive black holes were not formed in a vacuum. Dark matter was also involved. These enormous objects, located at the heart of the vast majority of galaxies, grew rapidly in the dense surroundings of dark matter halos. Cosmic webs are based on how dark matter was distributed in the early cosmos. A large-scale structure was formed when filaments of dark matter linked galaxy clusters, directing the development of galaxies along these filaments. Cosmic structures have evolved from their beginnings to the present day, and scientists may track this history with the assistance of dark matter in the early cosmos. It connects the Big Bang's original circumstances to the complicated cosmos we see today. More and more, scientists are keeping an eye on dark matter in the hopes of learning more about its characteristics and how it affected the early universe. The cosmic microwave background and galaxy distribution studies allow astronomers to hone their models and hypotheses. The existence of dark matter is still a mystery, but the impact it has on gravity is obvious. Its early cosmic existence was pivotal in defining the cosmos, impacting events as diverse as star formation and the universe's overall structure. The characteristics of dark matter will be further investigated in future missions and experiments, perhaps with the use of more sophisticated telescopes and detectors. The goal of these endeavors is to learn more about its characteristics and interactions so that we may better understand its place in the evolution of the cosmos. The impact of dark matter in the early cosmos demonstrates its significance in the development of the cosmos. A whole picture of the history, present, and future of the universe cannot be constructed without first elucidating the nature of dark matter, which is why astrophysics study on this topic is ongoing and crucial. Dark matter has a huge impact on how the universe's structures are formed. The early density variations were greatly influenced by the gravitational pull of dark matter, which ultimately led to the intricate structures that we see today. Minor fluctuations in dark matter density started to expand in the early cosmos as a result of gravity. These disturbances sowed the seeds for all later structure creation, leading to denser areas that would subsequently give rise to galaxies and clusters. These density peaks were surrounded by dark matter halos, which laid the gravitational groundwork for the accumulation of baryonic matter, also known as normal matter. These halos guided the distribution and development of galaxies, acting as cosmic scaffolding. The earliest galaxies and stars were born from cooled and condensed gas that fell into dark matter halos. These structures wouldn't have formed as quickly if dark matter hadn't acted as a gravitational force. The speed at which structures were built was likewise affected by dark matter. It accelerated structure formation compared to when matter alone was at work by amplifying gravitational pull. The universe as a whole evolved more rapidly as a result of this. Just ordinary stuff. The universe as a whole evolved more rapidly as a result of this. In the hierarchical model of structure development, dark matter dynamics drives the merging of smaller structures to produce bigger ones. From more compact initial galaxies and clusters, bigger ones emerged when dark matter halos expanded and fused. The cosmic web, an expansive network of filaments and gaps that extends throughout the cosmos, is intricately related to the dispersion of dark matter. Dark matter influences the large-scale structure of the universe, and galaxies are located along these filaments where the quantity of dark matter is strongest. As a result of gravitational lensing, dark matter is able to directly demonstrate its impact on structure development by bending light from faraway objects. Astronomers may learn more about dark matter and its role in creating cosmic architecture by analyzing lensing effects. Galaxy clusters, the biggest formations in the universe that are bound by gravity, are not immune to the gravitational pull of dark matter. The galaxies included inside these clusters are held together, and their movements are impacted by the enormous quantities of dark matter that they contain. There is a connection between dark matter and the expansion of supermassive black holes in galactic centers. The fast accretion of stuff onto these black holes is influenced by their development, which is facilitated by the dense surroundings inside dark matter halos, the buildup of materials on these black holes, which affects how they evolve. Dark matter left a mark on the early cosmos, according to observations of the cosmic microwave background. As a result of dark matter's shaping, the large-scale patterns we see today evolved from small-scale density disturbances, and these changes in the CMB's temperature reflect them. To fully grasp how galaxies come to be, one must also consider the function of dark matter in the construction of structures. Galaxies take on their forms, sizes, and distributions as a result of interactions between baryonic and dark matter, which govern their creation and development. The observable large-scale structure of the cosmos is faithfully reproduced in simulations of cosmic history that include dark matter. Researchers get a better grasp of the mechanisms influencing structure development and the impact of dark matter on the universe via these simulations. How dark matter affects structure development is an area that will be further explored in future experiments and observations. Dark matter's characteristics and interactions may be better understood by examining its distribution and behavior, which in turn might provide light on its place in the cosmos. To provide a whole picture of cosmic development, one must comprehend the role of dark matter in structure building. From the beginning of time till now, its gravitational pull has molded the cosmos, propelling the creation of galaxy clusters and the enormous cosmic web. A major obstacle in contemporary physics is the direct detection of dark matter. The characteristics of this enigmatic material are being investigated using a variety of techniques. Direct detection experiments are one main method. The goal of these studies is to discover how dark matter and ordinary matter interact with one another. To avoid interference from cosmic rays and other sources, they often take place at great depths below. One of the most important technologies in direct detection is the cryogenic detector. In order to detect the minuscule amount of heat generated when a dark matter particle collides with an atomic nucleus, they function at very low temperatures. Xenon and argon liquid noble gas detectors are another option. The interaction between these materials and dark matter particles results in the detection and analysis of scintillation, light, and ionization signals. Another tool used by scientists is the bubble chamber, which can convert superheated liquid to gas using the energy released by a collision of dark matter particles. This change produces observable, quantifiable bubbles. The products of dark matter disintegration or annihilation are the primary targets of indirect detection techniques. Space and ground-based observatories can detect gamma rays, neutrinos, and other particles produced by the annihilation of dark matter particles. In areas where dwarf spheroidal galaxies and the core of our galaxy are thought to have substantial dark matter, gamma-ray observatories, like the Fermi Gamma-Ray Space Telescope, look for areas with an excess of gamma-ray emission. Detectors of high-energy neutrinos, like IceCube in the South Pole, seek for these particles as a potential byproduct of interactions with dark matter. In order to record and analyze neutrino signals, these detectors use massive amounts of ice or water. And further technique for finding dark matter is gravitational lensing. Astronomers may map the distribution of dark matter and deduce its existence in galaxies and clusters by analyzing how it bends light from distant objects. The distribution of dark matter, as measured by its gravitational effects, may be better understood by large-scale studies of galaxies and galaxy clusters. The data gathered from these studies is essential for determining how dark matter contributes to the development of cosmic structures. The Large Hadron Collider and other particle accelerators use high-energy collisions to try to produce dark matter particles. Scientists are aiming to create dark matter by colliding protons at almost the speed of light, and then studying the particle showers that occur to identify its effects. Cosmic microwave background radiation and other astronomical data provide circumstantial evidence for the existence of dark matter. The circumstances of the early cosmos and the role of dark matter in cosmic development may be better understood with the help of these findings. Enhancing the sensitivity of dark matter detection is a future goal of both experiments and technology. We will be able to hunt for dark matter particles more effectively thanks to projects like the Deep Underground Neutrino Experiment and planned enhancements to current detectors. Many branches of science are working together in the hunt for dark matter. These branches include cosmology, particle physics, and astrophysics. Scientists want to construct a complete picture of dark matter by integrating data from different sources. Innovation and discovery are being propelled by the ongoing search to identify dark matter, despite the hurdles. Discovering dark matter's nature is becoming a more realistic aim as a result of scientific progress and technological advancements. Doing so would provide crucial clues about the universe's inner workings. The characteristics and actions of dark matter are the subject of several theories and models. Experimental searches and observations may be better interpreted with the use of these theoretical frameworks. In the search for dark matter, the weakly interacting massive particle, WIMP, is among the most prominent contenders. Weakly interacting massive particles, WIMPs, are thought to communicate with one another via the WIMP. It is believed that WIMPs interact via the weak nuclear force. Thus, they are hard to detect but might explain the observed dispersion of dark matter. Another conceivable contender is axion. Light and weakly interacting with matter, these hypothetical particles exist only in theory. Originally postulated to address issues with quantum chromodynamics, they are now being pondered as a potential candidate for dark matter. The interaction between sterile neutrinos is much less than that between ordinary neutrinos. A portion or even all of the universe's dark matter might be explained by sterile neutrinos, should they really exist. Every standard model particle is expected to have a companion particle according to the supersymmetry hypothesis. Potential candidates for dark matter might be some of these supersymmetric particles, such as the neutral lino. Dark matter, according to the extra-dimensional hypothesis, might be an expression of particles interacting in dimensions beyond our own. New insights into dark matter's nature are provided by this concept, which expands upon the mainstream paradigm. According to theories that account for self-interacting dark matter, a new force allows dark matter particles to communicate with one another. The density patterns of galaxies and galaxy clusters are among the data that might be explained by this interaction. According to warm dark matter theories, the velocities of dark matter particles are tiny yet non-zero. In contrast, particles in the cold dark matter concept travel at very modest speeds. Possible solutions to problems with cosmic structures on a microscopic scale may lie in warm dark matter. An alternate hypothesis that alters the rules of gravity to accommodate the impacts thought to be caused by dark matter is known as modified Newtonian dynamics, or MOND. Even though it's contentious, it offers a new way of looking at galaxy rotation curves. The interplay between dark energy and dark matter is a central theme in theories that attempt to explain the cosmos. The goal of these models is to bring our knowledge of dark matter and dark energy together. The distribution of dark matter in clusters and galaxies may be described using halo models. The distribution of dark matter and its effects on visible matter may be predicted using observational data by these theories. Lambda cold. Dark matter, LCDM, is the de facto cosmological standard model. It encompasses cold dark matter and dark energy, offering a framework that clarifies the distribution of galaxies, the cosmic microwave background, and the universe's large-scale structure. In order to mimic the known cosmos, dark matter models are used in simulations of the genesis of cosmic structures. Incorporating dark matter dynamics, these models foretell how clusters of galaxies and the cosmic web came to be. Emergent gravity and other competing hypotheses suggest that Arachi is affected by dark matter via changes to gravity itself, not by invisible particles. These hypotheses provide fresh perspectives on cosmic occurrences and cast doubt on long-held paradigms. New particles, which may be candidates for dark matter, are predicted to exist by string theory, which seeks to unify all basic forces. String theory's intricate mathematics give rise to these particles, which are called stringy dark matter. To improve these models and hypotheses, physics, astronomy, and cosmology must continue to work together. One of science's biggest mysteries, dark matter, is getting closer to being solved with every new observation and experiment that adds to our knowledge of it. The connection between the distance and velocity of galaxies is described by Hubble's law, a basic finding in cosmology. According to this rule, the distance from us to galaxies increases as their speed decreases. In the 1920s, Edwin Hubble found this connection. His measurements of the redshift of light from faraway galaxies showed that the distance from Earth was increasing, while the distance from nearby galaxies was decreasing. As the cosmos expands, the wavelength of light extends, causing redshift. Light is pushed closer to the red end of the spectrum as a result of this stretching. A higher redshift indicates that the galaxy is receding from Earth at a quicker rate. A galaxy's velocity, v, the Hubble constant, h0, and the distance to the galaxy, d, are the mathematical components that make up Hubble's law. The expansion rate of the cosmos may be measured using the Hubble constant. The finding of Hubble's law bolstered the case for the Big Bang hypothesis. Evidence of cosmic expansion suggests a denser, smaller cosmos in the past. One important aspect of our present cosmological knowledge is this expansion. Several observations have helped to fine-tune the value of the Hubble constant throughout the years. The size, age, and ultimate destiny of the cosmos may be uncovered with precise measurements of the Hubble constant. Spectral lines of elements in galaxies are seen to provide redshift values. A direct method of measuring the velocities of distant galaxies is provided by these lines, which move towards longer wavelengths. All of the universe's large-scale structure is subject to Hubble's law, not only galaxies. Astronomers are able to better comprehend the mechanics of cosmic expansion and create maps of galaxy distributions with its assistance. Cosmological redshift, which is driven by the expansion of space itself, is another notion that follows from the idea of redshift. Objects' relative velocity in space causes the Doppler shift. This is different. We learned about the universe's accelerating expansion via measurements of redshifts and distances taken from observations of faraway supernovae. Dark energy, an enigmatic factor propelling the expansion, is thought to be responsible for this quickening. Thanks to research into redshifts and Hubble's law, the cosmic distance ladder was born. To improve the accuracy of cosmological models, this approach integrates several distance measuring methods to estimate distances to distant galaxies. Also, according to Hubble's rule, the cosmos does not revolve around a central point. Every single point in the cosmos seems to be receding from every other point in the universe, since the expansion seems to be uniform in all directions. Redshift measurements are becoming more precise with the development of better telescopes and observational methods. Cosmologists are able to put their hypotheses about the expansion of the universe and the mechanics behind it to the test thanks to this continuous improvement. Redshift and Hubble's law are cornerstone ideas in cosmology. The growth, structure, and forces shaping the history of the cosmos on a grand scale may be better understood with their help. We will keep digging into the ramifications of redshift and Hubble's law in future studies. Researchers want to learn more about dark energy, the universe's ultimate destiny, and the basic rules of physics by delving farther into the expansion of the cosmos. We can learn about the early cosmos from observations of faraway galaxies. Astronomers may deduce information about the processes and circumstances that molded the universe billions of years ago by analyzing these galaxies. Because light travels at a fixed speed, distant galaxies seem to be the same as they were throughout the early cosmos. We can glimpse further into the past when we see galaxies that are farther away because it takes more time for their light to reach us. Our knowledge of faraway galaxies has been completely transformed by telescopes such as the Hubble Space Telescope. Thousands of galaxies, some of which originated as recently as a few 100 million years after the Big Bang, are shown in Hubble's deep field photos. These findings demonstrate that early galaxies had less structure and lower sizes compared to the ones seen today. They are constantly expanding and contracting, so they seem like clumps of stars and gas. Astronomers can find the redshifts of distant galaxies by studying their light. Galaxies with high redshifts are very distant and have had their light distorted by cosmic expansion. When looking at faraway galaxies, spectroscopy is an essential instrument. Scientists may learn a lot about the physical characteristics, chemical makeup, and star formation rates of these galaxies by studying their spectra. Exoplanet observations have shown that enormous black holes were present in the early cosmos. extremely brilliant quasars, powered by these black holes, may even outshine the galaxies that house them. Quasars are great for learning about the Big Bang and the early cosmos. Their blazing brightness may shed light on the intergalactic medium and the ionization process that ended the cosmic dark ages by illuminating the gas around them. Another essential tool for examining faraway galaxies is gravitational lensing. Clusters of galaxies and other massive objects may enhance the visibility of fainter galaxies in the background by bending and magnifying their light. Lens-ed galaxies provide a rare chance to see features that would be indistinguishable with unaided vision. As a result, astronomers are better able to examine distant galaxies for their structure and development. Our capacity to study faraway galaxies will be greatly enhanced by infrared observatories such as the James Webb Space Telescope. Through the use of infrared light, locations that would normally be hidden by dust clouds may have their star formation processes revealed. The study of faraway galaxies is also greatly assisted by radio telescopes. Insights into the mechanisms that drive galaxy development may be gained by detecting emissions from cold gas, the basic ingredient for star formation. We learn more about the history of galaxy creation and development from observations of faraway galaxies. We learn more about the assembly and evolution of galaxies thanks to their testing of theoretical models and simulations. The cosmic architecture at enormous scales is also illuminated by these findings. The dispersion of faraway galaxies may be used to explore the cosmic web and how dark energy and dark matter impact galaxy formation. Research into other galaxies will keep yielding fruitful results so long as our technology keeps improving. The complex processes that have molded the universe over billions of years are becoming better understood with each new observation, which in turn improves our knowledge of the universe's beginnings and history. A watershed point in cosmology came with the revelation that the cosmos is expanding at an exponential rate. This surprising discovery provided further evidence that the expansion of the cosmos is both ongoing and accelerating. The most compelling evidence of this acceleration is provided by studies of faraway type Ia supernovae. The inherent brightness of these supernovae is well known. Thus, astronomers may use them as standard candles to determine their distances with precision. Distant supernovae were found to be less bright than anticipated in the late 1990s by two separate study groups, the Supernova Cosmology Project and the High-Z Supernova Search Team. This suggested that they were less bright than anticipated. This meant that their distance was greater than what could be expected by universe decelerating theories. It was impossible to avoid the conclusion. The speed at which the cosmos is expanding is increasing. This quickening points to the existence of an enigmatic force, which is now recognized as dark energy, accounting for around 70% of the entire energy content of the cosmos. Theoretically, dark energy acts as a repellent, balancing out the attracting cosmic force of gravity. Despite several hypotheses, none of which have been proven, its precise nature is still a major enigma in the physical sciences. An old idea, the cosmological constant, first put out by Albert Einstein, is being considered again in the quest to shed light on dark energy. The cosmological constant stands for the uniformly filled space with a constant density of energy. Here it is a kind of dark energy that propels the acceleration. Dark energy, according to several competing hypotheses, might be a field that changes across space and time. Dark energy may really be a field that changes with the passage of time and different locations. Dark energy's characteristics may undergo changes as the cosmos develops, according to these quintessence theories. The ramifications for the universe's destiny are enormously significant, given the recent finding of accelerated expansion. The cosmos will become colder and darker as galaxies distance themselves from one another at an ever-increasing pace if the expansion doesn't slow down. The cosmos's grand architecture is changed by the acceleration. It affects the long-term evolution of galaxy clusters and other cosmic formations by affecting their development and growth. The cosmic microwave background, CMB observations provide credence to the idea that expansion is speeding up. Thorough evaluations of the CMB's variations are in agreement with a dark, energy-dominated cosmos. Sloan Digital. Sky Survey and the Dark Energy Survey are two examples of large-scale galaxy surveys that study the distribution of galaxies over huge distances. The impact of dark energy on the growth and structure of the cosmos may be better comprehended with the use of these maps. We learn more about dark energy from gravitational lensing investigations as well. Astronomers can deduce the distribution of dark matter and the impact of dark energy on the geometry of the universe by studying the bending of light from faraway galaxies. Dark energy is set to be the focus of future missions, such as the NASA Wide Field Infrared Survey Telescope and the European Space Agency's Euclid probe. The distribution of dark matter and the rate of cosmic expansion will be better measured by these missions. One of the most pressing questions in contemporary cosmology is how the universe is expanding at an ever-increasing rate. We are getting closer to solving one of the most fundamental scientific riddles as we combine data from different wavelengths and methodologies in our quest to discover the nature of dark energy. Our understanding of the universe has been completely transformed by the revelation of rapid expansion. It motivates continuous attempts to understand the basic forces determining our cosmic fate and emphasizes how much more there is to discover about the cosmos. Among cosmology's most fascinating ideas is dark energy. One possible explanation for the universe's rapid expansion is this kind of energy, which is thought to be present in every corner of the cosmos. In contrast to dark matter, which interacts via gravity, dark energy seems to be repulsive. It operates as a counterforce to gravity, which speeds up the expansion of the cosmos. The idea of dark energy was put up to account for faraway supernova sightings that pointed to the acceleration of the expansion of the cosmos. This finding cast doubt on earlier theories that predicted expansion should be reducing in speed as a result of gravity. The cosmological constant, a concept first suggested by Einstein in his general relativity equations, might be one explanation for dark energy. A uniformly dense energy field, represented by the cosmic constant, fills all of space. If dark energy is a constant in the cosmos, then the energy density of the vacuum doesn't change with time, even while the universe becomes bigger. If this is so, then the weaker the cosmos is, the more powerful the effect of dark energy becomes. An alternative explanation is that dark energy may function like a scalar field, in that it is constantly changing. This theory, called quintessence, suggests that dark energy's characteristics may evolve with time, possibly impacting the destiny of the universe in a manner distinct from a cosmological constant. Direct proof for dark energy may be found in observations of galaxy clusters, large-scale structure, and the cosmic microwave background. Theoretical models and its characteristics are both aided by these findings. Nearly 70% of the energy in the universe is dark energy, much more than any other component, including dark matter and regular matter. To get a full view of the universe, one must know what it is. The Hubble constant, which quantifies the rate of expansion, reveals the impact of dark energy on the expansion of the cosmos. The relative contributions of dark energy and other cosmic components may be better understood with the use of precise Hubble constant measurements. Additionally, dark energy modifies the cosmos's shape. Space is stretched by its repulsive force, which affects light trajectories and the creation of large-scale structures. We can see this stretching effect in galaxy distributions and cosmic microwave backgrounds. A deeper dive into dark energy is the goal of forthcoming experiments and observations. New information on the expansion of the universe and the behavior of dark energy throughout time will be revealed by missions such as Euclid and the James Webb Space Telescope. Dark energy is a mystery that basic physicists and cosmologists alike are trying to unravel. The comprehensive explanation of its features and implications may need the development of new theories or revisions to general relativity. Finding dark energy might change the universe's destiny in significant ways. A bleak, lonely future looms on the horizon if dark energy stays the same or perhaps grows. The cosmos may keep expanding indefinitely. On the other hand, other outcomes may result from a dynamic dark energy, such as a huge rip, in which the expansion is so intense that atoms, galaxies, and stars are ripped apart. A thriving area of research is the study of dark energy. To To solve the riddles of this mysterious force that is speeding up the expansion of the universe, it integrates observational astronomy with theoretical physics and state-of-the-art computer models. Despite its importance, our understanding of dark energy is limited. New understandings of space, time, and the cosmic forces behind them are sure to emerge as scientific inquiry continues. Observational, experimental, and theoretical methods are all being used in the present investigation of dark energy. The features of this object and its effects on the universe remain a mystery to scientists. From an observational standpoint, comprehensive surveys of the cosmos are crucial. In order to learn how dark energy influences the grouping and evolution of galaxies, projects such as the Dark Energy Survey survey their distribution. The European Space Agency's Euclid project is to study the universe's geometry in an effort to deduce the properties of dark energy. Important information on the expansion of the universe will be gleaned from its measurements of the sizes and shapes of billions of galaxies inside the cosmos. Important information on the expansion of the universe will be gleaned from its measurements of the sizes and shapes of billions of galaxies. Additional support for studies of dark energy will come from the James Webb Space Telescope. Thanks to its infrared capabilities, it will be able to see further into the past, studying the origin and development of the first galaxies and how dark energy affected them. Large synoptic survey telescope and other ground-based observatories will be able to capture the night sky with a great degree of detail. These pictures aid in monitoring the motions and changes in the forms of galaxies, which in turn illuminate the consequences of dark energy. Another way to go about it is using gravitational wave detectors like Virgo and LIGO. Scientists are hoping to learn more about dark energy by looking at the expansion of the cosmos via gravitational waves. In an effort to shed light on dark energy, theoretical physicists are creating novel models. To accommodate cosmic acceleration, some argue that our current understanding of gravity may need revisions to general relativity. According to quintessence theories, dark energy may be a field whose characteristics evolve across time. In order to determine whether these theories can account for the observed acceleration of the cosmos, they are compared against observational evidence. The potential impact of additional dimensions on dark energy is being considered by certain academics. Dark energy may arise from interactions in these unknown dimensions, according to string theory and other higher dimensional ideas. Examples of dark energy potentially exchanging energy with dark matter are crucial to the idea of interacting dark energy. What these interactions may reveal about the nature of the two dark sides of the cosmos is anyone's guess. Cosmic acceleration may be better understood in light of competing gravity theories, such as scalar tensor theory or free relativity gravity. These hypotheses generate effects analogous to dark energy by modifying the general relativity equations. A suitable setting for investigating dark energy is the vast empty space between galaxy clusters, which is known as a cosmic vacuum. The behavior of galaxies in relation to these gaps may be used to restrict theories of dark energy. The Dark Energy Spectroscopic Instrument, DESI, and similar studies are now mapping the 3D distribution of galaxies in order to quantify the expansion history of the universe. Our knowledge of dark energy's function throughout cosmic history will be enhanced by this intricate map. Models of the function of dark energy during cosmic history. Researchers are able to foretell the effects of various hypotheses on the large-scale structure by simulating the cosmos with dark energy. Analyzing observational data and improving theoretical models are both aided by these simulations. Researchers in the field of dark energy must work together, spanning different fields and even different countries. To better understand this enigmatic force, scientists are integrating knowledge from computer modeling, theoretical physics, and observational astronomy. The long-term objective of the ongoing study is to include dark energy into a comprehensive understanding of the cosmos. If we can decipher dark energy, we will have solved one of the greatest riddles in cosmology and may have a whole new perspective on basic physics and reality. The intricate arrangement of matter in the cosmos is shown by the cosmic web, a broad system of linked structures. It is made up of intergalactic gas, galaxy clusters, and individual galaxies connected by dark matter filaments. At hundreds of millions of light-years in length, these filaments dwarf all other cosmic formations now understood. They interconnect dense matter nodes, like as clusters and galaxies, in a manner reminiscent of a web. Matter collapsed under the force of gravity over a period of billions of years, creating the cosmic web. A key component of this process was dark matter, which drew regular matter into these filamentary formations by its gravitational attraction. Galaxy surveys and gravitational lensing are two of the many methods used to observe the cosmic web. Astronomers are able to chart the distribution of stuff on the biggest scales using these approaches. The cosmic web's strands aren't all the same. They include varying densities and compositions of cosmic gas and dark matter. Excessive heating of this gas makes it observable in X-ray measurements. Galaxy formation and evolution take place within the filaments. We see such a wide diversity of galactic structures because these dense settings may cause star formation and impact galaxy expansion. At the points where these filaments meet, you may find galaxy clusters, which are among the largest formations in the cosmos. As gravitational centers, these nodes increase the mass and complexity of the filaments around them by absorbing matter from those filaments. Investigating the cosmic network helps us understand the big picture of how the universe has evolved. The distribution of matter on these massive scales provides insight into the fundamental laws of the cosmos. An important part of this study is the use of cosmic web simulations, which represent the development and dispersion of matter. They compare various cosmological theories' predictions of the web's appearance with actual data and contribute to these predictions. A key element of the cosmic web is the intergalactic medium, which is the space between galaxies inside the filaments. As a crucial component in the gas cycle process, it houses the vast bulk of the universe's baryonic matter. Galaxy motion is also affected by the cosmic web. Cosmic flow describes the general trend of galaxies along filaments towards densest areas. Interactions and mergers between galaxies may be impacted by this motion. The universe's web is supported by dark matter. From the tiniest galaxies to the biggest clusters, its gravitational pull determines how matter is distributed and how these structures are formed. Findings on the primordial circumstances that gave rise to the cosmic web have been uncovered via observations of the cosmic microwave background. Our modern, large-scale cosmic structures evolved from far smaller ones in the early cosmos. As galaxies grow, fuse, and travel within the cosmic web, its structure is continually shifting. Researchers may learn more about the universe's past and future by observing its progression. The complex structure of the cosmos is a representation of how everything in the universe is linked to everything else. In doing so, it lays the groundwork for comprehending the universe's structure at the cosmic scale and draws attention to the part dark matter plays in this process. One of the biggest things in the cosmos is a supercluster. They are large areas of the cosmic web made up of clusters of galaxies that are gravitationally bonded together. Hundreds of millions of light-years in diameter, these superclusters may house thousands of galaxies. To comprehend the universe's structure on a grand scale, one must go no further than these densest areas, which they symbolically depict. Superclusters started to develop just after the Big Bang. Over time, these enormous structures were formed as a result of gravitational pull attracting matter, which expanded from small density variations in the early cosmos. Galaxy clusters are the main building blocks of superclusters. Gravity holds hundreds or thousands of galaxies, molten gas, and dark matter in these clusters. Among the most famous superclusters is the Sloan Great Wall. It is one of the biggest known structures in the cosmos, stretching approximately 37 billion light-years. The antithesis of superclusters are voxels. These huge, empty spaces are the universe's least dense, with hardly any galaxies to be found there. Voids may stretch hundreds of millions of light-years and be as massive as superclusters. A cosmic web structure is formed by the presence of gaps, which contrast with the dense areas of superclusters. The distribution of voids and superclusters provides a picture of the universe's large-scale structure. Voids do not contain nothing. Although they do include intergalactic gas and dark matter, their density is far lower than that of superclusters. Isolated and different from galaxies in denser areas, the few galaxies seen in voids are often rather rare. Researchers in the field of astronomy learn more about the distribution of stuff in the cosmos via studying voids. The architecture of the universe and the characteristics of dark energy may be better understood by studying voids. One may analyze cosmic evolution using superclusters and voids as a framework. They show how dark energy, matter, and gravity have affected the expansion and clustering of matter over billions of years. Galaxy motion is impacted by the interplay of superclusters and voids. A phenomenon that influences the dynamics of the cosmos is the tendency of galaxies to migrate from voids to the denser areas of superclusters. Using cosmic microwave background measurements and large-scale galaxy surveys, superclusters and voids are seen. Accurate models of the cosmos may be built with the use of these data. When dark energy and matter are included in cosmic simulations, the known distribution of voids and superclusters is reproduced with high accuracy. If we want to evaluate cosmological theories, we need these simulations. At more than 10 billion light-years in length, the Hercules Corona Borealis Great Wall is the biggest known supercluster. This kind of discovery keeps expanding our horizons in terms of how big and complicated the cosmos is. To fully grasp the vastness and complexity of the cosmos, knowledge of superclusters and voids is essential. To get a whole view of the cosmos, one must understand voids and superclusters. They stand for the most congested areas and the most empty spaces in the universe, respectively, and they show how diverse and expansive the universe is. Modern astronomical observational methods have allowed us to probe the cosmos with a level of precision never before seen. A wide range of objects, from neighboring planets to faraway galaxies, may be studied using these methods. In observational astronomy, the optical telescope is a key instrument. The use of optical telescopes has allowed for the thorough study of astronomical objects such as galaxies and stars by collecting and enhancing the visible light emitted by these objects. Items enabling in-depth examinations of celestial bodies, galaxy clusters, and other occurrences. Celestial objects' radio waves may be picked up by radio telescopes. Pulses, quasars, and the cosmic microwave background may be seen by these telescopes in visible light, which allows them to study regions of space that are hidden by dust. Since infrared radiation may pass through clouds of dust that absorb visible light, infrared telescopes are able to detect this kind of light. The study of star formation areas and galactic centers relies on this capacity. Space telescopes, such as the Hubble Space Telescope, are able to capture pictures of the universe that are crisper and more detailed, because they are not affected by Earth's atmosphere. From ultraviolet to infrared, space-based observatories may work throughout a spectrum of wavelengths. The light emitted by astronomical objects may be studied using spectroscopy. As light is separated into its many hues, astronomers are able to learn more about the stars and galaxies, including their composition, temperature, and velocity. A galaxy cluster or other large object's gravity may cause an effect known as gravitational lensing, wherein light from objects further away is bent and magnified due to the object's bulk. Because of this occurrence, astronomers are able to examine the distributions of dark matter in galaxies that are very far away. Adaptive optics is a system that instantly corrects for atmospheric distortion. This method improves the sensitivity of terrestrial telescopes, enabling them to capture pictures on par with their space-based counterparts. The goal of interferometry is to produce a higher resolution picture by merging the signals from several telescopes. Radio astronomy and, to a lesser extent, optical and infrared astronomy make use of this method. One way to track the brightness of the night sky is via photometry. The study of exoplanets, variable stars, and other ephemeral cosmic phenomena relies heavily on this method. By monitoring the tiny reduction in a star's brightness when a planet moves in front of it, transit photometry may identify exoplanets. We now know more about planetary systems because to this technique, which has uncovered thousands of exoplanets. Astrometry is the exact science of measuring the locations and trajectories of heavenly bodies. This method is useful for calculating stellar distances, planetary orbits, and galaxy and cluster dynamics. The most powerful events in the cosmos, such neutron stars, black holes, and supernovae, generate gamma rays and X-rays, which high-energy telescopes study. We learn more about the harsh space environment from these observations. Celestial phenomena, including supernovae, variable stars, and active galactic nuclei, are studied in time-domain astronomy because of their dynamic nature. In order to record fleeting occurrences, this sector depends on constant surveillance. Massive speeding objects, like as neutron stars and merging black holes, generate ripples in space-time, which gravitational wave observatories like Virgo and LIGO are able to detect. The most violent events in the universe may now be better understood thanks to these findings. Astronomers may construct a complete picture of the cosmos by integrating several observational methods. Understanding cosmic occurrences and the basic rules of the universe is enhanced by the distinct insights provided by each technique. Contemporary astronomy makes extensive use of computer simulations. Their use paves the way for the modeling and understanding of cosmic phenomena that would be very difficult, if not impossible, to witness firsthand. From the Big Bang all the way up to the current day, simulations can mimic the early universe's circumstances and show how galaxies formed and evolved. Cosmological evolution, dark matter, and dark energy ideas may be tested using these models. As far as simulations go, the Millennium simulation is among the most famous. It fits the distribution of galaxies and galaxy clusters with the effects of dark energy and dark matter, and simulates the creation of large-scale structures in the universe. The behavior of certain galaxies may also be investigated using simulations. Scientists may learn more about spiral arms, galactic collisions, and supermassive black hole evolution by simulating the gravitational interactions of gas, dark matter, and stars. Researchers may explore star formation, supernova explosions, and the interstellar medium with hydrodynamic simulations, which include the behavior of gas and fluids into the models. The evolution of galaxies and stellar life cycles can only be uncovered via these simulations. Extensive computing power is needed for cosmological simulations. It might take weeks or months for a single simulation to execute on a supercomputer, which can do quadrillions of computations per second. Massive simulations like the Illustris project also exist, incorporating complicated physics like star formation, black hole development, feedback from supernovae, and active galactic nuclei. It predicts the evolution and creation of galaxies. When it comes to investigating dark matter, simulations are equally vital. Dark matter may be predicted and its distribution compared with observations by simulating its interactions with normal and self-interacting matter. Scientists may learn more about the intra-cluster medium and the interactions between galaxies via galaxy cluster simulations. With the use of these models, we can learn about star formation, gas removal from galaxies, and the evolution of star clusters. The study of exoplanets relies on computer simulations to make educated guesses about the weather and atmospheres of other planets in the universe. Planets' habitability may be inferred by simulating their atmosphere, rotation, and orbital characteristics. Scientists may put many cosmological ideas to the test by simulating the cosmic microwave background radiation. Researchers may learn more about the early cosmos and how it evolved by comparing computer-generated cosmic microwave background (CMB) maps with actual observations. Black hole and neutron star mergers may be modeled using gravitational wave simulations. In order to better understand the signals picked up by LIGO and Virgo, among others, researchers rely on these models to forecast the gravitational wave waveforms. The study of the universe's structure at enormous scales is further aided by simulations. Researchers may learn about the cosmic web's creation and dark energy's role in its development by simulating the distribution of galaxies and dark matter. Scientists may try out different observational tactics and equipment designs in virtual observatories built via simulations before deploying the real thing. This method improves data quality by maximizing the efficiency of telescopes and detectors. Increasing the complexity and resolution of astrophysical simulations is the way to go for the future. Simulations will involve smaller scales, greater regions of space, and more precise physics as computing power increases, allowing us to learn more about the universe's inner workings. In astrophysical research, computer simulations play a crucial role. They supplement empirical evidence, put hypotheses to the test, and illuminate the essential processes that mold the universe. When compared to observational methods, simulations allow scientists to probe the cosmos in unprecedented depths. The role of dark energy and dark matter in the expansion of the universe is enormous. From the very beginning of time till the present, these unexplained elements have molded the cosmos. The creation of the first structures in the cosmos was greatly influenced by dark matter. Cosmic dust and other cosmic objects clumped together under its gravitational influence, giving rise to the first galaxies and clusters. If dark matter didn't exist, the cosmos would seem quite different. Galaxies, stars, and planets couldn't have formed from regular stuff since it couldn't build structures fast enough. Conversely, the acceleration of the expansion of the cosmos is caused by dark energy. The expansion rate increases with time because its repulsive force opposes the attraction pull of gravity. The universe's destiny is being dictated by this race against time. A bleak, lonely future awaits us if dark energy maintains its hegemony and the cosmos keeps growing at an exponential pace. The structure of the universe at large is impacted by the interaction of dark energy and dark matter. Cosmic webs are supported by clusters of dark matter called halos, and the growth of the voids between them is driven by dark energy. Dark matter density is greatest near the cosmic web's nodes, where galaxy clusters and galaxies themselves develop. Dark matter and dark energy may be better understood by analyzing the distribution of these structures. Inside galaxies, dark matter influences the dynamics as well. The extra mass it supplies is essential for understanding galaxy rotation curves, which reveal that stars in galaxies' peripheries are moving at a higher rate than what would be predicted from visible matter alone. Cosmic microwave background radiation shows the effects of dark energy on the expansion of the universe. Thorough observations of the cosmic microwave background, CMB, show that dark energy has influenced the universe's structure and expansion trajectory. The LCDM model, the de facto cosmological standard, was developed in response to the existence of dark energy and dark matter. This model lays forth the building blocks for comprehending the development of the cosmos by describing a world that consists of regular matter, dark energy, and dark matter. Cosmic evolution models that include dark energy and dark matter faithfully mimic the known galaxy and large-scale structure distributions. Cosmological ideas may be tested and improved with the assistance of these simulations. There is evidence for dark energy-driven acceleration of expansion from observations of faraway supernovae and galaxy clusters. For a complete picture of the cosmos now and in the future, these observations are fundamental. Even at the microscopic level, dark matter and dark energy have an effect. Stars and planetary systems are shaped by dark matter, whereas clusters and galaxies are shaped by dark energy. Stars and planetary systems and dark energy influences the cluster and galaxy dynamics. As far as astrophysics is concerned, the study of dark energy and dark matter is paramount. The influence of these enigmatic components on the cosmos is still a mystery, but ongoing observations, simulations, and theoretical studies are working to solve the mystery. Gaining a comprehensive understanding of the cosmos requires delving into the role of dark energy and dark matter in cosmic development. From the very beginning of time, these elements have molded the universe, shaping both its structure and its behavior. When large stars collapse due to their own gravity, they produce black holes. This collapse happens when a star reaches the end of its life cycle, usually when it runs out of nuclear fuel. A large star's ability to withstand gravity's pull is severely limited if its fuel supply is exhausted. After the core collapses, it may become a black hole if the amount of mass left behind is high enough. The majority of black holes, known as stellar mass black holes, form when stars with masses more than 20 times the Sun's collapse. A singularity, defined as a point of infinite density surrounded by an event horizon, is produced when the core collapses. Once something crosses the event horizon, they will be completely pulled inside by the black hole's gravitational attraction. The point where the escape velocity is equal to the speed of light is marked by it. The point where the escape velocity is equal to the speed of light is marked by it. At the heart of the vast majority of galaxies are supermassive black holes, which have masses comparable to or greater than the Sun's. Although the exact mechanisms by which they came into being remain a mystery, it is believed that they expanded by absorbing gas and merging with other black holes. The detection of intermediate mass black holes, which have masses between stellar and supermassive, is more challenging. Their formation may be attributed to the direct collapse of enormous gas clouds or the merging of smaller black holes. A hypothesized type of black holes called primordial black holes might have emerged in the early cosmos as a result of changes in density. If they do in fact exist, we may learn more about the early cosmos from their characteristics. Accumulating materials from their environment allows black holes to expand. The matter spirals inward during this accretion process, creating an accretion disk. As it heats up, it emits strong radiation, which is often seen in X-rays. Black holes in binary systems have the ability to absorb matter from their partner stars. Even though black holes are invisible, this process may cause them to emit X-rays and other radiation, which can be detected. Observatories such as LIGO and Virgo are able to detect gravitational waves, which are ripples in space-time that are produced when black holes merge. Black hole mergers have been confirmed by these detections, which also provide light on their characteristics. When black holes are born, their surroundings and the initial mass and makeup of the parent star play a role. Different evolutionary pathways culminate in the development of black holes for stars located in dense star clusters or those that have binary partners. The complicated processes of black hole generation may be better understood with the use of theoretical models and computer simulations. Models like this take into account the laws of star development, supernova explosions, and gravitational collapse. Critical validation of these theories is provided by observations of black holes and their surroundings. Astronomers may improve their hypotheses and get a better knowledge of these mysterious phenomena by researching black hole characteristics and behaviors. Research into black holes goes beyond just how they develop. Because of their very strong gravitational fields, they provide one-of-a-kind test beds for physics, especially general relativity, in environments that are impossible to simulate on Earth. When it comes to the development of the cosmos and galaxies, black holes are crucial. At all sizes, cosmic structures are shaped by their gravitational effect and interactions with matter in the universe. Modern astrophysics places a premium on unraveling the mysteries of black hole genesis and evolution. It brings together the fields of cosmology, gravitational physics, and star evolution to provide a full picture of the universe's most powerful and enigmatic phenomena. A wide range of sizes and kinds of black holes exist, each with its own set of peculiarities. There are three main kinds of black holes: stellar mass, supermassive, and intermediate mass. The majority of black holes are of stellar mass, having originated from the collapse of large stars. As a rule, their masses are 3 to 10s of times that of the Sun. These supermassive black holes often coexist with partner stars in binary systems. A companion star may have its mass stripped away by a black hole's gravitational pull, creating an accretion disk that releases radiation in the form of X-rays and other waves. The Milky Way, like the majority of galaxies, has a supermassive black hole in its core. They have a huge impact on the development and dynamics of their host galaxy, with masses that are millions to billions of times greater than the Sun's. Our current understanding of how supermassive black holes come to be is incomplete. Possible mechanisms for their expansion include gas accretion, mergers with other black holes, and the early universe's huge gas clouds collapsing. A black hole is said to have an intermediate mass if its mass is between 100,000 and several 100,000 times that of the Sun. These supermassive black holes might be the result of star cluster collapse or the merging of smaller black holes. A theorized type of black holes called primordial black holes might have originated as a result of high-density fluctuations shortly after the Big Bang. Their existence, if confirmed, would provide light on the properties of dark matter and the circumstances of the early cosmos. Nothing can escape a black hole's gravitational attraction beyond its event horizon. At this time, the black hole can no longer be seen, since its escape velocity has surpassed the speed of light. A black hole's mass determines the event horizon's, or Schwarzschild's, size. This radius may be as big as the solar system for supermassive black holes, but it's only a few kilometers for star-mass black holes. The event horizon contains the singularity, an extremely dense location at which the standard physical principles are violated. One of the most enigmatic features of black holes is the singularity, which is obscured from view by the event horizon. The characteristics of black holes are changed as they spin. In comparison to Schwarzschild black holes, which do not rotate, the architecture of Kerr black holes, which do rotate, are more intricate. Both the accretion disk dynamics and the event horizon geometry are affected by the spin. Theoretically, owing to quantum processes close to the event horizon, black holes may be able to emit radiation, a phenomenon known as Hawking radiation. Due to the gradual loss of mass caused by this radiation, black holes may eventually evaporate into thin air. A new window into black hole research has opened up with the discovery of gravitational waves. Scientists are able to identify and study the hidden features of black holes via these waves, which are produced when black holes merge. How black holes interact with space-time and matter around them is dependent on their mass, spin, and charge. The production of jets, accretion disks, light bending, and gravitational waves are all affected by these features. For a complete picture of the cosmos, knowing the kinds and characteristics of black holes is essential. These mysterious things provide fresh perspectives on the structure of space-time, quantum mechanics, and gravity, all of which test our current knowledge of the physical universe. When it comes to energy and brightness, quasars are among the cosmos's most remarkable phenomena. Their propulsion comes from the very rapid assimilation of matter by supermassive black holes located in the galactic cores. The material that is falling into these black holes becomes very hot and releases a lot of radiation because of the strong gravitational pull on it. A quasar is formed in this way, and it has the potential to be brighter than all the stars in its home galaxy put together. Although quasars were first identified in the 1960s by their radio emissions, it was later revealed that they produce all electromagnetic waves, including visible light, ultraviolet, X-rays, and gamma rays. The gas and dust accretion disk that spirals toward a supermassive black hole is the driving force behind the energy production of a quasar. Powerful particle jets that reach far beyond the host galaxy may be driven by magnetic fields inside the disk. These beams have the potential to impact the intergalactic medium and even nearby galaxies as they traverse millions of light years. Galaxy development is heavily influenced by the interactions of quasar jets with their environments. Understanding the early cosmos is greatly enhanced by quasars. They serve as guiding lights that astronomers may use to investigate the cosmos from billions of years ago because of how luminous they are. A quasar's absorption lines are the result of certain wavelengths of light being absorbed as it travels through gas clouds between the quasar and the observer. The distribution and composition of matter in the early cosmos may be inferred from the analysis of these lines by astronomers. The formation of supermassive black holes may be better understood with the help of quasars. By studying the accretion disk's characteristics and the gas's velocity, one may approximate the mass of the black hole in a quasar. Quasars and the galaxies that house them have a complicated connection. A quasar's radiation and energy may affect the host galaxy's dynamics and the pace of star formation, which in turn can control the black holes and the galaxy's expansion via feedback mechanisms. Supermassive black holes are found in the heart of the vast majority of galaxies, according to quasar observations. It follows that quasars were crucial in the coevolution of black holes and galaxies. Additionally, quasars may be used to measure distances in the cosmos. Their luminosity and distinctive light curves allow us to measure cosmic distances, which aids in our comprehension of the expansion of the universe. As more sophisticated telescopes and equipment gather data, our understanding of quasars develops further. Fresh observations of quasars are being made using ever-improving technologies and telescopes. The intricate physics of quasar settings may be better understood with the help of high-resolution photography and spectroscopy. A new tool for studying these mysterious objects and their effects on galaxy history and creation might be found in gravitational waves produced by merging supermassive black holes in quasar systems. The ionization of space and time is also associated with quasars. Quasars' powerful ultraviolet light helped end the cosmic dark ages, ionize hydrogen, and provide space for light to move in the early cosmos. Acquiring knowledge about quasars' function in the expansion of the universe aids in reconstructing its past. Their immense strength allows us to see the intricate dance of matter, energy, and gravity at the most fundamental scales, providing a rare glimpse into the formation of galaxies and their center black holes. The presence and properties of quasars may be inferred from observations made using a wide range of tools and techniques. The presence and properties of quasars are derived from a wide range of techniques and tools. Our knowledge of these strong objects has been greatly enhanced by these observations. The intense radio emissions from quasars were one of the first signs of their existence. These objects were once thought to be stars. However, their radioluminosity was far too high to be stars. The fact that quasars have high redshifts, as subsequent optical observatories found out, means that they are very far away and that their light has traveled for billions of years to reach Earth. This points to quasars as potentially primordial things. Quantitative data on quasars has been uncovered using spectroscopy. They exhibit wide emission lines in their spectra, which indicate the presence of gas flowing rapidly inside the accretion disks around supermassive black holes. The whole electromagnetic spectrum, from radio waves to gamma rays, is scanned by quasars. Because it sheds light on the many processes happening in and around quasars, this multi-wavelength observation is vital. Examples of such observations include X-rays, which show the high-energy surroundings around the supermassive black hole. Chandra and XMM Newton are only two of the space telescopes that have uncovered priceless information about quasar X-ray emissions. Even though dust may block off visible light from quasars, infrared observations can see through it. Numerous quasars previously concealed by dense dust clouds have been discovered by Spitzer and other infrared telescopes. A novel approach to studying quasars has been made possible by gravitational lensing, in which the light from a farther away quasar is bent by the gravity of a large object, such as a galaxy. The quasar and the object that is focusing light on it are both illuminated by the many pictures that lensed quasars produce. Research into the polarization of quasar light has shown that these objects release jets that include magnetic fields, and that these particles are aligned. Scientists get a better grasp of the function of magnetic fields in quasar dynamics from this data. Another significant area of study is quasar variability. Observations of quasar brightness variations across timescales of days, months, or even years may provide light on the black hole's immediate surroundings and the accretion disk processes. A vast database for researching the features and distribution of quasars throughout the cosmos has been provided by the Sloan Digital Sky Survey, which has recorded hundreds of thousands of quasars. Studies of quasar evolution may be conducted statistically thanks to this enormous sample size. The Hubble Space Telescope and other high-resolution imaging equipment have resolved quasar-host galaxies, exposing mergers and interactions that might cause quasar activity. The formation and evolution of quasars may be better understood with the help of these pictures. By combining signals from several radio telescopes, radio interferometry has been able to trace the intricate structure of quasar jets. Jets impact their environment via interactions with the intergalactic medium, as shown by these findings. Observations demonstrating that quasar activity often occurs at times of high star creation in the galaxies that host them provide strong evidence of the link between quasars and galaxy development. This points to a connection between the age of galaxies and the formation of black holes. James Webb Space Telescope and other future observatories will be able to observe quasars with much greater granularity. With their superior sensitivity and resolution, these new detectors will reveal hitherto unknown facets of quasar physics. In sum, quasar observational data provides a detailed description of these unique objects. Astronomers are still trying to figure out what quasars are and how they fit into the cosmos by examining them at various wavelengths and across time. One of the most intense phenomena in the cosmos is the gamma ray burst. They are capable of releasing gamma rays that are so powerful that they may briefly outshine whole galaxies. Generally speaking, gamma ray bursts may be either long or short-lived. Massive star collapses are the usual culprits in long-duration bursts, which last longer than 2 seconds. A short-duration burst is associated with neutron star mergers and has a length of less than 2 seconds. When a large star runs out of nuclear fuel and falls into a black hole, it is believed that long-duration gamma-ray bursts would occur. A supernova explosion is set off by this collapse, which creates a jet of material traveling at almost the speed of light. The most common explanation for short-lived gamma-ray bursts is the interaction of neutron stars, either with one another or with black holes. Extreme gravitational waves and gamma-ray emissions are the results of these mergers. Due to atmospheric absorption, gamma-ray bursts can only be detected by space-based telescopes. The Swift and Fermi observatories, both operated by NASA, have identified and pinpointed hundreds of gamma-ray bursts. The X-ray, optical, and radio afterglows of gamma-ray bursts reveal a lot about the space environment around these events. As a result of afterglows, astronomers are better able to investigate the characteristics of the parent stars and locate the bursts. When looking at the early cosmos, gamma-ray bursts are crucial. The fact that certain bursts occurs at very high redshifts suggests that they occurred during the early cosmos. These long-ago explosions shed light on how the universe's initial stars and galaxies came to be. Very early in the universe's history, as shown by their extremely high redshifts, these long-ago explosions shed light on how the universe's initial stars and galaxies came to be. Because of their tremendous energy, gamma-ray bursts may alter the environment around them. Star formation and galactic development may be affected by the ionization of gas in the host galaxy caused by the high radiation. Relativity jets may also be studied in gamma-ray bursts, which act as natural labs. These bursts provide a test bed for ideas of jet formation and particle acceleration, with their highly collimated jets traveling near light speeds. New age of multi-messenger astronomy has begun with the observation of gravitational waves from neutron star mergers and gamma-ray bursts. A fuller view of these catastrophic occurrences may be obtained by combining gravitational and electromagnetic evidence. Explosions that release gamma rays may be used to study the space between galaxies. The gamma rays learn more about the universe's makeup and structure as they pass across space by interacting with the radiation and matter they encounter. Much of what we know about star development, black hole creation, and high-energy astrophysics has come from gamma-ray burst research. There are few occurrences in the cosmos as dramatic and explosive as these bursts. We hope to learn more about gamma-ray bursts with future missions like the SVOM satellite and the gamma-ray burst polarimeter that is being considered. Additional information on the characteristics of these intense occurrences may be gleaned from the more in-depth observations that these missions will give. The hunt for extraterrestrial life is another area where gamma-ray bursts might have an impact. The habitability of areas inside galaxies might be affected by the sterilization of planets by the powerful radiation from neighboring bursts. As more information on gamma-ray bursts is gathered, theoretical models are being revised. Scientists may learn more about the causes of these bursts and how they affect the cosmos by using these models. A gamma-ray burst is a stark illustration of how the universe is both active and violent. A gamma-ray burst is a stark illustration of how the universe is both active and violent. They provide light on the most inhospitable cosmic circumstances, illuminating the basic processes that mold our cosmos. Space-time is rippled by some of the universe's most powerful and violent phenomena, which are known as gravitational waves. It was in 1916 that Albert Einstein first foresaw them as a result of his general theory of relativity. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time in 2015. A new age in astronomy began with this revolutionary finding, which verified a crucial prediction of Einstein's theory. When large bodies accelerate, it causes a phenomenon known as gravitational waves. The most prevalent causes are supernova explosions, neutron star mergers, and black hole mergers. These waves contain information about their source as they travel at the speed of light. Using laser interferometry, LIGO and its European counterpart Virgo are able to detect these minute spacetime waves. With their tiny size, the detectors can detect changes in distance less than 1/1000th of a proton's diameter. The interferometer arm's lengths are slightly altered whenever gravitational waves go through the detectors. Scientists may learn about the waves' characteristics and where they came from by studying these changes. Two black holes merged around one, 3 billion light-years distant, causing the first ever gravitational wave event, GW 150914. This occurrence offered the first concrete proof of binary black hole systems. A new lens through which to study the cosmos is provided by gravitational waves. Since they are unaffected by matter, they can transmit data from the furthest, most remote corners of the universe, unlike electromagnetic waves. In multi-messenger astronomy, electromagnetic observations including light, radio waves, and X-rays are combined with data from gravitational waves. The happenings in the cosmos may be better understood using this method. Understanding the formation of heavy elements has been aided by the discovery of gravitational waves emitted by neutron star mergers, such as GBM 70817. Neutron star collisions unleash precious metals like gold and platinum into space in the form of kiloneu. When neutron stars explode, they release heavy metals like gold and platinum into space in the form of kilonovae. Additionally, gravitational waves allow us to put the basic principles of physics to the test. They provide an exceptional setting for research into general relativity in the strong field region, characterized by very strong gravitational forces. Gravitational wave observations may be used to calculate the Hubble constant, which is the rate of expansion of the universe. Scientists may improve their estimations of this crucial cosmic parameter by monitoring the redshifts and distances of gravitational wave sources. We will be able to detect these waves more effectively with future gravitational wave observatories like the LISA mission in orbit. Supermassive black hole and other exotic object mergers will be detectable by LISA because of its sensitivity to lower frequency waves. Another way to find gravitational waves is using pulsar timing arrays. In order to detect minute changes brought on by gravity waves, these arrays track the pulse timing of millisecond pulsars. Unexpected and novel occurrences may be revealed by gravitational waves. More events will be noticed, and better detection technologies will allow scientists to uncover previously undiscovered sources and processes. Gravitational wave research is changing the way we think about the cosmos. These waves open up new vistas for cosmic observation and exploration, shedding light on nature's most powerful and enigmatic forces. Our knowledge of the universe's basic mechanisms is expanding as our ability to detect and analyze these waves continues to grow. Intense radio wave bursts that last just milliseconds are called fast radio bursts, FRBs. One of the most fascinating enigmas in astrophysics, they were originally found in 2007 and have remained so ever since. It is thought that FRBs originate from sources beyond our galaxy, maybe billions of light-years distant. However, their exact origin is still mostly a mystery. They are likely created by very energetic processes because to their extraordinary brilliance and brief lifetime. A number of hypotheses have been advanced to account for FRBs, such as neutron star collapse, compact object mergers, and magnetar-neutron star-related activity. The ephemeral nature of FRBs is one of the main obstacles to researching them. Their ephemeral nature makes them challenging to identify and pinpoint using conventional radio telescopes. New radio astronomical tools as the Pathfinder Australian squarockilometry and the specialized equipment SHIME have greatly enhanced the quantity of FRBs discovered. The likelihood of detecting these evasive signals is increased by the fact that these observatories can survey vast swaths of the sky. The fact that certain FRBs tend to recur gives important hints as to where they came from. The ability to examine FRBs over longer periods of time and with more granularity makes it possible for astronomers to better understand their mechanics and identify their origins. A dwarf galaxy, located more than 3 billion light-years distant, was identified as the source of the first recurring FRB, FRB 121102. The finding provided evidence that persistent and active environments, such as those around newborn neutron stars or black holes, are linked to at least some FRBs. FRBs have potential as cosmic probes. As they go across space, radio waves interact with matter along their path. The density and nature of the intergalactic medium may be inferred from astronomical studies of these interactions. The quantity of matter that a FRB has gone through may be inferred from its dispersion measure, which shows the extent to which the signal has been scattered by electron interactions. The distribution of matter in the cosmos can be better mapped out, and distances may be estimated using this. The magnetic fields that FRBs encounter may be inferred from polarization studies. By studying the signal's Faraday rotation, which is induced by magnetic fields, one may learn about the local and line-of-sight magnetic environments. The study of dark matter might potentially benefit from FRBs. Scientists may learn more about the composition and distribution of dark matter if FRBs' signals are impacted as they travel through areas with large densities of this mysterious substance. Various theoretical theories have been proposed to explain FRBs due to their enigmatic character. Supernovae, gamma-ray bursts, and other catastrophic phenomena fall under this category, as do more fantastical possibilities involving alien technology. If we want to know where FRBs came from, we need to keep an eye out for them. New patterns may appear when more data becomes available, allowing us to differentiate between various theoretical theories. To further our knowledge of FRBs, international cooperation among radio observatories is essential. Researchers may increase the likelihood of making groundbreaking findings when they pool their data and resources. An excellent illustration of how novel astronomical events might test our preconceptions about the cosmos is the phenomenon known as fast radio bursts. As a result, we are reminded that the world is teeming with surprises and that fresh discoveries may transform our understanding of the universe's underlying processes. Fascinating variations from the CMB's normal distribution are known as cosmic background anomalies. The cosmic microwave background, CMB, is a weak radiation that permeates the whole cosmos and serves as a record of the universe at its youngest point, 380,000 years ago. Among anomalies, the Chile spot is among the best recognized. The Planck spacecraft verified what the WMAP data had already found. This area is noticeably colder than the rest of the sky, which might indicate the presence of a supervoid or some other inexplicable phenomenon. The alignment of the CMB's quadrupole and octopole moments is another peculiarity. This alignment of these small multipole moments seems to indicate a spatial preference, which goes against the cosmological concept of isotropy. Another perplexing aspect is the hemispherical power imbalance. The cosmic microwave background, CMB, reveals that the sky's northern and southern hemispheres experience different temperature variations, suggesting a large-scale asymmetry that contradicts conventional cosmological theories. The CMB polarization data has also shown several anomalies. Among them, we find anomalies in the E-mode and B-mode polarizations that point to gravitational waves and density fluctuations in the early cosmos. The standard model of cosmology is not the only possible explanation for these strange occurrences, according to some researchers. Primordial magnetic fields, topological flaws like as cosmic strings, and inflationary era characteristics are all possibilities. Something else where outliers have been found is the integrated Sachs-Wolf effect. When large-scale structures cause temperature oscillations, this phenomenon happens because cosmic microwave background photons travel via potential wells they've produced. Inconsistencies in these fluctuations may point to either novel physics or mistakes in our model of larger-scale structures. Galaxy clusters seem to be traveling in an astrophysically unanticipated direction, according to the dark flow anomaly. This may suggest that our current knowledge of gravity has changed, or that things outside of the visible cosmos are having an impact. Another abnormality is the absence of large-angle correlations in the CMB. Theoretically, huge angular scales should exhibit strong correlations. Nevertheless, measurements reveal no such correlations, which begs the issue of what the early cosmos was like. An anomaly in cosmic background measurements, the Hubble tension is unrelated to the CMB. When there is a difference between the pace of universe expansion as observed locally and the rate estimated from cosmic microwave background, CMB data, it might indicate problems with measurement or novel physics. The CMB data is subject to random oscillations, which might explain certain oddities as statistical flukes. But these abnormalities have been around for a while and have shown up in other trials, so they could have bigger consequences. Better measurements of the cosmic microwave background, CMB, are the goal of future missions, such as the Simons Observatory and the CMBS-4 project. A deeper knowledge of the cosmos may result from these findings, which may shed light on existing anomalies or reveal brand new ones. Data from the cosmic microwave background, CMB, may be cross-correlated with data from galaxy surveys and gravitational lensing maps, among other cosmological measurements. By combining them, these studies may provide a fuller picture of the outliers and how they could be explained. In order to improve our cosmological models, it is essential to comprehend cosmic background abnormalities. The quest for new physics to explain the universe's basic workings is driven by these anomalies, which challenge our present hypotheses. Cosmology is a dynamic field, and the study of cosmic background anomalies is a prime example of this. We still have a lot to learn about the universe and how it all started, and every abnormality is a possible signal in that direction. Possible outcomes for the cosmos are the subject of theories of cosmic destiny. The Big Freeze, often called the heat death, is a well-known idea. The cosmos keeps expanding forever in this model, which leads to the ultimate separation of galaxies, stars, and atoms. Eventually, star creation will come to a halt as the universe continues to expand. Black holes, neutron stars, and white dwarfs will be the remnants of dying stars. In the course of 1 trillion years, even these traces will cool and disappear. Black holes will rule the cosmos far, far away. Hawking radiation will cause them to slowly dissipate, which is a very lengthy process. Last but not least, black holes no longer exist. Most of the particles and photons in the cosmos will have very low energies. The Big Crunch is an alternative hypothesis. A collapse of the cosmos would result from the ultimate reversal of its growth, according to this scenario. A fresh Big Bang or a singularity might occur when all energy and matter are drawn back into an ever-increasingly dense and hot state. The quantity and characteristics of dark energy determine the universe's destiny in the Big Crunch. Constraints on the expansion of the cosmos might result from gravitational forces acting alone if dark energy levels gradually decline. In the most catastrophic Big Rip scenario, the cosmos speeds its expansion to the point where it rips galaxies, stars, planets, and even atoms apart. A kind of dark energy called phantom energy, which becomes stronger with time, is crucial to this idea. The Big Rip predicts that the expansion rate of the cosmos will keep increasing until it reaches infinity within a limited period. Cosmic structures would disintegrate in the last seconds of this terrible conclusion that will happen billions of years from now. A cyclic world is also a possibility that theories take into account. The hypothesis describes a sequence of cosmic events called Big Bangs and huge crunches as expansions and contractions of the cosmos. At the conclusion of every cycle, there is a collapse that triggers an expansion. The problem of a discrete beginning and end is sidestepped in a cyclic world, which postulates that there is no finite beginning or end to time. In order for the model's matter, energy, and physical law cycles to recur, certain requirements must be met. Our world may be one of many, according to the multiverse hypothesis, another possibility. The physical rules and constants that hold in one universe may not hold in another. This broader multiverse and its features and interconnections may hold the key to our universe's destiny. Astronomical destiny ideas are also affected by the idea of cosmic inflation. A fast expansion of the cosmos soon after the Big Bang is postulated by inflation. A number of hypotheses postulate that inflation persists in certain regions of the cosmos, giving rise to bubble universes doomed to different outcomes. According to the holographic principle, a lower dimensional limit may be used to explain all of the information in our cosmos. This concept has the potential to provide light on the universe's composition and ultimate destiny. Aspects of quantum physics are also relevant to ideas of cosmic destiny. different outcomes beyond those anticipated by conventional physics might result from quantum processes that either avoid singularities or change the behavior of dark energy. Our knowledge of the ultimate destiny of the cosmos is constantly being enhanced by developments in theoretical physics and observational technologies. We are getting closer to knowing the universe's final fate thanks to data from space missions, particle accelerators, and telescopes, which help test these hypotheses. In addition to shedding light on possible universe-ending scenarios, research into cosmic destiny enriches our knowledge of basic physics and reality itself. The more we look into these ideas, the more we learn about the history, present, and future of the cosmos. In the Big Freeze, or heat death, scenario, the cosmos keeps expanding indefinitely. According to this theory, all of the thermodynamic energy is eventually spread across the cosmos since it cools down as it expands. When the gas required to make new stars runs out, star creation will come to a halt. At the end of their lives, stars will die out, producing neutron stars, white dwarfs, and black holes. Over very long periods of time, even these traces will cool and eventually become dormant. A universe devoid of stars will be formed when galaxies drift apart and the night sky gets darker as more stars fade beyond the visible horizon. Black holes, which dominate the cosmos, will gradually evaporate due to Hawking radiation. This process takes an extraordinarily long time, but eventually, even black holes will vanish, leaving the cosmos almost empty. When the cosmos approaches maximum entropy during the Big Freeze, all available energy sources are exhausted. The universe becomes black, frigid, and devoid of life as a result of the cessation of all substantial physical processes. In the Big Crunch, an alternate world in which the expansion of space-time turns backwards is considered. This takes place when the attractive pull of all the stuff in the cosmos is stronger than the repellent pull of dark energy. Closer clustering of galaxies and higher densities of stuff are consequences of the expanding cosmos. As the cosmos continues to contract, temperatures will rise and circumstances will revert to the Big Bang. Massive black holes will be formed when galaxies and stars unite. In due time, these black holes will combine into one massive object, which may be known as a singularity. This singularity, a location of endless density and temperature, may be the target of the universe's collapse in the latter stages of the Big Crunch. This, according to some ideas, would trigger a fresh Big Bang, resuming the expansion and contraction cycle. An ever-increasing kind of dark energy drives the Big Rip, a more horrific conclusion to the cosmos. The scenario is predicated on phantom energy, a kind of dark energy with an ever-increasing repulsive force. Eventually, in the Big Rip, the acceleration of cosmic expansion surpasses all other forces, including electromagnetic and gravity. Ultimately, it triumphs over all opposing forces such as electromagnetic and gravity. Clusters of galaxies are the building blocks of this process, which progresses via stars, planets, and finally atoms. Cosmic structures disintegrate one by one according to the Big Rip timescale. Star systems and galaxies are ripped apart in a certain order. Lastly, atomic-level rips tear the fabric of space-time itself. The universe would be ripped apart in a limited length of time as a consequence of this cataclysmic finale, causing all matter and energy to dissolve completely. The Big Rip is a metaphor for the Last Judgment, in which all matter is annihilated. Big Freeze, Big Crunch, and Big Rip are three possible outcomes that show how the universe may end. The properties of dark energy and the overall cosmos density determine the precise result. Determining the most probable of these situations is the goal of ongoing observational and theoretical study. Scientists are hoping to learn more about the fate of the universe by analyzing dark energy and its expansion pace. Gaining insight into these alternative outcomes allows us to comprehend the universe's long-term trajectory. It also emphasizes how basic constants and forces have shaped the history, present, and future of the cosmos. Our understanding of what happens in the end becomes clearer as our knowledge grows. When it comes to the fate of our universe, dark energy is king. Its characteristics will determine the final destiny of all things, and it is a mysterious force that accelerates the growth of the universe. This accelerated expansion of the cosmos will continue so long as dark energy is constant, as predicted by the cosmological constant hypothesis. If this happens, the universe will cool down, darken, and become empty as galaxies separate, stars die out, and the big freeze sets in. Dark energy may evolve in its character. Dark energy may evolve in its character. A slowdown in expansion and maybe a massive crunch in which the cosmos collapses back into a high-density state might result from gravitational forces taking over if it drops. On the other hand, the big rip might result from an increase in dark energy. As dark energy's attractive force increases, it rips galaxies, stars, planets, and even atomic particles to shreds, leading to the ultimate collapse of everything as we know it. One of the most difficult problems in cosmology is figuring out what dark energy is. About 70% of the energy in the cosmos is this mysterious substance, and very little is known about it. The key to unlocking its mysteries lies in empirical observations and theoretical theories. New evidence from sources like supernovae and the cosmic microwave background lend credence to the concept of a cosmological constant. To validate this model, or show how dark energy's behavior changes over time, further data is required. The James Webb Space Telescope and the Euclid satellite are two upcoming missions that will detect dark energy more precisely. With the help of these data, we hope to better monitor the expansion of the universe and learn more about its behavior over the long run. The universe's shape is also related to dark energy's function. The expansion of the cosmos will maintain its flat or open geometry so long as dark energy does not change. The mechanics of the expansion of the cosmos might be affected by changes in dark energy, which could change its geometry. Both the expansion rate and the creation of cosmic structures are impacted by dark energy. It controls the rate of matter clumping together over time and affects the formation of galaxies and clusters. Crucial is the interaction between dark matter and dark energy. The expansion is propelled by dark energy, while the gravitational pull is supplied by dark matter. The structure of the cosmos at large can be better explained by gaining an understanding of their interaction. Examining dark energy also entails putting basic physical hypotheses to the test. Possible new fields or changes to general relativity could give light on dark energy and its consequences in ways that current theories don't. Possible explanations for dark energy may be found in string theory and quantum field theory. More complex relationships between dark matter, dark energy, and the fabric of spacetime may be revealed by these cutting-edge ideas that aim to unite all natural forces. Even the destiny of black holes is affected by dark energy. Hawking radiation will cause black holes to evaporate in a universe that is constantly growing, which will cause the universe to cool and darken over time. Dark energy's influence on the universe's long-term trajectory begs the big philosophical concerns concerning our own existence and what happens to matter and energy in the end. Research and exploration are fueled by these questions. Our knowledge of the history, present, and future of the universe is being enhanced by ongoing research into dark energy. The interdependence of all cosmic events and the underlying forces that control them is highlighted by the function of dark energy in determining cosmic destiny. A trip to the scientific edge awaits those who dare to explore dark energy. With each new finding, the influence of this enigmatic force on the universe is revealed, and our grasp of its nature and ultimate destiny is deepened. The existence of dark energy is significant for the fields of cosmology and physics. Because of its discovery, we have had to reevaluate some of our most basic assumptions about the cosmos. Recognizing the actual character of dark energy is a crucial consequence. It will change the way we think about the forces at work in the cosmos, whether it's a cosmic constant, a dynamic field, or something else totally. Our present gravity theories, which are based on general relativity, could be lacking if dark energy exists. If our current theories are inadequate to account for the consequences of dark energy, we may have to come up with some new ones. Additionally, dark energy has an impact on the universe's destiny. Which big freeze, crunch, or rip it causes is dependent on its characteristics. The fate of the universe can only be foretold with a knowledge of dark energy. According to cosmologists, dark energy plays a role in how massive objects come to be and how they change over time. It influences the formation and evolution of galaxy clusters and galaxies themselves, which in turn influences our knowledge of the universe's past. Understanding the early cosmos is another goal of research into dark energy. The role of dark energy in shaping the cosmos from its early stages may be uncovered via studies of the cosmic microwave background and large-scale structure. Particle physics and dark energy research meet. Novel particles or fields beyond the current standard model of particle physics may be necessary to understand its characteristics, which might lead to significant advances in both areas. Dark energy may be explicable according to quantum field theory. Dark energy may have ties to vacuum energy and quantum fluctuations, indicating a close relationship between quantum mechanics and cosmology. Dark energy could be better understood with the help of string theory, which seeks to unite all basic forces. In order to shed light on the nature of dark energy, it suggests the existence of more dimensions along with new kinds of matter and energy. A fresh round of observations has been launched in response to the revelation of dark energy. With the help of missions like James Webb Space Telescope and Euclid, we hope to get vital information on dark energy by measuring the expansion of the universe with unprecedented accuracy. Another important consequence is that dark energy changes the universe's shape. It determines whether the cosmos is flat, open, or any combination of the three, which impacts cosmic evolution and the possibility of multiple universes. There are ramifications for basic physics in the research of dark energy as well. It calls into question our assumptions about space-time, energy, and the universe's underlying rules. An important field of study is the connection between dark matter and dark energy. We may learn more about the universe's makeup and discover new physics if we can figure out how these two parts interact with each other. The hunt for a universal explanation of everything is not far from the reach of dark energy's consequences. In order to unite gravity with the other basic forces, a full comprehension of dark energy may be required. Lastly, investigating dark energy highlights the value of multidisciplinary studies in expanding our knowledge of the cosmos. The key to understanding dark energy and its far-reaching scientific consequences lies in the collaboration of astronomers, physicists, and cosmologists. In this all-encompassing investigation, we dove into the intriguing past of the cosmos, following its beginnings at the Big Bang all the way to its possible final destination. In order to create the framework for the universe as we know it, we started by looking at its early circumstances, the inflationary phase, and the creation of basic particles. We continued by going over the history of the early cosmos, which includes topics like primordial nuclear synthesis and the creation of hydrogen and helium. The importance of protons and neutrons as well as the quantity of light elements were investigated. The formation of the cosmic microwave background, a crucial piece of evidence for modern cosmological theories, and the shift to a transparent cosmos during the recombination era were both illuminated by this. From the first three-star populations to the intricate structures we see today, our exploration of galaxy formation and evolution continues in great detail. Galaxies, their interconnections, and the structures they create on a huge scale, such galaxy clusters and the cosmic web, were discussed. This revealed the intricate structure of matter at the largest scales. We also explored the enigmatic elements of the cosmos, including dark energy and dark matter. We spoke about how they were discovered, what evidence there is, and how they will change the course of cosmic development. We looked at many models and theories of dark energy and dark matter and what they may mean for the structure and destiny of the cosmos. The next thing we did was to bring attention to important phenomena like as gravitational waves, gamma-ray bursts, and quasars, all of which reveal the most intense and extreme processes in the universe. These findings are fundamental for verifying our hypotheses and comprehending the violent and dynamic features of cosmic development. We also discussed how computational models and sophisticated observational methods have contributed to the field of contemporary astrophysics. Through the use of these instruments, scientists are able to simulate intricate processes and make exact observations, expanding our horizons of cosmic knowledge. Lastly, we went over some of the potential cosmic aftershocks caused by the mysterious dark energy, such as the Big Freeze, Big Crunch, and Big Rip. The nature and actions of dark energy determine each of these possible outcomes for the cosmos. We appreciate you coming along with us as we explore the history, present, and future of the cosmos. Please hit the like button and subscribe to my channel if you found this video interesting.